been associating with university stalwarts like Dr. CSK, who is well known for taking a lot of initiative to bring together the celebrated, I will not just call statisticians, they are the innovators, they are the contributors, and they are the useful parties, the change of lifestyle and change of digital system that is, and such people in this platform is a honor of Dr. CSK's initiative and the university that in taking to tell this topic on distribution theory and estimation. I find it's a big problem everywhere on the prevalence estimation. When it's a lot of issues of disease where people don't even come forward to seek
Probably our Perumal sir is checking.
will you please, Dr. Ashish Sengupta, switch over to session because I don't want to take their time, and Dr. Arnold and Dr. Ashish, you can definitely come back to us, and we are all waiting to hear your questions on the winner. Of his, the problems in estimation diseases on that to 2019, 20 years trend, but this region trying to say how the statistical data help and planning strategic, the analytical estimation and statistical distribution. Will have confidence into it, and it is always for mean or this having uncertain which they take out of 1,000 people, two and a half, I mean 2.5 percentile point and 97.5 percentile point, and they found the tolerance interval, and from that how many people are becoming risk factors to IHD, ischemic heart disease. The study says that it is increasing. The ischemic heart strokes to adolescent is increasing, but these neurological strokes, which is something like problem like a part of the body not functioning. So that increasing, but they said IHD is increasing. The risk factors they have found out of 218 risk factors, 8 are very significant and validated with the study immediately looked at it. I recall our in going through USA, that is about where reading articles are accepted, and it is open to all global health. There are 8 factors they have told for ischemic heart disease. That is where the adolescent are subjected to heart problems, and people in the prime age of 30-35 also having. These are all entire analytical work of 20 years of about 59 countries with 219 variables. Definitely one medical professional cannot do. Only the people from the statistical field can talk about these uncertainties. The 8 factors that they have told out of 219, and India is also in the middle, Southeast Asia, middle, we are included. And much more risky countries are there, like Zambia and Middle East also. Also, they have given 8 risk factors. One is vitamin A deficiency, body mass index, alternative breastfeeding. You can imagine that how today it has become a trend that mothers are also equally busy in their lifestyle, and they are modified. They could not find time to feed their own children, infants, and that when they go for alternative breastfeed, it is another reason for IHD. And the third one, they told about fast foods, saturated food. These are the three important ones that we should take care. India also. Four are all related to demographic factors. Gender doesn't matter. Earlier, it was believed that female in the menopause, but these are all what I am trying to say, an estimation of prevalence estimation. This prevalence estimation and the distribution is becoming a challenge. How do you estimate this based on limited sampling studies? Can I go ahead, or what do you say? Or any paper we can talk? Because talking how,
Yeah, Professor, I see Professor Ashish Gupta in the
okay,
but whether the right time at 9:55, or is it necessary to change
Dr.
Professor
Ashish,
Barry?
can you talk now, because
Yeah,
your time
yeah,
was
I
9:50.
can do that. Uh,
Can I introduce you now, Ashish?
yeah, you can do that. I mean, if
Right.
you want to,
Thank
I
you.
can go
Thank you.
ahead. I think we don't
Yes.
have much of
Thank
an
you.
option.
Yes.
I
Okay.
saw
Okay. Okay.
Barry on
Because
the screen. He is there. Somehow the
Okay, okay.
connection is not working. That is the
Yeah.
problem.
yes, his telephone is also not being picked up. I sent a message to him.
But we saw
Incidentally,
him on the
I'm.
screen, no? We saw him on the
Yes,
screen.
I
He was
saw
there.
him.
Yeah.
Yes, I called him also, but it is not
Okay.
going in the message, voice message.
So
Going in the
let me
voice message.
let me see if I can share the screen first. Okay.
Can I share my screen?
Yeah. Let me share my screen. share the
Introduce you.
yeah. Let's see if we can share the
Okay.
screen. Is my
It
screen
is
coming
there
out?
in that itself.
Yeah, so that's what I'm trying to do. If I can share the screen,
Okay, that's great.
but it's not coming up. That's the problem.
Oh, well, you go to the share entire screen and then share
Yeah,
it.
that's what I did. I did go to the share entire screen.
Then there will be one icon. Click on that. Then again share.
Yeah,
One dark
that's
icon will be there.
what happened. I
And then
just had, unfortunately, a virus attack just now in my main computer.
oh,
Oh,
Now I had one, so change my computer into this new one. This one. I was looking at some paper and then suddenly.
whether we need to
Can you?
whether any help from our side you request, please.
No, I have to do it myself because I'm trying to share the screen. It shows in my screen, entire
Yeah, yeah.
screen.
Right.
I put the entire screen. Can you see anything on your screen?
Then can
nothing.
yeah,
We are not
pop-up.
seeing.
Let me maximize the screen if you can see anything. Can you see anything now?
No, not professor. You can
No.
just entire screen. Then that share button have to whether it is active
You
or not.
have to, share button is highlighted in the
Yeah.
icon. Entire screen. Then there is one icon. No, on that you
Yeah,
click
so I'm getting
black
the
dark icon.
entire
On that,
screen. Entire screen is there.
on in that then
I'm
one
trying.
dark black icons.
All. I am on
Okay.
the screen. I can see you all.
Then sharing, it's only a arrow mark. You click entire screen. Then that this
Let
one
me try
will.
again. Give me 1 second.
Yes.
Let me see. What
Yes.
can
Please.
let me try one more.
Yes. Chat
Because it
box.
is a
Can you
hyperlink.
chat box? Can you
It's a
write?
hyperlink. Let me try first. Okay, let me try
Okay.
if I can do
Okay.
anything. Okay,
Okay. Okay. Okay.
that is the
Can
main problem. I can go back to my original computer, but it will be from time to time giving me this virus infection note.
okay.
This is strange, really. How come? Nope. What is this black thing?
Can you send a message in chat box? We'll see whether it works.
In the chat box?
Huh? Just send a greeting.
This is not moving. Oh, it's not.
Mm.
That's another option, but I
Yes.
don't know.
If you
Okay,
restart
but
the
I got the
grandma
screen and I got everything. Restart, okay? But see,
Okay.
this screen
I think if nothing works out, you allow me to present. I am ready. I can present.
Okay. So in fact, I'm Professor. Professor
Okay.
back. Yeah. And otherwise, some people from medical side probably joined by that time for your professor for your talk.
Okay. Okay.
Professor Ashish, will you please try. And in case of difficulty, Nikhil will help you, Professor. Don't worry.
No, I'm trying. See,
Okay, Professor. Okay, now it's time. No problem.
you can see me, right?
Yes.
Yeah, we can see you. We
Okay.
can see.
Yeah, so that's everything is working, but somehow your connection is not coming through for the. I'm trying again. Okay.
Yeah, okay, Professor. Okay, go ahead. Okay.
So there's an arrow which says the.
Yes.
I brought my third laptop. If doesn't work, I'll
Wow.
try to use my third laptop.
Okay.
Okay, here's
Now
an
it's-
entire screen.
Yes. This.
So I'll put the entire screen now. The same thing hopefully will not happen. Let's see. Okay, I'm clicking on the entire screen. There comes the entire screen.
Then there is
Now,
one dark. Then there is
so,
one the middle.
yeah,
Click on that. Below highlight.
Share button will be active so that you can.
it's so many times, but this
Oh. Below bar is bold.
highlight. Not only that,
It is
but
in
I
blue color.
do not see any black buttons.
Blue
That's the
color, yes.
problem.
No, blue color below share will be there. That will be highlighted in blue color. That will get highlighted only when you click on
Yeah,
the
yeah.
center screen.
I'm trying to click each and every button. So
The center screen, if you click it, the share button will get highlighted.
I have clicked on the shared one, but it's not coming up. I've clicked on the centered screen.
Then share will get highlighted.
Yeah, I've clicked on it.
Oh,
There is some system problem.
yes, there is an
Let,
operating
I'll try.
system.
I still 10 more minutes. I'll try my third laptop. Okay, let's see
Okay,
if
right.
it works because the first
Your
one
file
got.
is-
This
That
is
is
after
strange, Satish.
restarting.
Yeah, no, I did restart as you mentioned, Professor
Okay.
Rajagopal. I did that.
Okay,
I restarted,
okay. Then there is
but
some
then,
OS problem.
huh?
There will be some OS problem in the laptop.
Could be. That is what I'm wondering. Could be some problem there because it's not becoming active. But
Okay.
you can.
We are seeing you, yes.
But I.
Can't change the link. We send another
No,
come on
no.
that. Is that
Let me
possible?
change my
Yeah, we
laptop
have
one
to
more
take
time.
send it. Okay.
Let me
We have
try
to change.
my other laptop first.
Okay, sir. Okay.
Let me try my other laptop because
Okay.
when I'm trying to.
Can we do one thing? Meanwhile, can we invite the third speaker and we can join
Yeah,
speaker
that would.
slowly.
Yeah, that would be
Okay.
much better.
Dr.
Yeah.
Seeker, Professor CS, Professor CS, sir, are you available?
Yeah, Professor, I'm here.
Can you ask the third speaker?
By the time
He will be ready.
just got
Dr.
a,
Ashish will be ready.
yeah, okay.
He'll
Uh,
be ready in another 5-10 minutes. He'll be ready. We can ask the third
in
speaker.
fact,
No?
so there is time say, to start. In fact, so by that
Okay.
by the time Professor Ashish time, he gets ready and no problem, Professor.
Okay.
So timing will in the chat box. Will not,
Okay.
will not
Right,
happen.
right.
Just
Okay. He's
technical issues.
also a
I
difficult.
as expert.
Okay.
ব্যারি আমার আগে ব্যারির কন্ট্রোল হয়েছিল তো আমার হয়েছে।
ওখান থেকে কোনো সমস্যা হতে পারে।
Ashish Sen Gupta, who is already well known in the not only in Indian Statistical Institute, also worldwide. And is that he is the principal investigator of the participant of intelligence
for p belong to the integer value. Equation I am because mentioned as I go let me see otherwise the symmetric we'll talk about the symmetric stable and the Linux distributions, okay, and wrapped versions, but this can be extended to the unwrapped situation. So here are the characteristic functions, and the density function. Similarly, here is the characteristic function for the Linux and function for the wrap Linux. Since you do not have it cannot be incorporated here. So we need to go into non-likelihood based, and that was given by Hill in a classic annals paper in 1975. Later on, by Dufour and Coates came into. It says that you take the order statistics, n plus 1 minus j and xn minus, take the logarithm, take the average, get where is the number of terms you are adding to. Now, k I have is the number of observations lie on the tails of the distribution of interest, and optimally chose. Obviously, can take values into this estimate. So this is one of the serious, but this alpha function of the input. So that obviously creates a problem for it. But with the
I think
why
there's
is this
some
not coming?
audio problem to call. He's continuing. So we left mainly probably because network.
You were showing the paper. Financial risk management paper he was showing.
He will join soon, so sir. Right. It's a
long time. So you have to so this is for the apps compared in details. These have been all these estimators have been called. Here is one that the our approach of the moment-based estimators, the WSR over here that we get TTM estimator, gives you the efficiency, better efficiency, both in terms of the bias, in terms of the root mean square error. Finally, the last example, these examples are and the Gen case, the common, which is a very that we take gives us the assumption dependent. In its closed form and asymptotic test
It's very
2 3 minutes that now and
identification estimation, this and our classical statistics, whatever you studied so far, is based on only four that all our statistics, the unstructured database and high dimensional and highly correlated variables, particularly when they're dealing with biological variables. And big data, not only physically, we are making one assumption that the intention is pretty much far than only big data analytics. And so the aim data collection with many measurements, not one will be relevant. The aim is to find the relevant variables from class deals with the and measure these all if for fix have 65,356 variables in terms of variables. Suppose you are having a color image, it is power 3. There's 65,000. So many variables will prepare a single image. Remember the dimension. Then next one is the microarray data, which revolutionized the field of what you call high dimensional database analysis from 2000, because it started only in 2000, statistical analysis. Here you can see the number of, I can able to get using a microchip, I can able to get any information about 15 to 20,000 third one the next one is the messages for 2,500 variables. That is, they got 250. One thing, the ham database, ham 10,000 database, you can have this one, image, cancer image database, where we're having about 10,000, more than 20,000 for each, this one. These now to reorient all our we borrow the concept of machine learning. That is the idea of this lecture. No, the so what in a big way still it is continuing. It is the area where a lot of expertise is needed, because it is extended like because you were your vehicle having genome, you is that you have a cancer. This is the message I want to give. Now, the statistical methods for high dimensional data started only after microarray of 2000. A single omics experiment, thousands of hypotheses are tested simultaneously. Each based on very were shown to perform poorly. Simultaneous consider of many if I cannot develop, classical example is principal component. So that some fixed number of handful number, you can use the transformed variables, whatever the latent variable, as this one for classification purposes. Okay, but problem is I want to identify the genes which are associated with these individual things are there. Formerly, what we used to do about 20 years back, we used to look at the loadings of this one crudely. We used to pick it up. Nowadays, we got a lot of selection methods. So here, we the people we start principal component. This one. Now there are a lot of non-linear. We got a lot of non-linear. We got a lot of non-linear things. These are the recent developments. Kernel PCA, then T-distributed stochastic embedding, the non-metric multi-dimensional scaling, and isometric mapping, the what you call the isomap. And so these are the recent this kind of which are then method. Of course, we know partially square. One of the important methods they are using, discriminant analysis. Then genetic algorithm, set of variables from a lower set. Now the extension have been from this one recent extension, artificial neural network based bottleneck methods, non-linear iterative partially square, then a neighborhood component analysis, then SATIS and particle swarm PSO. So these are the things that has been used, particularly the green ones, for the IDAM, the recent biological databases. For any database where we are having different scales have been merged this one. So what you have seen so far, these can be broadly classified under 5 categories. The filter type of method, I think even the previous speaker talked about the regular method. Then hybrid method, combination of both filter and this one. Embedded method, because embedding is one of the important. Use classical methods like what you call the rather is the class. So subset and take the best subset. Then embedded method, you create a model for the data with all features. Then based on the model, ensemble method, as I said, subset into those problems with a different focus, one with inductive inference and generalization. It differs from data scientists because we are having statistical thinking set statisticians apart from data scientists in 3 ways. This is the first thing. Data scientists qualify their use with the measures of work with available data, also design studies to provide data to our right information. So that is a very good order. The next, these are the theory associated with this, where vectors. Support vectors, because you cannot. Yes. Can be embedded into your framework, can be reduced to a finite. Yeah.
One to assume normality. Generally, is being ignored here. Cut is much debated. Here, normal not follow the norm over nature. This find this limitation Curtis as a measure of the required of the distribution along with the peak. Together, aspects contribute to Curtis. Intrinsically contour distribution. Curtis generally detail not the peakedness alone, but also the tailedness, the tails, nature of the tails, which important role in deciding the kurtosis measure of a distribution. Kurtosis feature finds relevance in several real-time scenarios. It supports discriminated candidate doctor currently in business. Harnessed by Campany 1981, which gives a mathematical formulation for representing these authors some property elliptically symmetric and contrast these because my normal distribution is elliptical symmetry. They compare the properties of the new family with the multi-normal distribution. Bagneto et al. 2017 focused on the curves and constructed a class of leptotic distribution for the formation suffers from mathematical discussed by Bagneto et al., but it is a totally different class of distributions, which includes not only the leptoc
Excellent talk. We are very much grateful to you, Dr. Manoj Kumar. And in fact, Dr. Raviraj has not joined due to some technical network issues there in their place. Anyway, if possible, we can reschedule. That's all. We extend our gratitude to both professors, Professor Dr. Manoj Kumar for your nice talk, and Professor Rajan sir for chairing the session in a very interesting way. Thank you so much. Thank you so much. Now we have a lunch break time. Now it is time 1:30, 1:28, 1:30. So up to 2:10. So please join by 2. So that 2:10 itself we can let us start the next session. So half an hour break for the present in this hall. In the other halls, the sessions are going on. Okay, thank you, professors. Thank you so much for your support. Let us start the next session. Indian time, 2:10. Thank you, professor. Thank you so much. Bye.
Thank you, sir.
Thank you. Thank you.
Hello?
So good afternoon, sir.
Namaste, namaste. So this is my session. Here is my session. Eh?
Yes, sir. His session is here only.
Because there were several links. I was wondering which one I should choose.
Yes, sir. Main link we have to come, sir. Main link.
No, randomly I'll just choose.
Okay, fine, sir. Right, sir.
Anyway, so it was the right one.
Is the right one, sir?
Yeah. No, the first choice itself was the right one. So there was no problem.
No issues. Yes, sir. Exactly.
Since there were so many links, I just thought of clicking at the first one itself.
Yes, sir. Yes, sir. Yes.
So how are you?
Yeah, doing good, sir. How about you, Professor?
No, I'm okay. There is no problem with me.
So,
my health is okay.
Nice meeting after a long time, I think.
Yeah, we didn't. No, I will one day come there to just. You do not have to worry about the financial side or anything. I will come and talk to your students.
Definitely, sir. It's always welcome. Just to make a call me, just to give a call to me, this will arrange for you.
Yes. Okay. Thank
for
you.
accommodation and everything. Then
Okay.
you can come and talk to students.
Professor Yagin Thomas was your supervisor?
No, sir. Professor K.K. Suresh.
Oh, I see.
Professor K.K. Suresh from Bardiyar.
Bardiyar. Okay.
Yes, sir. I'm from Bardiyar, sir.
Oh, I see. But you basically you are from Kerala. You are a native of Kerala.
No, sir. I'm from Tamil Nadu, Coimbatore.
I saw. Oh.
I think you wrongly remember the name. I think so.
Yeah, this name is not that common in Tamil Nadu.
It's a Kavi Arasu, sir. My name is Kavi Arasu.
Okay, very.
Yes, sir. Yes, sir.
Sir.
Which place you belong to? Namaste.
Namaste,
Namaste. Which place you belong to in Tamil Nadu?
Sir, from Coimbatore, sir. Coimbatore.
Oh, Coimbatore.
Yes, sir. Bardiyar, sir.
Uh-huh.
Yes, sir. Yes, sir.
Have you met ever personally?
Yes, sir. We have met in many occasions in conferences.
Oh,
I think last time Cochin also, 2023 earlier, we met in. Did you come to Cochin, sir? Yes. That time we met, sir. That time also we met. Sir.
Professor Yagin Thomas is now associated with your department?
No, sir. He is not with us, our department.
Oh.
Yes, sir. Satish, sir.
പിന്നെ ചിലപ്പോൾ നിന്റെ സഹായം വേണ്ടി വരും ഷെയർ കുഴപ്പമില്ലാന്ന് ഞാൻ വിചാരിക്കുന്നു.
Satish sir?
What happened? Yeah. What happens there? There was network issues.
Yes, I said there was some network, some issues. Now I think it's okay. Now it's clear, sir.
Oh, yeah, here it is okay. Okay,
Yes, sir.
Professor. Yeah.
How things are going, sir?
Yeah, everything going well.
Yes,
In
ma'am.
fact, in this session, you have three
Yes.
speakers.
Okay.
Professor Krishnamurthy sir.
Okay.
Then Professor, in fact, earlier, Professor Divanji, Anup Divanji was from ISI was
Okay.
here, but his talk rescheduled because of
Okay.
some issues with him.
Okay.
And
Professor.
then Professor M.R. Srinivasan from our Madras University.
University of Madras.
And instead of Anup Divanji, someone has Velusamy Velu Chinnasamy Shanmugam from USA.
Yes, sir. Yes, I'm here.
Yeah.
Yeah. He is there.
Hi, Kaviar, sir.
Hello, sir.
Can you remember me?
There is a midnight. He is waiting for.
It is a
Yeah.
midnight.
Yeah.
Hello.
That's
Hello,
okay.
sir. How are you?
I'm good, sir. How are you? And can you remember me?
Yeah, this is
I'm
Velu.
Pratipha Gandhivandan classmate.
Yes. You're first student of mine, right?
Yes.
I think I taught you C++, Visual Basic, everything, right?
Exactly. Yeah.
Oh, so nice to meet you after a long time, huh, Velu?
Yeah. After I think 18, 20 years. Yeah.
Yeah, more than 20 years. I think in 2003 we met and 23 again.
Correct.
Exactly.
Fine.
Where are you working, Velu?
I'm working with DirecTV
Okay.
in US,
Oh.
Texas
Texas.
state.
Oh, nice. So still you have contact with your Gandhi Vendan and Pratibha?
Yeah. Pradeepa only nominated me for this conference. I was
Oh.
looking for a couple of international conference, and she recommended me to.
Oh, fine.
Get it.
Nice. Nice meeting. Sir, shall we start, sir?
Okay, I'm ready.
Satish, sir, it's muted. Kind of unmute.
Yeah, Professor. Yeah, I noticed. Yeah, Sangamitra, who is the?
Sir.
Yeah, please, Teresa, you please introduce the chair and do the needful for the smooth running of the session, please.
Okay, sir. A warm welcome to everyone. I hereby welcome you all to the technical session 19 with session chair Dr. Kaviyarasu, faculty at Department of Statistics, Bharatiya University. His research area mainly includes statistical quality control, data mining, and data analysis and analytics. He's a life member and present EC member at Indian Society for Probability and Statistics, life member at Indian Bayesian Society, and he has a lot of international and national publications. We are really lucky to have you with us, sir, sharing the session today. Without delaying further, I once again extend a warm welcome to you on behalf of the organizing committee and kindly request you to take over the session. Over to you, sir.
Please unmute your mic. Unmute your mic, Professor. Please unmute your mic.
Thank you very much, Professor Satish, for your kind invitation. I'm very happy to be in part of this program. Specifically, I'd like to thank Professor Satish sir for organizing this kind of international conference continuously every academic year, twice. So really, we are very happy to participate in this program and to get insight of more information from your various parts of the country. So thank you very much for the initiative, Professor Satish sir.
Thank you, Professor.
And today we have three eminent speakers who have accepted our invitation to join here and to give their deliberation discussions in this forum. So in that note, first I'd like to invite our senior professor, Dr. A. Krishnamurthy sir. So he is presently a honorary director for Center for Research in Mathematics, that is in CMS College, Kollam, and honorary visiting professor, Department of Mathematics, Central University of Kasaragod. Sir is retired from a professor of mathematics. Yes, sir?
No, it's okay.
Kochi University of Science and Technology, Kochi. So sir has a vast experience with, I think it need half an hour to give
No,
explanation about this contribution.
I'll straight away start my talk. That will be better. No need of
Development of
yeah.
statistics subject.
I'll just start the talk. Okay.
Yes, sir. Thank you very much, sir, for joining with us, and we are very eager to wait for your talk, sir. Please, sir.
Okay.
Thank you.
Okay. I'll try to share my screen.
Yes, sir. Please,
I don't know how to. Oh, it is not the way.
sir. You can see that in the bottom there is a hand symbol is there.
Oh,
hand symbol is there. Near to left side there is a button is there.
Oh.
One arrow key.
Oh.
Just press that. A window will appear.
Huh?
A window will appear to you if you press that.
Oh.
Then you want to select what is the item you want to. Then there is 3 windows are there: crop window, entire screen.
Okay.
So you select entire screen. You select entire screen.
Chrome tab, window, entire screen.
You click entire screen.
Oh.
Then select the screen.
Then
touch the entire screen button.
Let me.
Just click the entire screen.
Yes, I'll take the help of my.
Then down there is a button called by share.
Yeah.
Just click that.
Okay. Oh, share.
Whether that share button in blue color is active?
It's enabled. It's enabled.
No, it is disabled. It is
so
not
once
enabled.
You just click the window, then would it enable?
In a dark space.
Okay. Now it is.
Yeah,
okay.
Yeah, that's fine.
So now I can.
I think it's coming. It's coming, Professor.
So now I have to.
Now we can move to the.
Yes. Select the PPT what you want to.
Yeah.
Yes.
Okay. Is it visible now?
Yes, it's visible. It is in the conclusion slide. You go to first slide.
No. There's no problem. I'll rather explain things because I did not prepare the slide as such. But then there is a lot to be presented. Anyway, to start with, my heartfelt thanks to Professor Satish Kumar for this invitation. I actually wanted to come to the university and present this, but somehow there were some problems at home which I had to take care of, and therefore I did not come there. Okay, this is a very recent work.
In fact, we missed you, Professor, yesterday.
Pardon me?
Yesterday we missed you.
No. See,
expected you, Professor, your presence.
I should say I missed all of you. That is what I should say.
Also, I invited Professor Rajan sir to chair that session.
Yesterday he was here. Yeah.
Okay,
so shall I start my presentation?
Please continue.
Okay. So this is a paper on K out of N G system, or can be F system, but I'm describing the G system here, viewed as a multi-server queue. Well, all are familiar with what is K out of N system. It is a very well-known entity in reliability theory. So it has N components, identical, can be non-identical, independent, or not even independent. It can be interdependent even. So when the number of failed items, these are subject to failure. The components of the system are subject to failure. And the moment the number of components reduced to k-1, the system fails. Then there is warm system, hot system, and cold system. I'm considering here the cold system. Cold system has the interesting property that once the system is down, that means k-1 units alone are functional, and therefore the system failed. Now none among the k-1 components fail. This is what is called cold system. So I'm essentially considering a cold system, but we can extend it to warm system and also hot system. It is not difficult at all. Now, there is a specific reason why I chose this topic. Well, I had two Indo-Russian projects funded on this side, on the Indian side by the DST, and the Russian side was supported by the Russian Science Foundation. So I had made a couple of visits to Moscow, where my counterpart team is working in a Trapeznikov Institute of Control Sciences. So during my 2018 visit there, the leader of the team there told me about what is called the HAP system, that is high altitude platform, where it is something like tethered platform. So we have something raised to about 200 and 300 meters above the ground level, and this is supported by, and there is a platform where there are drones which will be actually helping for smooth communication. When calamities occur, this is very important. The help of this will be required in remote areas where telecommunication facilities really fail. And so this was a very important question that they were actually looking at. And then I asked them a few questions to which they did not have an answer at that time. It was on interdependence, but then, of course, I am not going to deal with the interdependence here, but then I just promised them to give a reply to my question by the end of the year, 2018, which I could do, but then I just left it there and then revisited that in 2020 during the start of the corona, and then continued to work quite a bit on that. But this is actually a system where interdependence is not involved. Now, what we have here is not exactly a reliability system. I consider each component as a server. So there are n servers, you can call them parallel servers, but that may not be apt word because k equal to 1 alone can make it a parallel system. So I do not therefore call it a parallel system. So these servers, when they serve, are subject to failure. While they are idling, there is no question of failure. But only when they are operational, failures take place. So when the number of units accumulate to, failed units accumulate to little n minus capital N. Capital N is a number between k and little n. Then we start a service facility for the repair of the failed components. And then it is exponentially distributed. In fact, all the distributions involved here are taken to be exponential because then it will be easier to handle, otherwise the dimension will be increasing tremendously. Dimension of the underlying Markov chain. So customers arrive for service according to the Poisson process of a certain rate, lambda. Then they go to the free server who is operational to get service. If there is no server, operational server who is idling, then the customer will have to wait in an infinite capacity queue. So this process goes on, and then when the number of operational components come down to k minus 1, there will not be any service. This is in fact very important for the HAP system, and the paper is prepared particularly keeping in mind the need of the HAP system, high altitude platform, tethered platform. Though I'm not associated with the currently operated Indo-Russian project because there is some restriction that those who are retired, those who have only at most 3 years to retire, and those who are not in regular service, they cannot be part of the project. So I am outside the project, but giving necessary instructions to my former PhD students. And so this time again, they could get the project. So now our interests are many. The most important thing is the kaplan value. The optimal value of kaplan we are trying to compute. When to start a repair? Once the repair starts, repair a failed component start, it will be continued until all components are in operational state. But once the system fails, and that happens when only K-1 components are operational, suppose by repair, one unit joins, and the service time of these units are also exponentially distributed, the repair time. There is only a single repair facility. We can increase the number of repair facility as well. So now it has come to K, the system starts operating. And then it continues. We have several quantities of interest involved here. First passage time, for example, starting from little n operational units, the time until the first failure takes place. And it is not just that easily computable, because the moment the number of operational components reach kaplan, the service or the repair of the failed component start. It's like that. I now come to what are the salient features of this, and then come to the mathematical modeling. This work is the first of its kind to consider K-out of n system as a multi-server queue. Earlier, one of my doctoral students, his thesis is on that particular thing, which I am going to now say. Instead of considering this as a multi-server, it was considered as a single server. The whole system was a single server. That was how it was considered. But then a failure, that such things were not considered at all. Unlike the classical, no, of course, failure of components will be taking place, but then repair facility, all those things were not given much attention to. Then the second feature is, unlike the classical multi-server queue, the present work, at least K servers should be operational in order that the service can be provided. So in classical multi-server queue, if there are n servers, there is no problem at all. If there is at least one server operational, then the service will be going on. But here, the moment it comes down to K-1, the system totally fails. So this is but then when K is taken as 1, then we will get the classical multi-server queue. Multi-server here, it will mean n-server queue. Now here, two birth and death processes act simultaneously. One is the arrival of customers, and with the service completion, they depart. So it is a birth and death process. Birth and death process because the underlying distributions are exponential. Then, okay, the other birth and death process is the following. The failure of components. From little n operational units to capital N operational units, that going down, it is a pure death process. But when the number of operational components come to capital N, we start the repair facility. Then the birth and death process starts here, because failed components are repaired and then failure components take place. So there is the second birth and death process. But this is on a finite state space, whereas the first one is on a countably infinite state space, because the number of customers in the system, it is an infinite capacity system, and therefore it happens in that form. Now, system under consideration reduces to the classical infinity queue if you assume that the servers, that is the system components, do not fail and that k equal to 1. But then k equal to 1, that k has no relevance at all in that context. Now take the limit as n goes to infinity. We get the classical infinity q. Now we move to the notations. These are the notations. We have the continuous time Markov chain. How it becomes a continuous time Markov chain? That is because all the underlying distributions are exponential. The notations and then mathematical model description. Well, I have already given a description of the model, and we are considering the cold system. Mathematical formulation is as follows. Take any time t non-negative. Then N1T denotes the number of customers in the system at time t. N2T, the number of operational units in the system at time t. R of t, the status of the server who repairs the failed components, which are servers serving the customers at time t. This is again time t. So R of t stands for, it takes the value 0 if the repair facility is off. That means the server who repairs the failed components is off, which means that the number of operational components starting from little n has reached capital N for the first time. Now the repair facility starts. So up to that time, server is off, the repair facility is off, and therefore RT equal to 0. Now RT equal to 1 if the repair facility is on. Once the repair facility of the failed servers is switched on, it keeps on in that state until all the failed components are repaired and the system is fully functional. That means little n components are operational. Now, what happens is with this description, because all the underlying distributions are exponential, so we have a continuous time, 4-dimensional continuous time Markov chain with the state space described here. And the infinitesimal generator of this Markov chain is represented by Q. And this one, now if you look at the matrix, along the diagonal, what you have is, they are all block matrices. Along the diagonal, upper diagonal, along the lower diagonal, these are all matrices. Now, where there is no entry, those positions are occupied by the zero matrices of the same order. So now what we have is, along the diagonal, what happens is, it is something happening within the system. Within the system, what I mean is, no customer arrival, no departure. That part is taken care of by the diagonal matrix, which means that what is happening, for example, a repair facility, that is either it is off or on. When it is switched on, well, that will be just appearing in the diagonal. And then when a customer arrives, then that will be actually indicated by the matrices on the right side, which are again rates of arrival. Then those on the lower diagonal, they have entries which will be representing customer departures after being served. And the dimensions of these matrices are all given here. Now coming to So there are so many methods. Basically, linear algebra, a lot of that is made use of in this work. Now, in the transition rates, actually, how the elements of these matrices, block matrices within the large infinite dimensional matrix can be got, that is described in this slide. Transitions due to arrival of a customer to the system. So N1, N2, that is number of customers in the system is N1, number of failed units is N2, failed servers is N2, and R is the status of the server. The repair, the server who repairs the failed customers or failed components. So if N2 is not equal to k minus 1, then there is something. That means that the system is operating. Then transitions due to service completion of a customer. So those are actually, the first one is actually having an impact on the upper diagonal block matrices. And the second one is having an impact, that means a customer departure, and therefore it is along the lower diagonal matrices that will be presented. So the rates are indicated here. Transitions due to breakdown of an operational unit in the K-out-of-N system. Breakdown, transitions due to breakdown. That means a unit fails, and therefore what is happening? So that will be along the diagonal, because it does not go to the left or to the right, it rather stays along the diagonal. No customer arrival, no customer departure. It is what is happening within what is called a level. Actually, by level, what I mean is the number of customers in the system. N2 and R are the sub-levels. So transitions within the sub-levels are indicated along the diagonal. Transitions among the first coordinate, that will be along the upper diagonal and the lower diagonal. In fact, N1 becomes N1 when it becomes N1 plus 1, that is because of an arrival of a customer. We have an entry, positive entry in the upper diagonal matrix. Now, transitions due to breakdown of an operational unit in the K-out-of-N system. So that again is along the diagonal. Now, transitions due to repair of an operational unit again it is along the diagonal. Now, stability condition. Why need of stability? That is required because we have an infinite capacity system where the number of customers who can be accommodated is countably infinite. So the stability question arises. So we have to examine the stability. Now notice that the system is stable provided, that actually is rather very easy to see. What will happen is, suppose the arrival rate is very high compared to the service rate, then what will happen is the right drift means the number of customers increasing, that will be much higher than the departure rate of customers. So that system loses equilibrium and therefore it just explodes. So what is the condition required for stability, in the sense that it just gets stabilized or it is in equilibrium state? In order to compute that, we have just done the following thing. We define a matrix A, which is the sum of the elements in the Q matrix. We take what is called a repeating part. There is a non-repeating part which is a boundary, and thereafter, starting from a certain level, the matrix A2, A1, A0, starting from n minus n. So A0, A11, A12, so on, A1, N-1. But there is a A1 along the diagonal. So that is the repeating structure. Then we have along the lower diagonal, A2 starts at a so there is no problem regarding that. So that repeating part we just catch hold of. And then construct a matrix A, which is equal to the sum of A1 and A2. And then see the left drift rate and the right drift rate. So this is the A matrix, which is the sum of A2, A1, and A0. So then what will happen is we have the following condition for stability. So this one, lambda is the right drift rate because that is the customer arrival rate. Now the thing on the right side in relation 3, that's the left drift rate, the departure rate. And remember that when all components are operational and if there are more than n customers in the system, customers will be in service. So the rate of departure or rate of service, it will be n times mu, where mu is the individual server service rate. Each server serves at an exponentially distributed duration or rate with parameter mu. So when there are n servers operational, so n times mu will be the service rate. When there are only k-1 operational service, well, the system is totally in failed state. So the stability condition is this. Therefore, lambda, which is the right drift rate, and the right-hand side of 3 represents the left drift rate. So that is essentially the departure rate from the system. Now, steady state probability vector, well, this is computed as follows. We define an R square A2 plus RA1 plus A0. This is a matrix quadratic equation. Solve that and find out it recursively R. That is a procedure. There is a very nice recursive relation to compute that, which I am not explaining here. Now, the special case is the following. One of the special cases is the following. Consider the system in which k equal to 1 and assume that the servers do not break down. The above queuing model reduces this classical MML, that is the n server MMQ, where capital M, first M stands for the post-on arrival process, second M stands for the service of customers, and last n stands for the number of servers. So there is no failure. That is essentially what is assumed. In this case, we get a very simple one-dimensional continuous time Markov chain on the state space, which is the set of non-negative integers. So infinitesimal generator in this case reduces to very simple form, minus lambda, lambda in the first row, all the remaining elements. So all those block matrices are now replaced by scalars. Now see, along the diagonal, what we have are negative elements. And the property of an infinitesimal generator is that the row sum must be equal to 0. There can be negative entries, but only along the diagonal. What is the transition probability matrix? All elements are to be positive, and each row should add to, sum of elements in each row should add to 1. Okay. Now the some system characteristics. For example, distribution of server idle times. This is what does it actually mean? It just means the following. Suppose the number of customers in the system is less than the number of operational units at some time. Then suppose, for example, 10 customers are in the system, whereas the number of operational components turn out to be 15. In that case, 5 servers will be idling. The remaining ones will be serving. So such customer servers or components have idle time. We are now considering the distribution of the server idle time. And that is computed. Again, it is a linear algebra that we have employed. Row vector with 1 at the first, with 1 as the first coordinate and the remaining things equal to 0. And the dimension of this beta is same as the number of rows or number of columns of this Q2. Distribution of first passes time from an operational server state, from an inoperational server state to an inoperational state, inoperative state. So here, there is a first a jump from RT equal to 0 to RT equal to 1, the moment the number of operational components come down to capital N. So accordingly, we have this matrix here. So we have the result that W be the random variable denoting the first process time from an N operational service state to an inoperative state. Then we have the corresponding distribution for that first process time to be phase type. Whereas again, initial probability vector is a chi with the first component equal to 1 and the rest is 0. Distribution, the number of times the system becomes inoperative before reaching the, this is again a quantity of quite great interest. So, because this will be playing a very important role in the optimization side, when to start the repair of failed servers. So, I'll skip these things and just to say the expected number of times the system hits k minus 1, that means becomes inoperative before reaching the N server state, operational state, optimal capital N value. So that we have computed here. There is a results in this one. A typical two and then close the presentation. Yes, what is it? On top. To see, we have a graph. Just to
Thank you very much. Now let's move to the next speaker. So our next speaker is waiting for a long time. So he is none other than Delu Chinnaswamy Shanmugam. He is he was in US America. I think it's a midnight, 3 o'clock. He was waiting to talk to the listeners. So thank you very much for your patient listening, Velu. And also on behalf of the organizing committee, I welcome you. So he is an principal of advanced analytics as a director, Direct TV, a leading American multi-channel video distribution platform based in California, USA. He is accomplished analytical leaders for 18 years of experience applying data science and machine learning across various industries. He is adapted translating high-level business objective into tangible analytical frameworks and strategies. So such an eminent speaker has accepted an invitation and came over here to give his talk. So on behalf of the organizing committee, I welcome you, and the session is for you, sir. Just give your talk for 20 to 30 minutes, and then later we have 1 or 2 questions with the listeners. You can.
Sure, sir. Thank you so much. Thank you very much. Let me share my screen.
Well, it's visible. It's visible.
Oh, you can see it. Okay, perfect. Okay, thank you. Thank you so much for the opportunity, and thank you, sir, Kavir, sir, for giving a wonderful, the intro. So it saved me maybe 1 or 2 minutes for that one. Thank you so much, and thank you so much for the opportunity for Satish sir, and so I'm really lucky to have this conference, and this is my second conference, so this is really good. And I would like to share my experience as well as the use cases that I'm having right now, challenges, and then we used advanced machine learning algorithms to solve multiple business problems. So today, I want to talk about how the advanced machine learning algorithms are helps to predict customer churn in specific business use cases. And before that, I would like to talk about types of analytics that we focus in our company, and where actually the advanced machine learning algorithm or advanced data science models that we use it. So first one is the business intelligence. This is where the top executives, they spend a lot of time going through the dashboard and historical performance, everything. But we don't really play any major roles here, but we definitely use those historical data to predict for the future. Descriptive analytics, this is kind of a second level of analysis that we do for creating a segmentation, clustering, and customer journey analysis. And this is also kind of profiling and the attribution model type of analysis. And these insights that goes into the model, data science model, that's where we use for the predictive modeling. Yesterday I was talking about the sales forecasting, and today I would like to talk about churn models, how much we struggled and how much that advanced machine learning or data science is helping to improve the customer churn, and that drives the business value and the revenue for the company. Optimization, this is more like a product level team, but we still help them doing market mix modeling, pricing models, and a lot of other stuff attribution model for them, also campaign analysis for how the marketing campaigns are doing for them. So a lot of analysis we do, but our main focus area, the predictive modeling, that is where we use historical data, and also we predict for the future to share with the business. And I'll quickly move on to the next slide. So business objective, we want to build propensity to churn models using machine learning techniques to identify the customers who are more likely to churn using the internal and the external demographics data. So that helps identifying where the pressure is coming, why the customers are leaving. And that is where the attribution model plays a major role here. So we use 200 to 250 attributes into the model, but we definitely need to know what attributes are actually contributing, why the customers are leaving. We also customize our marketing strategy, and that helps for the marketing team to target them. So there are these are the marketing channels that we currently use: email, in-app, SMS, direct mail, and retention calls is a major role for them. Okay, so what we use for the churn prediction, we used multiple models from logistic regression, gradient boosting method, XGBoost, and also multiple algorithm. But what we choose random forest is the most important, and then it predicts very well. So because the random forest classifier is an ensemble supervised machine learning techniques for the classification task. So it operates by constructing multiple decision tree during the training. When you're training the model, it takes it splits the multiple subset and then fit the model for each subset, and each decision tree develops. So that is where it definitely predicts better than the other algorithm. And the random forest algorithm is also uses the bootstrap sampling of random training data to train diverse and then the create the decision trees. So yeah, if you look at the final the churn from the classification model, so probability of churn, this is the equation that we use, but we include a lot of attributes into the model, more than 200 attributes, and so n is the number of decision trees, and you can get the sum of tree classification, how many 0 1 classification for each decision trees. So based on this, the model takes care the overall model average classification from all the trees. If it is a closer to 1, then the final random forest classifies that the customers are more likely to churn. So that is what we get it from at the end of the model, and then we use that propensity model, propensity scores, to create a deciles or create a segments that helps for the marketing team to target. So I'll explain you where I'll show you how we create a segmentation or the deciles to target the customer. And before that, these are the key benefits that when you use the random forest. These are the based on my experience, our current project that we are working on. These are the most important, and most of the data scientists struggle here actually. So, but random forest takes care giving high accuracy, because the random forest combining prediction from the multiple decision tree and then averaging the predictions. So that is where it is significantly improving the predictive accuracy. So that is the very, very important. Everybody is want to build a model and then see how accurately predicting, right? And it also takes care of overfitting, but still when you we are inputting, you need to take care how many variables is there any direct correlation also. So that is what important for whenever, but still the random forest takes care, but better. We need to have a business knowledge also to take care of removing a couple of attributes, right? And feature importance, and when you have the random forest, it gives you top 15 or 20 attributes, and then it gives the ranking also for the each attributes. So that is really good to have that metrics here. And handling missing values. Missing values is also good. Missing value is good, but better to have some extra the combining algorithm. I'll show you what algorithm we use for the missing values, so that if you clean them, I don't know if it is missing, if you create separate attributes or separate category levels, then the model learns better instead of just giving the missing values. So no need to any scaling. It takes care automatically normalizing all the attributes, and then it can be also parallelized. So we have 15 million users, and it in and then score the model, right? For that, what we do, the use a for each function using R. You can have a creating multiple jobs instead of one job, one thread running, right? So you can parallelize or do a multiple jobs, then that takes care, and it is also faster than the single thread models. And so when you have more attributes, so you need to know what attributes are correlating and what attributes are how much the predictive power comes from the each attributes, right? So it is variable importance, and then you also do a profiling. So we call it attribution modeling. So we take all before we build the random forest, we need to do most of the data scientists spend a lot of time on analyzing the attributes, right? So but what I did, I wrote this paper in LinkedIn, but so this is really beauty, using the weight of evidence and then information value. You can use these attribute these algorithm to one, you can bend the continuous attributes. So tenure, age. So what you can do, when you use those attributes into the model, you may know whether it is positively impacting or negatively impacting. I don't know. It's a good variable, but the business side, you have to explain to them. Okay, when you are saying the age is very important, they need to know what age group the customers are churning. Right? That's where it is helping using the weight of evidence and information value. So weight of evidence value, it is a natural logarithm that takes percentage of churn events and the percentage of active non-events. So this is the formula that we use for calculating the evidence. So you see the right side the table, it shows the positive, right? Positive means directly impacting. So the low income users are more likely to churn because the economic is performing very bad, and a lot of people losing jobs, and they don't have money. Every month they have to pay $150 to $200 for having the subscription TV, right? So that's where this is the two category less than 100K. That's where we are seeing a lot of pressure from the customer side. And you see the information value above 0.3, that is a strong predictor in the model. So this is what the information value, the formula is there here. So it helps to improve your predictive power for the each and every attributes, and also it helps you to group the attributes. For example, if you have the zip code, or if you have a demographics data, so you want it has more than 53 or 60 category levels. So random forest doesn't handle more than 50 through category. So that's why better to group them, or create a k-mean clustering groups and then use it for the model. So that you can increase the predictor instead of just dropping that attributes from the model. So next, these are the data source that we use, internal and external attributes. And mostly for churn, the internal attributes are very, very important. So how much they pay and what plan they use, or what are the segments there, how many boxes that they connected, and what DMA they are in, so where the pressure is coming. So these are the very, very important, is that the new customers are churning, or no, the old customers are churning. So this is where very, very important. This is directly for the marketing team working on these attributes. So this is when you build the model, we need more weightage to these attributes. Verifying the right data, cleaning the data, and then create a segmentation or do a profile analysis for the management or the business team. And then this part is just one line of code, and you can use Python or R. It is just one line, but you have to be very careful what data you give into the model. That is where they're important. And so it is, again, when you have everything, then you are just giving to the machine learning algorithm that automatically takes care. And then when you give the input layer, it identifies the best fit and then gets the final propensity score. So once you have the propensity score, you create the segments: high propensity churn, medium, and the low propensity. So when it comes to targeting audience, we recommend high propensity and medium propensity to target them. So if it is their high likely to churn, then they are going to give some higher offer or higher promotions to retain them. So this is very important. And this is where I was telling, if they are highly active, we don't want to tell or give any promotions to them. And finally, the model building. So we used 80-20% for model. So 80% is training model, 20% is the validation. Since we have the huge sample, so that's why we just 80-20. If you have an unbalanced and something, if you want to balance and then predict, so we use 60-40 on that case, because we need for validation also more samples, right? So and then target variable 1 is churn and 0 is active. Algorithm and then overall model accuracy we got 97. We know little bit multi-columnarity is there, but the business said we are okay with that, because they want to go with higher accuracy. And then that's where we focus only for the positive predictive, negative predictive value. So if it is negative, that is 98, because more customers are more likely to stay with us. They don't want to leave. But positive, it is really hard. And 88.3%. That is where we are able to predict. Here is the code that I used. So these are the libraries, and then train and test data, and imbalance data set. So if you have an imbalance, then make it random sample, take it, and then the balance, and then use that for the model. So I was telling you the forecast for each. This is the you can use the parallel jobs instead of single thread. You can do parallel is the library, and then you can register how many core you want to, how many cluster you want to split the jobs. So 15 core I'm selecting and then running the model. So it uses 30 into 50, so 1,500 trees it develops within the model. So it's huge, but still takes care because you are doing the two parallel jobs. And you can save the model for scoring time. So every time you need to have that one predict, and then classification. Confusion matrix. So confusion matrix is the one we always follow. I know a lot of other metrics we use, but confusion matrix is we focus type 1 and type 2 error, false positive and false negative. We want to reduce this type 1 and type 2 error. So that is the goal. And here is the confusion matrix. It gives the sensitivity, specificity, positive predictor, negative predictor value, everything. So, and you can also calculate. We don't really focus precision and precision side, but recall and all. But we only focus type 1, type 2 error in this case actually. And the last slide. So when you have the propensity score for each individual customer level, we create a segments, high, medium, low. So the high is always 0.60 to 1, so that is high propensity to churn. This where we recommend to target these customers actually. And then medium and low. So low, I'm okay if I'm missing any customer and then I'm not targeting. But I should not predict false positive rate is higher, and then we simply ending up giving more offers to those customers, right? So that is very important in here. And that's all from my end. And any questions?
The floor is open for any one or two queries. As well, you said that you're talking about random forest methodology, right?
Yes.
So is there any specific reason to choose only random forest, or have you tried any other algorithms available?
So I used logistic regression as well, but the problem is a lot of overfitting, multi-collinearity issues are there.
Okay.
And also we have more than 200 attributes into the model. So what happens it struggles a lot, and then it overfits. That's why we don't want to use that for the logistic regression. And it also when it comes to scheduling, it takes 15 million. When you score 15 million, the random forest is faster than the logistic regression.
Okay, but the logistic can apply only in the case of binary case, right? When it's in the main variable should be in the binary. Whether your data is follow that kind of situations?
Yes, this is also churn. If the customer churned 1, else 0, the action is 0. So ours also binary. Yes.
Yes. Okay. Fine.
So we have a random forest as well as the random forest regressor.
Okay.
So random forest regressor is used for the forecasting.
Okay. So which model gives the best fit for your data?
For random forest gives a better because we focus only for the type 1 and type 2 error, right? We want to reduce that error, right? So this gives a better accuracy for us. And the XGBoost also gives very good accuracy, but a little bit higher on the true false positive rate. So that's why but very close, only maybe 1 or 2% difference, but both are really performing better. Maybe for my use cases, this random forest is performing better, but some other business use case, maybe the logistic regression
might be better case. Yeah. So it depends upon the data set what we are taking into consideration.
Exactly.
Okay, thank you very much, Velu Sinnasamy, for your nice presentation. It was very useful for the listener. Hope our students and scholars who are listening in this online meeting may get benefited how to apply your random forest algorithm through R or Python. Whatever the language they want to perform, they can apply such kind of situations. So on behalf of the organizer, I wholly thank Velu for your valuable time with us. Even the midnight you are spending with us and sharing your thoughts and ideas to the forum. Thank you very much.
Thank you, sir. Thank you very much. Thank you very much for the opportunity.
So now we have the another important speaker, our Professor M.R. Srinivasan sir. Sir is going to talk on post-hoc analysis and design of experiments. Professor?
Can you hear me?
Yes, sir, I can hear, sir.
Yeah, okay. Okay, then. Thank you.
So I just want to say a few words about our Professor M.R. Srinivasan sir. Sir is working as an adjunct professor in Chennai Mathematical Institute, Sriseri. Sir has a vast experience and sir was employed earlier as a professor in the Department of Statistics, University of Madras. He got his education in BSc Hons in Osmania University, MSc Statistics in Osmania University, MBA in University of Madras, and PhD in University of Madras. Sir has plenty of assignment as a visiting professor to Hyderabad, University of Naples, Italy, University of Dodoma, Tanzania, ISI Kolkata, McMaster University, Canada, Italy, and School of Genetics, University of Texas in USA, Division of Biostatistics in Washington University. Then he also visiting scientist of University of Manchester of Rothmastad Experimental Stations, UK, and sir has many of academic and administration positions as a chairman, Board of Studies, University of Madras, Dean Academic and CDC in University of Madras, member NAC Committee, member Backward Class Commission, Government of Tamil Nadu. Sir has guided more than 18 PhD scholars under his able guidance, and many scholars are benefited apart from this 18 students under his leadership. So Sir has published more than 90 articles in national and international journals. Sir has deliberately delivered invited lectures in India and abroad, including many endowment lectures like M.N. Das endowment lecture, etc., etc. Sir is a member in the Institute of Mathematical Statistics, USA, and Sir was then elected and made our statistics community a proud moment to the elected as the International Statistical Institute in Netherlands. Sir co-research. Sir is interested in teaching in MSc Statistics, Actuarial Science, and Data Science. So such an eminent personality in his busy schedule accepted invitation and came over here to deliver the talk to the young minds. So on behalf of the organizing committee, I welcome you, Professor, and I hand over session to you, Professor. Thank you, Professor.
Yeah, is it visible?
Not it, sir.
Not yet. The screen is not visible. Okay, just a minute. Just a minute.
Yes.
How about you? How about now?
Sir, screen is visible, sir, but the slide is not visible. Slide, I think you have to select.
Slide? Oh, slideshow, you mean?
Yes, sir. Yes, sir.
Is it okay now?
Not yet, sir.
Not yet?
Yes, sir.
How about now?
Did not came, sir.
Oh, okay.
They can see now.
No.
So better you stop sharing and you start again, sir. Do it again.
Okay, okay, okay.
What is the issue? They're not able to see.
Now visible, sir.
Yeah, okay. Okay then. Thank you very much, Professor Taftish, and thank you, Professor Kaviyarsu, for chairing the session. It's a great opportunity for me to interact with a lively audience online. So as you know, my talk is going to be on post hoc analysis in design of experiments. Indeed, this is something which my student who completed his PhD last month worked with me in this particular topic on post hoc analysis in design of experiments. Let me just explain to you what the problem is all about before I just go further into my presentation. See, the usual part, which I'm sure many of the students are aware of, when you carry out your ANOVA, which is going to be a comparative experiment, 1-way, 2-way, 3-way, and whatnot way you want to do it. Probably you can go further to design of experiments in factorial plans and so on and so forth. So you are basically interested in comparing multiple means. Let's say you have 3 means, mu A equal to mu B equal to mu C. So you have a data available to you. Use this particular data, set up a particular model, an appropriate model, whether it's going to be a 1-way model or a 2-way model or whatnot, which is appropriate based on your objective. And then you analyze it. And many of the students know how to prepare an ANOVA table. And based on the ANOVA table and using this particular data, they come to a conclusion whether to accept the null hypothesis or not so. Now, when you accept the hypothesis, things are going to be quite easy and sweet for us to work out. Of course, we can just shut the system and go. Now, what happens when we reject the null hypothesis? Indeed, there is a sort of a plethora of work that has been done when the null hypothesis is rejected. And I'm sure many of the books do cover this particular area under the domain called multiple comparisons. So under the multiple comparisons, you have a LST, you have a 2-case test, you have a Newman-Coles test, you have a Duncan's test. All these tests are available to you to identify the culprit which created the rejection of this particular hypothesis. So obviously what we do is, we just go up to this particular point and then we identify who is the real culprit who has created the rejection of the hypothesis. And then what we do is we stop there. Indeed, going through this particular multiple comparisons is in some phrase or in some sense, people call it as a post hoc analysis in design of experiments. So you try to compare and say whether mu A equal to mu B or mu A equal to mu C or mu B equal to mu C or none of these equalities hold good. And there is what your story is all about. And you try to stop there after that. Now, the question that has been of interest to me is, why should I stop here? After all, I have to go further from this particular point of what this post hoc analysis gives me. So I have to think about a model which is going to be a reduced model. And there I have the option now to choose which of those equalities. For instance, let me give you an example. Indeed, this happens probably in a real data, like something you talk about your GRE scores or the GMAT scores and so on and so forth. Many times what happens is there is a tie. There is an equal score. So some sort of a yardstick is applied to give one person a weightage over the other person. It could be in other subject other than the particular examination, like English and other things. Or in some cases, they use the age as a criteria to select one of them, and so on and so forth. So some criteria is adopted to choose one among the equal one, or a tie-up is there. Now, the same sort of a logic here, when there is a set of treatments, let me say mu A equal to mu B equal to mu C, which is going to be a simple one to think about when I have three treatments. If mu A equal to mu B holds and it is not equal to mu C, then obviously my question, which is of interest to me, I'm going to have a reduced model. Should mu A marry mu C, or should mu B marry mu C, or which one should go with mu C? That is my reduced model. Though both of them are equal, probably based on this particular multiple comparison test. Now I have to choose one of them and decide whether the reduced model is better to be with mu A or better to be with mu B. And then the whole story around what I'm going to talk about is mu B should go with mu C. That's what the story is all about. So be we need the student of mine adoption method to be with the domain of industrial experiments also.
Professor, your slide is not moving, Professor.
Slide is not moving?
Yes, sir. Now it's moving, sir. Now it's okay.
Is it okay now?
Yes, Professor.
Okay, right. So the other part of the story, whatever has done, is basically the classical story. There were quite a good number was discussed, and the probability of D given H0 and probability D given H1. Now, based on this particular one, you have a probability of Hi given D, which you can write down. And now, if you look at the last expression there, it is going to be probability of given H0 into probability of D given H0 by the denominator H1, probability of D given H1. So, this particular D given H0 by D given H1, that particular part is what is called as a Bayes factor. So we are calling it as B10. And you can have different sets of hypotheses, and you can think about what your numbers are going to be or suffixes going to be. So this is going to be your Bayes factor. So what happened is, Cass and Raftery, they started looking at this particular Bayes factor, and they try to quantify that particular Bayes factor. So what they did is they tried to give some sort of interpretation of the for hypothesis H0 or against hypothesis H0, or you can say for H1. And you can see based on the Bayes factor, you can see that if it is this is factor, Bayes factor turns out to be less than -2, then there's a decisive evidence for H0. If it is going to lie between -2 to -1, there's a strong evidence for H0. And you can see that it just goes on that if it crosses or if it is going to be greater than 2, then there is a decisive evidence for H1. So this is a sort of a table which was provided by Cass and Raftery in their paper in 1995. And this particular one has come out handy for us when we try to make use of it in our post hoc analysis in order to assess the strength of a factor which we are interested in incorporating in the model. Now, what we have done is, as far as the present study is concerned, we have considered 5 different priors and used those particular priors as far as the study is concerned. So you can see the first prior which we have considered is the Zellner's prior, Zellner's Z prior. And you can see what is going to be the model, what is going to be the prior here, and what is going to be the nature of distribution there. And you can see the Bayes factor which you are going to have, which is given by this particular function which is given here. So this is going to be one of the priors that has been considered by us. Now we have considered the other priors also. One is going to be the unit information prior if G is equivalent to N, and we have a risk information prior if G is equivalent to K square, and we have given probably this is a Bayes factor for the full model to the null model that was given by Zellner's G prior for UIP and RIC. So this is a second set of priors which we have considered. Now there's a third prior which is going to be Jeffrey-Zellner's Theo prior. So this was to apply to a Cauchy prior, whether a parameter mu is 0 or a non-zero. And the same was proposed to a multivariate Cauchy prior. And you can see the bunch of Jeffrey-Zellner's Theo prior that has been considered. And probably the Cauchy prior was the simplest distribution to satisfy consistency requirements that Jeffrey is considered important for hypothesis testing. So you can see this is a third sort of a prior which one can think about. So here we have got, you can see the Bayes factor function is given in this particular case. So now what is that we have? So my interest is to identify or to examine the strength of the factors under the rejection of the null hypothesis in multiple comparisons. Now, to identify the strength of main bar interaction effects in the analysis of variance, of course, I have just considered only 2 or 3 cases here, and we have probably in his thesis he has considered much more larger models also, and probably he has extended it to factorials of different types and shapes also. So we are interested in looking at probably here one-way, two-way model, and probably a factorial which is going to be 2 cubed. And of course, we have considered 3 cubed and others also. I think I will restrict myself to some of the simple things which are going to be there, probably a 2 cubed. So here the study tries to identify the suitable models, reduced models for the ANOVA one-way, two-way, and factorial experiment design by both frequentist and Bayesian approach. The present study also performed the same analysis on simulated data sets. That has become the usual order of the day, that people try to question that how strong is your, how robust is your procedure. So we try to simulate the data and then try to see how this particular procedure of using the Bayes factor to assess the strength of the main or interaction effects in the models has been carried out. Now here, the first one, probably to start with a very simple model. An algorithm is presented, then you have a Bayes approach for the ANOVA model, then you have a Bayes factor for the ANOVA full and reduced model, and Bayes factor values for the ANOVA full and reduced model by simulation. So whatever has been talked about, that has been done for a one-way, two-way model. Now, I've just presented the algorithm here. What we do is apply one-way model for a suitable research problem. If the null hypothesis is rejected, go to the next step. Otherwise, we stop the procedure. Now, what we do here is apply any one of the post hoc tests, because you know there are many post hoc tests like what I mentioned. One can apply whatever you feel is going to be right for you. So the post hoc test results will produce the following. A single non-significant pair of treatments is identified for the model. Then the model is split into 2 reduced models. If you have 2 non-significant pair of treatments that are identified, then the model is split into 4 reduced models, right? If you have 2 non-significant pair of treatments that are non-distinct, then the model is split into 2 different reduced models, and so on and so forth. So you just keep on reducing, splitting up your given model based on how many of them are going to be insignificant or not significant. That's essentially what the step 2 is all about. Now the step 3, you select the suitable prior to find the Bayes factor, to validate the full and reduced model, and also assess the strength of the treatments. Now what we do, as I said, you try to simulate the data, and then you decide about which factor to be included or which model to be considered for your further study. So we could check the intensity of the treatments while eliminating from the model by the Bayes factor values. Finally, Bayes factor results will provide ample evidence for the level of support to data under both the full models as well as under the reduced models. So we start with a simple illustration here. Probably you can see this in Montgomery, that you have a synthetic fiber data of tensile strength at levels 15, 20, 25, and 30. So the calculation has been done. You got an F ratio, and probably you can see what it is going to be. And so Y is being given that based on the null hypothesis, and the null hypothesis is rejected based on the analysis. So we wish to test all pairwise mean comparison by using multiple comparison, which is going to be the two-case test. So probably, as I told you, one can think about all possible or whichever test that you want to think about. So you can think about all possible comparisons, what one can think about. Out of 10 possible pairs of treatment means, 6 pairs were significantly different, and the remaining 4 pairs were not significantly different. So once you decide or once you identify which of them are going to be different, then you can form reduced models based on that. So you can get a reduced model based on what to be included in the reduced model. You also have a full model which is available to you. Now, using both of them, you can try to get the strength of that particular factor by using what is known as a Bayes factor. Of course, we have also done the shrinkage factor, but for the time being, I will not go into this particular aspect. We have done, you can look only into the Bayes factor and see the Bayes factor under the different priors have been worked out for the model, and you can see for the full model it is going to be there, and for different types of priors what is going to be the Bayes factor. Now you can see either one of the treatments on the non-significant pair in the ANOVA models, then it leads to form 2 possible reduced ANOVA models. Obviously these 2 models will not be the same in terms of significance per Bayes factor. Now if one pair of treatment is significant, then there are 8 possible reduced ANOVA models with 4 treatments. So you can see all possible models that are being given. So one can choose the full model and the reduced model, appropriate model. So you have a model with BCD, model with ACD. So there are 4 factors in this particular model. And so you have a full model, you have a model with 4 factors. So you can assess the strength of factor A, strength of factor B, and so on and so forth. Now, the same thing has been done here. So you can see the Bayes factor for the 4 components or 4 factors that are being considered for the model. So you have a full model, you have a model with 4 factors which are given here. Now you can see the Bayes factor for 3 treatments. So now from the 4 treatments, we have gone, as I told you, it's in a hierarchical form. You can think about going further to think about all possible 3 factors. And based on the 3 factors, you can decide about which one is going to be more powerful. Let us say you have decided about BCDE. And now from BCDE, you want to go in for a 3 factor if needed. Then you have to decide about which of them based on the combinations that you are going to have at 3 factors. And now you decide about which one should be considered and which is going to be more powerful or which is going to be a more stronger or intensity is going to be higher. Now we can see that the Bayes factor values for all possible models has been considered here. So you can see the ANOVA full model ABCD and reduced models ACDE except B have similar Bayes factor. In the ANOVA reduced models such as ABDE, BCDE, and CDE, the Bayes factor is going to be lie between 2.5 and 3. Thus, no changes are noticed in the Bayes factor values when the treatment B is included or excluded in the model. Now you go over any of them and you can see it is going to lie between 2 and 2.5 and see you are going to draw which one is going to be of more stronger intensity. Now you can see BCD and BCE models, Bayes factor value is going to lie between 0.5 and 1. So if in the only model ABE, Bayes factor value is going to be less than 0.5. So going in a stepwise fashion, you are able to identify the strength of the factors involved in the model when the basic ANOVA model has been rejected or when the basic multiple comparison has been rejected. So you want to go in a sequential way to identify which is going to be the most appropriate reduced model. So we have done the appropriate distributional part of it. And this is going to be the variances also, because one would like to ask how the behavior is going to be when you try to have the variances. You keep the variances varied, and you can see what is going to be under the different types of priors which are being considered. So this is going to be histogram for Bayes factor values to ANOVA of the reduced model to the simulation data set. So you can see the summary, and we have considered with significant treatments ABD. I think this should be ABE if I'm right. So that is the part one, where for a one-day model, when we started off with 5 factors, we tried to reduce it when the null hypothesis was rejected. We tried to identify ABE as a plausible reduced model based on the strength of the factors which are involved in the reduced model. The model which is going to help us to go further. And that's the reason why we call the post hoc analysis. So I'm just going to skip this particular part also because of the lack of time. We have done the same thing for a two-way model also. The model you can see here. So we have considered the same, one more example from the same Montgomery book. And probably you can see the bunch of models that are being considered, right? The algorithm is just going to be on the same lines. We have seen what is going to be the strength of each of the factors that are being considered under each of the priors that are being considered. Now, you can see that it's sort of a visual treat of how the Bayes factor and the different data sets are also being considered for the two-way model. Now coming to probably the last lap of my story, I'm not going to go further. So we have done the same sort of a story as far as the Bayes factor for a factorial experiment. But here one has to be careful that you have a two-cubed full model. You have a factorial which is going to be a reduced model, because as you know, by confounding and all those things, you are going to have a model which is going to be a reduced model. You are also going to have a fractional factorial which is also going to be a part of the factorial designs. Now, when you have these 3 different choices, a full model, a fractional factorial model, and a reduced factorial model, now you have to choose an appropriate one based on the strength of the factors. So that's essentially what has been done as far as the post hoc analysis is concerned. So here you can see the algorithm is going to be a 2-cubed factorial design. Identify the significant and non-significant interactions or main effects. Construct a fractional factorial based on confounding or alias factors and then check its significance. Generate a reduced factorial design according to the significant factors from the full model. Compute the Bayes factors for all of the cases, like your full model, a fractional model, and a reduced model, to compare the strength of factors while incorporating them into these designs. And then conclude the reliable and instructive conclusions, and also generalize the results based on the different simulation sets that are used to find the Bayes factor. So in this study, the effect of factors in full factorial, fractional factorial, and a reduced factorial, which consists of significant factors alone, are considered. And as I told you, that has been done. And we use the Bayes factor to examine the strength of the factors. So you can see the model for a 2-cubed factorial. You can see the model for a fractional factorial. You can also see that you can get a model which is going to be for a reduced factorial. So one can think about different types of models: a full model, a reduced model, a fractional factorial model. So here is an example which has been considered, and you can see which factors are going to be significant, which of them are not going to be significant. So you can look at that particular 2-cubed fractional reduced factorial designs. And we have looked at the priors. You can see the full prior. You can see the reduced. You can also see the fractional priors, the fractional factorial. And you can see what is going to be the Bayes factor for under each of these priors that are being considered. And you can see beautiful color set of distributions which are here for the data sets which are being considered. Full prior for the fractional and reduced factorial set based on the simulated data sets. Also, we have considered, as I told you, it's important to see how the behavior is going to be as far as the error is concerned. So we try to look into the error variances also to examine how the system or how the procedure works. The same set of things for the data sets with different variances. Okay. Now, let me just sum up the whole story. So all we have is a complete model, right? And now when your null hypothesis is rejected, obviously you have to go for a reduced models. Now the reduced model, the need for reduced models is very important. And which model to be considered? Based on the strength of the factors that are incorporated in the model or that are involved in the model. So in order to examine the factors which needs to be a part of the model, we adopt the Bayes factor, and based on the table that has been created, that has been given, sorry, that has not been created, that has been given, we try to identify the factors, and then we try to come up with a reduced model which is going to help us in further studies. So you can see as a part of conclusion, the aim of the study is to employ the Bayesian framework of analysis for experimental design, particularly the reduced analysis of Bayes model for one-way, two-way, and factorial designs to identify and study the strength bar intensity of the treatment bar factors, which usually goes ignored in the frequentist framework. We have considered different set of priors. So here, because usually when you go in for a Bayesian setup, people ask you, why did you consider only this prior? Why not that prior? Why not this prior? So the people, the question that needs to be answered. So we have considered a bunch of priors. Do you mean to say is this exhaustive? No, one can think about other different types of priors also, but this is the priors that we have considered as far as the present study is concerned. So I think I will stop here, and as you can see at the end, so I don't always test, but when I do, I prefer Bayes factor analysis. So this was the one which was proposed by Jeffrey Rauder, and so all we have done is when you have finished with the post hoc analysis, you can go further. I can call it as further to post hoc analysis in order to identify the strength of the factors that are going to be incorporated in a reduced model is what is being done as far as the present study is concerned. And invariably, we try to look at all possible models that one can look at it, like a simple comparative models of one-way, two-way, three-way, and so on. We also look at a factorial experiments of 2 cubed 2 power 4 and also a 3 cubed factorial. And then we try to look at how good or how bad the factors, the strength of the factors. And based on that, you are going to decide whether that particular one should be incorporated or not to be incorporated. So thank you for your patience.
Thank you much, Professor, for your wonderful presentation. So it's the forum is open for any discussion with the Professor Srinivasan sir. If nothing is there, so let me thank our Professor Srinivasan sir on behalf of the organizing committee and my personal behalf for joining with us on this Sunday and given a wonderful talk to the listeners. Thank you very much, sir. Thank you very much.
Thank you very much. Thank you.
So that's all for in our session. So I hand over the session to Professor Tisha for further proceedings.
Thank you, Professor. Sorry for the network issue here also, because there is a raining. Yes, probably that may be the reason. Very much thankful to all the speakers of the session for their wonderful talks, and also we wish to extend our gratitude to Professor Kavirasu for nicely managed the session with great speakers. Thank you so much. Let us give a all the speakers of this.
Thank you, sir.
Thank you. Now we are expecting another important session and great speaker, Somesh Kumar.
I am here.
His team. Hi, Professor. Hi. Let us wait some 5 minutes because otherwise some people, we have to. Now 3:50, the time is very correct. The right time. In fact, the session scheduled at 4:05. Professor Sakti will also join.
Yes, sir. So, good afternoon, sir. Good afternoon, Professor Somesh Kumar, sir.
Good afternoon.
Good afternoon.
Yes.
proceedings of the session.
Sure, sir. Everyone, we are moving on to the 20th technical session of ICSTC 2023 that shall be chaired by Professor K.M. Shaktivel. Now, Professor K.M. Shaktivel is a professor to the Department of Statistics, Bharatiyar University, Coimbatore. His areas of interest include statistication, alpha power transform Pareto distribution, and so on. It's with great pleasure and honor that I invite you, sir, to chair the session. On behalf of the organizing committee, I once again extend a warm welcome to you and kindly request you to take over the session. Over to you, sir.
How you feel now?
Hear you. Everyone. Of factor A and B levels of the factor B. So you can look at it as in the way that mu is the general effect and alpha is the effect due to the ith level of factor A, and beta j is the effect due to the jth level of the factor. Problems, and that is why this problem has not been studied in literature before. So we are taking the full-fledged model that is unknown and heterogeneous, and also these Nij's are different. So that means we need not have balance within the cells here. We have the constants, that is sigma alpha I must be 0 and sigma beta j must be 0. These are the estimability conditions. So the test for homogeneity of row and column effects, these are widely used in experimental studies in engineering, biology, agriculture, social sciences, clinical trials, etc. The standard problem in classical ANOVA is to test the null hypothesis of homogeneity of main effects against the alternative hypothesis of at least two of them are unequal. Now, in many applications, we have some prior information about the main effects. For example, the effects of factors A and B, they may follow monotone increasing or decreasing order or tree orders. This extra information leads to more powerful tests. So I'm considering one example. We have a two-way model with factor A as different cities in India and factor B as the years and response variable as the RSPM, that is the fraction of total suspended particulate matter, that is TSPM, which is inhaled by humans through the respiratory system. So if we consider RSPM values, then if the city population increases, it is natural to expect that RSPM values will increase because the population density will lead to the total TSPM to increase, and as a consequence, RSPM will also increase. Similarly, on a year-to-year basis, if we look at the data for last 20 years or last 10 years, you will see that there is an increase in RSPM values. Similarly, if we consider epidemiology of virus infection, you consider the transmission rate of a respiratory syncytial virus as response variable, then the relative humidity as one factor and ventilation as another factor. Then if you look at, there is a reference by Pika and Boyer, they have studied that the transmission rate will decrease with an increase in RH as well as ventilation. Let me give some literature review on the problem of testing of homogeneity against order alternatives in various works from the beginning. So the first one is Bartholomew. He studied testing against order alternatives in a one-way ANOVA model when errors follow normal distributions. And he derived the likelihood ratio test, assuming error variances are either known and unequal or unknown and unequal. So the case when they are completely unknown and unequal, that was not considered by them, and it has been recently studied by us. So I'll be mentioning about that. When the group of is less than 5, 1% and 5% percentages point of the proposed test statistics were tabulated for selected parametric configurations. For homogeneous variances, he extended the tables of percentage points and also addressed the hypothesis of equality of means when the direction of the ordering of means is unknown. That means it could be in any of the orders. Later on, some extension to such works have been done. Shorak in 1967, he considered the testing of homogeneity of main effects in a two-way ANOVA model. So we are considering ordered alternatives, but the interaction effects are not present. However, he took the homogeneous error variances as well as the balanced samples. And when the error variances are homogeneous but unknown, then the Williams has proposed a test statistic for ordered alternatives. It is based on the difference of MLEs of the largest and the smallest mean responses. Then for testing of homogeneity of means in K normal population with a common known variance against ordered alternatives, Mudholkar and McDermott have considered K-1 contrast-based nesting test problems, which is equivalent to the original testing problem. Then Hayter in 1990, he proposed the test for in a balanced one-way fixed effects model when the error variances are homogeneous but unknown. Now, the test which is given by Hayter, if the computation of the size and power value is considered, it becomes very complicated when the larger number of treatments are there. So Hayter and Liu proposed a new method to evaluate the critical points. And this method works well for the calculation of size and power values when the number of treatments is large. Then Chen in 2000, he considered unknown and heterogeneous error variances, and he proposed one-sided range test using one-stage and two-stage procedures to test the null hypothesis of homogeneity of means in a one-way ANOVA model against ordered alternative. Recently, Hassler and Hawthorne, they have considered a Williams-type approach for testing of multiple contrasts in randomized dose-response studies with correlated multiple primary endpoints. And they actually proposed some approximation of the test statistic using a multivariate t-distribution, which is actually helpful to compute the critical points using a R program actually. And recently we have done in 2022, we have considered several test procedures, including likelihood ratio test procedures for testing homogeneity of treatment effects in a one-way ANOVA model with unknown and unequal error variances. And in another one, we have considered two-way ANOVA, additive ANOVA model when the errors follow normal distribution. And this has been further extended to the crossed ANOVA model also. That has also recently been published. Then there are certain works which are in the parametric and the non-parametric works, like Mansouri, Calagari, and Aketas, Davido et al. In real life situation, the homogeneity assumption for the cell variances in the classical F test of ANOVA problem, it is often not satisfied. And then in that case, these tests lead to the misleading conclusions in the presence of heteroscedastic variances. And there are a lot of simulation studies by Zhang, Zhu et al. In 2013, Zhu et al. In 2015. They indicate that the standard tests are not robust for heterogeneous variances. Also, it has been widely analyzed in Pauli et al. In 2015, Batke et al. In 2018, Sattler and Pauli and Noguchi et al. Also, it has been observed that the classical F test is not robust when the sample sizes are not equal. And this was shown by Ananda and Veerahandi. And for unequal sample sizes, they considered something called a generalized F test, which we call GF test. However, their test was seen to be quite conservative. And for multiple contrast, Hassler and Hawthorne, they have proposed a simultaneous test and used some heuristic techniques to find the approximated distribution. Then Zhu et al., they have proposed a parametric bootstrap approach, and they compared the performance of their procedure with that of the generalized F test and showed its superiority. Then Zhu et al., they have also proposed a parametric boot test for testing homogeneity in a two-way heteroscedastic ANOVA model. And they observed that it controls the pre-assigned size level even for small sample sizes and large number of factorial combinations. So if we consider the problem of testing of simultaneous ordering on both row and column factors, it is useful in many situations. We consider the problem of homogeneity of both row and column effects against their ordered alternatives when errors are independent and normally distributed. So if we represent the hypothesis, it becomes simultaneous homogeneity of levels of factor A and factor B. That means all the alphas are equal and as well as all the betas are equal. And then it is against the simultaneous ordering. That means alpha i's are in increasing order and beta i's are in an increasing order. So if you look at, say, for example, if I keep this one fixed and this one fixed, then this is problem which has been studied in the one-way ANOVA model. And if I keep them to be fixed but unknown, then this problem has been studied for the two-way ANOVA model by our group in 2023 Journal of Multivariate Analysis, as well as in the test paper. But this problem is completely new, and we have not seen anywhere where the simultaneous ordering has been considered. Actually, although it may look like a little bit artificially set up problem, but then when we were analyzing certain data sets, we find that such situations actually occur in various experimental studies. So one of the studies which we looked at, it was like considering alcohol specific deaths in UK, and the data is actually arranged by gender as well as age. So that is the way we looked at the data. And when we plotted it, we considered the box plots here. You can very clearly see. So for example, if you look at the female individual deaths from the age group 40 to 44, 45 to 49, 50 to 54. So in this box plot, you can easily see that there is a increasing trend. Similarly, if I consider the similar data for the male population between the three age groups, 40 to 44, 45 to 49, and 50 to 54, you can easily see that it is an increasing order. At the same time, if we fix the age group and we look at the male and female as the factor, that is the gender, then you look at that the mortality of the male is much higher compared to the mortality of the females here. Here you can see the upper points here. This is, you can see upper quartile, that is 200, and this is something like 175. Whereas here you can see it is nearly 300, I mean, maybe a little less than that, 290. And the upper one is around 360 here. And it is happening across all the age groups. So you look at the next age group, then the female plot is here, whereas this is the male plot. And if you look at this age group 50 to 54, then the box plot of the females is here, whereas the females it is, for the males it is here. And you look at the scaling here, here the scaling goes up to 350, here it is going up to 600. So you can see that there is a clear-cut example of this situation, that is alpha i's are increasing and beta i's are increasing. So because we had the interesting examples, we decided to completely analyze this one and propose the test. So we model it as a two-way ANOVA. So the response variable is the number of deaths in a year due to alcoholic liver disease as a response variable, and the age as factor A having 3 levels, and the gender as factor B having 2 levels. So let us look at the possible way of solving this problem. What we considered here, we split the problem into 2 parts. So firstly, consider the hypothesis of equality of alpha i's against hypothesis of monotone trend for alpha i's. And similarly, H0B and H1B we consider for the hypothesis of homogeneity of B factor levels and the monotone ordering for the same. So if we consider the original hypothesis H0 and H1, then you can see that we can write H0 as H0A intersection H0B and H1 as H1A intersection H1B. Because of this representation, we can use certain representations of the likelihood ratio test procedures which are available for H0A and H1A as well as H0B and H1B. So let me now explain this one. So you consider the hypothesis testing problem H0A against H1A. So here we have introduced certain notations here. Alpha as alpha 1, alpha 2, alpha A. And here alpha I prime I defined by mu plus alpha I. So this is alpha prime vector. Then the beta vector is there. And similarly, beta prime vector is there. So if we consider the first hypothesis H0A and H1A, then the null and the full parameter spaces, if we want to derive the likelihood ratio test, we need to write down the maximization of the likelihood function over the null space as well as over the full parameter space, and then we take the ratios. So this is the representation that is given here. So we in our Journal of Multivariate Analysis paper in 2023 in Mandal et al., we have actually obtained the maximum likelihood estimators of the parameters under both null and the alternative hypothesis, which is specified here. So if we consider that, then we are able to write down the likelihood ratio test. Now, if we apply symmetry, because we can interchange the factor A and the factor B, then similarly, we can have a solution for H0B against H1B. And we can derive the form for the likelihood ratio. In fact, there is a procedure that we developed for solving the likelihood equations, which is actually you can consider as a generalized or a nonlinear Gauss-Seidel method. Actually, Gauss-Seidel method is used for solving the system of linear equations, which is actually an iterative procedure. That means you take certain initial solution and then you substitute in the equations, and at each stage you revise your previous value. So here we are able to do that and propose something. But of course, this is a highly non-linear system, but I will not be reading each of these values here. But we have shown that this procedure actually converges to the true solution values. So this is the algorithm for that. Maybe I can skip these steps here. Basically, we have proposed these procedures here for getting the solutions in both the cases, and we get some sort of desired level of accuracy. This leads us to the likelihood ratio test statistics for testing H0A against H1A. Let me call this lambda 1, which is defined as product of sigma ij head square omega A by sigma ij head square omega naught A, where this one is the maximum likelihood estimators under the first one null hypothesis, that is H0A space, and this is under the full space. And similarly, lambda 2 we define when we consider the testing of H0B against H1B. So now, because my hypothesis is represented as the combination of H1A, H0A, H0B, H1A, and H1B, we actually make use of both of these statistics, lambda 1 and lambda 2, in certain sense. So Q1 we define as maximum of lambda 1, lambda 2. So the test will reject against H1 if Q1 is less than C. Now you see here, C is of course the critical point that needs to be determined. So if I have Q1 less than C, it means basically lambda 1 is less than C and lambda 2 is less than C. That means both H0A as well as H0B will be rejected. That means H1, we are taking decision in favor of H1A and H1B. Now, the main question is how to evaluate this C, because we want to actually a procedure which can be readily implemented on the real data sets. So we use a parametric bootstrap approach to determine this. And so what we do, we have the original samples Xij1, Xij2, and so on, Xij and Ij for I is equal to 1 to A, J is equal to 1 to B, etc. And then we generate, so of course we calculate Sij squares, which are the sample variances. Then the next set of observations that is called bootstrap samples, they are generated from normal 0 Sij square. And then using the parametric bootstrap samples, the MLEs of sigma ij squares, etc., they can be calculated. And we can calculate the bootstrap versions of these test statistics as lambda 1 star and lambda 2 star. So Q1 star is the bootstrap version of the test statistic Q1 here. So we generate these values, and then we arrange these values of this test statistics actually in a ascending order, and then we calculate the alpha hat quantile. So you get the bootstrap critical point here. So this is the first test procedure, which is actually obtained as sort of compromise solution by using the likelihood ratio test, which have been developed earlier by us for a two-way classification procedure where one level of effects has been considered. So here we have merged the two procedures. So the question is whether these procedure will perform well. So that we are going to study. Then secondly, we considered certain union intersection type of tests. So we considered the pair-wise consecutive differences of the means, where we have considered the means either row-wise or in the column-wise fashion. So T1i's are defined as xi plus 1 dot bar minus xi dot bar. These are the standard things which we do in the two-way ANOVA model. And in the denominator, we are having the corresponding sample variances, that is Si plus 1 j square by Ni plus 1 j. So you can easily understand these are Welch-Satterwhite type of statistics that are used for comparing of the means of two normal populations when the variances are unknown and unequal. So we have adopted that kind of statistics for considering the consecutive differences in the, because here we need only consecutive, it is ordered here. And we consider certain stabilizing factor here, like 1 by b square, and here 1 by a square here, because this term is based on the means of a level of terms here. Here it is based on b level of the term. So that term will also come here. So based on this, we define, so T1 we consider as the vector of this T11, T12, T1a minus 1. And similarly, we consider T2 vector as T21, T22, that means vector of these values. And then you look at maximum of T1, maximum of T2, and then we look at the minimum of that. This test statistic we define as Q2 statistic, and we can consider it as one of the test statistics. Here we will reject H0 against H1 at level alpha if Q2 is greater than certain D1, which is calculated as a critical point for alpha level test. The analytic form of this Q2 is again complicated if we want to find out the distribution. So again, we have used a bootstrap approach for implementing of this. So this T1i star, T2j star, etc. And based on that, we consider T1 star, T2 star, and Q2 star as the bootstrap version. And we can actually implement it. And one is used as Q3 minimum of the minimum T1 and minimum T2. We will look at the relative advantages and disadvantages of considering this Q2 and Q3. Because if you look at Q2, in the Q2 we have taken minimum of the two maximums, whereas here we have taken minimum of the two minimums. So we will see this one. When the levels of both the factors follow strict ordering, that is alpha i's are in the strict order as well as beta i's are in the strict order, then this test is expected to have a good power performance in detecting small differences among the effects of the factors. And actually it is shown by the simulation studies for power function that we have done. So once again, of course, the rejection region is in the Q3 greater than D2, where D2 is the critical point at alpha level. When there is at least one equality among the factor levels, then Q2 will perform better. So we will explain this again. Again, for implementation of this, we have used the bootstrap algorithms here. Now, another important part is we are repeatedly mentioning that we are using bootstrap procedures. So the first thing is whether the bootstrap procedure is accurate in this case. Bootstrap procedures, as everybody understands, that the proofs of accuracy are quite complicated because you have to prove the equivalence of the conditional distribution of the bootstrap statistic given the original sample as well as the null distribution of the original statistics. We have to prove that the two are asymptotically the same. Fortunately, we are able to work it out. So we have used the methodology of using Kullback-Leibler divergence measure, and we have shown that the divergence distance between the probability distributions of the Q1 star given X and Q given H naught, it goes to 0 in probability as the sample sizes increase to infinity. The result is established in the theorem, which is written here. So if I denote the conditional CDF of Q1 star given X as F, Q1 star given X, and FQ1 given H naught as the null distribution of Q1, then we have been able to establish the supremum of mod of F of Q1 star X given X minus F of Q1 given H naught X. It converges to 0 in probability as minimum of Nij tends to infinity. Similar results have been proved about the parametric bootstrap accuracy of the statistics Q1 and Q2 also, Q2 and Q3 also. But for that, firstly, we have proved for T and T star, because those statistics are framed from the T1 and T2. So we combine it and put it as a T star. Fortunately, that also we are able to establish using the Kullback-Leibler distance function. This is the derivation part, but I think I will be skipping here. Because we have to derive the asymptotic distribution, and then we have to use the multivariate Slutsky's theorem, etc. But we are able to prove that thing. Now let me describe the setup of the performance of the power and the size of all the tests here. As you can see here, that even if I have a small number of labels of factor A and B, for example, if I have 3 and 3, then it becomes 9. So you can have the 9 choices of the samples, like N11, N12, up to N33, and so on. Then you have the values of alpha E's, beta J's, which needed to be selected for the simulation purposes. So it makes this simulation exercise to be very extensive. Fortunately, we are able to do the entire exercise, and we are able to calculate the size and power values by using 5,000 iterations of the samples, and then the bootstrap samples are taken for each of them. So we have considered several configurations. For example, we have taken small sample sizes, equal variances, moderate sample sizes, large and unequal sample sizes. So for example, this is 3-2 design. Similarly, for the variances you have considered, we have equal variances, unequal variances. So we have 3x3 design, 3x4 design. And as you can see that the number of various type possibilities for the sample sizes and the values of the variances, they can be too many. And but we have been able to do all of this in detail. And so a wide variety of parametric settings for sample sizes and variances has been considered. So we have taken, for example, balanced sample sizes, homogeneous error variances, unbalanced sample sizes, homogeneous error variances, balanced sample sizes, heterogeneous error variances, unbalanced sample sizes, and heterogeneous error variances, etc. We have chosen nominal size as 0.05 for our consideration. But if you want to do it 0.01 or 0.1, etc., the same thing can be done. Actually, we have prepared a software package where you can substitute this value and get the results for your outcome. The distributions of the given test statistics, they are independent of the location parameter mu. So in the simulation study, mu can be taken to be 0. This first table, if you see, this is about the empirical sizes of the test statistics Q1 and Q2. And we have considered various possibilities here. These values of NI's and sigma I square, etc., I mentioned in the this particular table. We have used this one here. These choices are written here so that the table is a little bit crisp. And if you just go through this one, for a nominal size of 0.05, if you look at the empirical sizes 0.05, 0.051, 0.054, you can easily see that the values are extremely close to 0.05. In fact, all the values are accurate up to 2 decimal places. Even for Q2, if you look at the other one, that is max of min T1 and min T2, this is also performing very well. So these tests are behaving almost as exact test as you can see here. And this is true for all choices of the sample sizes as well as the variances. And then we are considering the power curve. So we have taken again, in the power curves, we need to show that the alphas are in the increasing order and in the betas are in the increasing order, and the differences keep on increasing as the differences increase. So we consider 4 different scenarios. Again, small sample sizes and the variances with moderate heterogeneity, small samples with the high heterogeneous, and large samples with moderate heterogeneity, and large sample with the high heterogeneous variances. And you can actually see we have plotted the power curves for Q1, Q2, and Q3. As expected, tests which are based on the likelihood ratio test, actually we cannot call it a likelihood ratio test because that would have required the simultaneous optimization. We have actually solved 2 problems and combined that and LRT based on that. But in this test, you can see it is performing much better. Okay. So in all of these cases, you can see the performance of, but of course, other tests are not performing bad. They are also performing quite well in all the cases that you can see, but they are slightly inferior to Q1. So Q2, Q3 we have plotted, and power value.
I think we have a section post 50. If it's okay for you, you can continue, sir.
Okay, so just I will take another 2 minutes. The conclusion is that actually these tests perform very well. Q1 is having the best performance, and Q2 and Q3 are basically heuristic tests, but they also perform quite well. The advantage of using Q1 is that it is giving you the best result, and the advantage of using Q2 and Q3 is that these are computationally easier because they are based on simultaneous differences only. So these are all various things. So I will just skip it again. And next one is that we have also considered the robustness. That means if we deviate from the normality, then we have Laplace distribution, student state distribution, uniform distribution, contaminated normal distribution, etc. And we have considered skew symmetric distributions also as alternatives. That is variable, exponential, chi-square, log normal, mixture of normals, etc. And our conclusion is that the likelihood ratio test is robust for all the symmetric distribution. But if you have a skewed distribution, then Q2 and Q3 they are still all right. So this is the conclusion here. The heuristic tests perform better from the robustness point of view for skewed distribution, but for symmetric distributions, the Q1 and Q2 and all the tests are performing very well. Then we implemented on a real data set. So I think skip this part here. And we have prepared an R package, additive ANOVA, and it is actually shared on the open platform GitHub. So any user, if he wants to use, he can actually make it. Thank you.
Thank you so much, Professor. It's a really very wonderful talk. It's the first time I'm seeing the solidity hypothesis should be less than or equal. So now it's a discussion open with Professor Somesh Kumar. If anybody is willing to ask any question, please. Now it's time for you. If there is no question, then we thank Professor Somesh Kumar. He gave valuable resource of additive ANOVA package available now. So all of you can make use of it. So on behalf of the organizing committee, I thank Professor Somesh Kumar for having given wonderful talk in this plenary session. So I thank you, Professor. Thank you. Now it's over to organizing desk, Professor Satish Kumar sir. I think Professor Sarishma sir is busy with other para sessions.
So I think maybe, yeah, Professor.
Professor, now the session over.
There is not ready. So now let me thank Professor Charan sir for speaking.
Thank you, Professor Somesh Kumar, for your excellent talk. In between, I have some network issues and also not more than other parallel sessions also how to just manage. And very informative talk and useful for the researchers, young researchers. And you have a team, in fact, I know. Let us congratulate Professor for your excellent talk. And also, we wish to extend our gratitude to Professor Shaktivel for nicely managing this session. Timely concluded this session. Okay.
Thank you.
In fact, now we have to move to the next session, which right time 4:50. So this session is a special session organized by Professor Somesh Kumar, and Professor he will chair the session and manage everything. Okay, welcome, Professor. I'm not giving introduction because already they have given.
Yeah,
okay.
yeah. So let me start this session, which we are calling innovations in statistical inference. So we called it innovations simply because the work which is being presented in this session, also all the problems are actually new problems. So I thought we can have just some appropriate title. And so we have our three speakers in this session. Dr. Manas Ranjan Tripathi, he's from NIT Rourkela, and Raju Day and Subha Haldar, they are from IIT Kharagpur. So firstly, let me welcome Dr. Manas Ranjan Tripathi. He is an associate professor in the NIT Rourkela. He has published around 50 research papers on various topics in the estimation of parameters, confidence intervals, and the problem of classification. And in particular, his specialization is estimation of parameters under the constraint of equality of parameters. That means in the model, something may be common. And he has published large number of papers on this. He has also produced several scholars, I think 6 or 7 scholars. And he has been regularly teaching courses on probability, statistical inference, and other topics at NIT Rourkela. So without losing much time, I now invite Dr. Tripathi for speaking on estimating powers of the variances under order restriction for two normal populations with a common mean. Dr. Tripathi.
Yes, sir. Thank you very much, sir, for your kind words. I also take this opportunity to thank the organizer of this conference, Professor Satish Kumar, and his team. So let me just go through. So just let me share this actually. So is it visible, my slide?
Yes, it is visible. You can just put it full screen.
Yeah. Yes, sir. Yes, sir. Just 1 minute. Is it okay, sir?
Yeah.
Yes. Yeah. You can just put that hide button.
Yes. Yes. Thank you, sir. Thank you, sir.
Yeah. Okay.
Sir. As it is written, the topic of the presentation is estimating powers of the variances under order restriction for two normal populations with a common mean. And in fact, this is a joint work with my PhD student, Mr. Prabhas Jena, who has just submitted the thesis. And so before I go to the details of this, let me just tell you in the beginning, because everybody knows about the normal population. So the idea is very simple here. We have two normal populations with common mean and different variances. So the problem here is to consider the estimation of the powers of the variances. Okay, so looking at this model, the literature of this study moves around basically three directions. If you look at, one is the common mean, the second one is the ordered parameters, and the third one is closely related to the function of parameters. So as I will go through the literature, the first one is, as I told, the estimation of the common mean for two or more normal populations. So because I'm considering here two, so I'll concentrate on two normal populations. The problem of estimation of the common mean actually has a long history, and it is quite rich in the history of statistical inference. And the problem actually got motivated from the work of Yates, who was actually dealing with the problem of balanced incomplete block design problem, where he was actually trying to get the information for using this intra-block and inter-block, and combining these two, the information from these two, to get better information for either of these. So that was the motivation. That is the practical application he was dealing with. Then after that, Grebel in the year 1959, considering two normal populations with common mean, they gave actually a nice estimator, which is actually the convex combination of the individual sample means with weights as the sample variances. And after then, the common mean problem actually got attracted by many researchers, basically in two directions. One is to propose various alternative estimators for the common mean. The other one is to prove or to disprove that the Grebel-Deal estimator, since that was the what I can say, the first result, that's robust kind of estimator that Grebel-Deal proposed. So some of the researchers actually tried to prove or disprove the inadmissibility. That means, can we get another estimator which will dominate the estimator? So a lot of research work has been done. So here I am just citing few literature. You can go through that. Then the other one, more recently, some research has been done in this direction. So the other one I told, that is the estimation of the ordered parameters, because looking at my model, there is a chance that I will consider the ordering of the parameters. So if you go through the literature, basically all the results are deal with the estimation of ordered parameters using the isotonic regression. That is using the prior information, then they can actually improve the estimator. So the results up to 88 can be obtained by this literature, that's by Barlow et al. And Robertson et al. Most of the results are actually used, they have used the maximum likelihood estimation technique. Then some recent results on this ordering of the parameters, assumption of the ordering of the parameters are obtained by Elfesi and Paul, Misra and van der Meulen, and Jena et al. So the other one I told, that's the function of parameters. The function of parameters, basically in the case of say normal population, we have a mu and sigma. So instead of estimating individually mu and sigma, one may consider also the function of mu and sigma. For example, the quantile, or you can consider the hazard rate. You can also consider the powers. Here we are considering, instead of the variance or the standard deviation or the precision parameter, we are actually considering the power of the variances. So the literatures are actually there. Few literatures are actually there, literature in that direction. We can go through that. So the main idea of this work, that we have considered the model that has been considered by this Misra and van der Meulen, and we can say Jena et al., or you can say Elfesi and Paul. So these three results, which are actually already published, we consider the same model. That means common mean, the variances are ordered. So under that setup, we try to estimate the powers, say sigma 1 power c, or you can say sigma 1 square power c. Okay, so without wasting time, I'll go to the model directly. So let us consider the two populations, X and Y, having the sample sizes M and N. as I have written, normal mu sigma 1 square, normal mu sigma 2 square. Now I will denote for my convenience, we can denote beta I is a sigma I square. That is beta I is the variance. So we will estimate the parameter beta I power plus minus c. So I can say plus minus c because I can take c greater than 0. Otherwise, you can consider beta I power c and then beta I power minus c, where like that also means beta I power c, where c is a negative, positive, both we can do. So for our convenience, we have considered like this. And the condition is that beta 1 is less than equal to beta 2. So for estimating this parameter, this function of parameter, we consider the loss function as quadratic loss, or you can say the scale invariant loss function. Okay, so I think this notation is okay to all of you. Now for this model set of, for this, the minimal sufficient statistics exist, and we write it here: x bar, y bar, sx square, sy square, where these random variables are defined like this. Now when we start any statistical inference, particularly the point estimation problem, we look for some estimators, some basic estimators. So in this model, let us try to get the maximum likelihood estimator for this problem. So the maximum likelihood estimator, if you like to try, so you have to use the basic procedure to differentiate, to get the log likelihood function, then differentiate and equal to 0 the parameters. So then you get actually a system of equations here. I'm getting the system of equations. So this system of equation doesn't have a closed form solution, so which has been discussed in Pal et al. So we can numerically solve this and get the values of the estimators with some proper guess of the initial values. So we denote these MLs, which we have obtained numerically, say beta 1 ml hat plus minus c and beta 2 ml hat plus minus c. Now the next step is to get some other estimators. So as the sufficient statistics or the minimal sufficient statistics is not complete, we are not going to get the UMB by using the usual procedure. It's not possible. So what we do here, basically, the idea is to get an unbiased estimator first for the beta 1 power plus minus c. So if you look at the unbiased estimator of this, so let us consider the positive powers first. Then similarly, you can get for the negative powers. So for the positive powers, we have obtained the unbiased estimator here, 1 by a sx power 2c, where this is the expression, where a is given by this gamma function. Similarly, for the negative powers of this beta, we are getting the unbiased estimator here. Now, once we get the unbiased estimator, then the idea the trick comes. If you look at the estimation of the common mean problem, the Grable-Dill estimator, there are many Grable-Dill estimator, then other estimators, some these alternatives, say estimators proposed by Brown Cohen, if you have gone through the literature of common mean, or you can say the Khatrisa, Murray Krishnamurthy. So a lot of, in fact, 7-8 estimators are actually immediately you can get. So those estimators are given in this Tripathi and Kumar. So the idea is here, in the place of this x bar and y bar, because these are the estimators of the common mean, I can use estimators, the alternative estimators, or we can say better estimators of x bar and y bar. Okay, so I collected all the estimators and substituted here. So these are actually this mu hat ZD. Okay, so this mu hat ZD is the estimator proposed by Grable-Dill. As per the name, ZD is written. So I'm just proposing these estimators, just plugging the existing estimators. Mu k is the estimator proposed by Murray and Krishnamurthy. See, the common mean estimator is being plugged here to get an estimator of the power of the variances, we can say. So similarly, TK, the estimator proposed by Tripathi and Kumar, BC1, Brown and Cohen, BC2, like that. So the procedure remains same, just I'm plugging in the estimator. Now, similarly, we can get for this negative powers also. Okay, so I'm not going to negative parts. Now, these are the estimators we have obtained when there is no order restriction, just the plugging the estimator, the existing estimators of the common mean in X. Okay. Now, when there is order restriction, that is beta 1 is less than equal to beta 2, if it is given, we can actually, so obviously the corresponding estimators will not be good. So the idea is to obtain some better estimators. So under this condition, as I told you, we can use the isotonic regression of the corresponding estimators. That is the estimator of beta 1 and the estimator of beta 2. So using the isotonic regression version of this estimator with the weights mn, so the weight actually you can choose, so you have to choose the weight in such a way that the original, when there is no order restriction, you are actually coming back to the original estimator basically. So that's the idea, or you can actually propose your weight as per your choice. So the formula that we are using, that is given by Barlow et al., that is we call it is minimax formula. So the estimator that we are proposing for this beta 1 power c and beta 2 is this formula. Okay. So the formula is ABST here is the weighted average of all those estimators. Now we are using the MLE for the isotonic purpose, and the estimator for beta 1, we are getting D hat 1 CML. That's the minimum of this and this. And D2 hat CML is maximum of this and this, because when the order violation is there, so we are actually reversing the estimators here. We are taking the average of those. And though we are not able to prove it theoretical, so we'll do some numerical comparison. So as I told you that all the these isotonic estimators, the isotonization technique have been used only for the MLEs. So here we have also used for the unbiased estimator, because we have obtained the unbiased estimator. So using the unbiased estimator, we have also obtained the minimax estimator for the power of the variances. Now, as I also told, we have various estimators. We have just proposed various estimators. Just we can see here. This beta 1 GD, beta 1 KS, beta 1 MK, beta VC1, like that. So all the estimators can be used for this purpose. So similarly, we have obtained this D hat C1 GD, D hat C2 GD, like that. All the estimators we have proposed, which we call the estimators under order restriction using the minimax formula. See, there are a lot of estimators, in fact 9 estimators for beta 1 power C, 9 for beta 2 power C. Now, after we propose all these estimators, what we do? Because just proposing the estimators, it does not fulfill our target basically. So we have to say whether these estimators are good or bad, or how can we use in practice. So for that purpose, we introduce a group of transformation that is called affine group of transformation to our model, which is given by this HABX, which is AX plus B. So under this transformation, the sample X bar, Y bar, Sx square, Sy square, the statistics, they are actually transformed in this way, and the parameters will be transformed to this mu will go to A mu plus B, beta 1 will go to A square beta 1, like that. And using this sufficient statistics, we can actually obtain the form of an affine equivalent estimator, which is given by this D psi 1, where this psi 1, any positive function, and T1, T2 are given by this. So the target here is to obtain, so now this is a class of estimator. So we are trying to get a condition, or we can say a procedure which may give improvement for this class of estimators. Can we improve this class? So the target is basically this. So if this class is being improved, then this class actually contains all the estimators that we have recently proposed in the last 2-3 slides I just talked. So all these estimators are actually belonging to this class. So if that purpose is solved, then I can actually give a result which will definitely solve our purpose. So for this, we define 2 functions, psi1 lower star and a psi1 upper star, like this. So by defining that, I am proposing this function psi1 hat, which is given by the psi1 lower star. If psi1 is less than the psi1 lower star, and if it is greater than psi1 upper star, I'm defining psi1 upper star. So this technique that I'm going to use here, actually given by this Brewster-Gitech 1974. And the result tells like this: let d psi1 be an affine equivalent estimator of the form cysteine that we have just discussed, d psi1 for estimating beta 1 power c, and the loss function be as defined. That's the quantitative loss function we have taken. Now the estimator d psi1 is inadmissible. That means we can get an estimator better than d psi1. Okay, and if there exists some values of the parameters mu, beta 1, beta 2, such that beta 1 less than equal to beta 2, with probability that psi1 hat not equal to psi1 is greater than 0. That means if I can get a function psi1 hat such that the psi1 hat is not equal to psi1 with probability not equal to 0. That means it's actually different from, I can get a psi which is different from the original psi. Okay, then for some parameter, then I can get an estimate of estimator which will dominate this d psi1. So if that is the case, I'm actually able to get it. So this is a very weak condition, in fact. Now for the proof, I'm not going to the proof because it's very just steps. I'll just tell briefly. You need to consider the conditional risk function of this d psi1 which you want to improve. And if you look at that with respect to that quadratic loss function, it is the function this risk is actually convex with respect to this psi1. Now you can easily get the minimizing choice of this psi1, which I am getting this one. And to evaluate this expression, we need to get the conditional density of a W1 given T. So the conditional density of a W1 given T is a gamma function, so which I have actually computed. And if you substitute those values, I'll get the value of a psi1 as this one, d into something where it is being this reparameterized here, rho. So rho is basically beta 2 by beta 1. Okay. Now we can actually get to apply this Brewster-Gitech technique. We have to get the supremum and infimum of this psi value. So we are obtaining that one. Infimum is basically d, and supremum is d times something, which we denoted as psi1 upper star, and this is actually psi1 lower star. Now the Brewster-Gitech technique tells that if there exists some parameters for which this probability is greater than 0, then the risk of this estimator d psi1 hat is less than equal to d psi1. Okay. Now similarly, yes. Similarly, we also estimate this the second component, that is the beta 2 power c. So in this case, we obtain the form of affine equivalent estimator as sx power 2c psi 2 t1 t2, where t1 t2 as defined earlier. And to get improved estimator for this d psi 2, we define a function psi 2 hat as this one, as it is given here. And defining this, we prove a result as similar to this theorem 3.1. So let d psi 2 be an affine equivalent estimator for estimating this beta 2 power c, and the loss function be as given in this one. That's the quadratic loss function. Now psi 2 is defined like this. Then the estimator d psi 2 is inadmissible. That means it can be improved by another estimator if there exists some values of parameters, say mu, beta 1, beta 2, such that beta 1 less than or equal to beta 2, with probability this psi 2 not equal to psi 2 hat is greater than 0. That means the region where actually this inequality, this probability should be greater than 0. That means that region should not be empty. Okay. So then we can improve. Now similarly, the proof you can see, it's very similar to the previous one. So I am skipping the proof of this. Now the main idea of this theorem to this theorem is to apply basically. So proving theorem is not difficult one. Now we have to think a little bit practically whether it is possible to improve the existing estimator by using this technique or not. Now the first estimator that we have actually obtained is the unbiased estimator, if you look at that. So unbiased estimator is in this form. So it is actually in the form of the cysteine, that is the affine equivalent estimator, where this psi1 is 1 by a. Now, if I use the theorem 3.1, I can easily define another estimator, let's say delta hat C1U, which is actually defined like this. So in different region, we have to define the estimator. Now this estimator, we are defining using theorem 3.1. Okay, so that means as per the theorem, this estimator will improve upon this beta hat C1U if there exist some parameters where the function that is 1 by a is different from that psi 1 hat. That's the original one that we have derived actually psi 1. Okay, star. So similarly, we have also defined other estimators. If you remember, beta hat C1 GT, it is actually in that form. So again, psi 1 is given in this form. So this estimator is also improved, or you can say we construct estimator using that theorem 3.1. Similarly, the estimator that used the estimator of the Khatrisa, we are also obtaining one estimator here. And also the Murray Krishnamurthy estimator we are using, and also we are using the estimator proposed by Tripathi and Kumar, and then the estimator proposed by Brown and Cohen. There are two estimators for Brown and Cohen, so we are also giving here, and the corresponding estimator obtained using this Brewster-Gidde technique, or you can say theorem 3.1 under order restriction. Finally, the estimator that has been obtained using the grand sample mean, so which we denote by here delta hat C1 GD. Okay, so yeah, of course, finally we have another estimator, that is the MLE, which does not have the closed form expression. But what we can see, if you go back to that system of linear equations, we can have that beta 1 is given in the explicit, not explicitly, beta 1 is beta 1, the estimator is in a very nice form. So from that, we can actually numerically obtain the form of the estimator numerically. See, Sx power 2c I can take from there, means take common, and whatever left I can keep it psi 1 t1 t2. So where this psi 1 t2 t1 t2 is given by this, where this beta 1 ml, beta 2 ml are actually the mLs which will be obtained numerically. So though the closed form does not exist, but still we can find out the form. Okay, and compute it in
Dr. Tripathi, try to finish in another 3-4 minutes.
Okay, I'm actually sorry, sir. Okay, so this MLE we are also able to write in that form. Then similarly, we have the estimators for the second component, whatever the results we have derived for the first component, that is beta 1 power c. Similarly, we obtain for the beta 2 power c. So all the results you can just have a look. So I'm skipping. The same procedure will be used for the beta 2. Okay. Now what we do, since we are not able to prove the dominance of one estimator upon the others analytically, or you can say theoretically, so we employ the numerical technique, or you can say numerically we compare the risk values to see how the estimators actually behave, how one is better than the other, or what is the relationship between in terms of the risk values. So in the first table 1, we actually see the percentage of improvement of the estimator proposed by the Minimax approach and the Brewster-Gidde approach upon their original one. So if you see the values of the risk values, or we can say the percentage of risk improvement, it is actually positive. That means that all the estimators that have been obtained using the Brewster-Gidde technique, that is denoted by delta, and the Minimax approach, that is denoted by D, are actually improved. Now, these are the results what I told. Then after we get all the estimators, the improved estimators, now we have to see overall among all the improved estimators which are actually best, we can say, or better, we can say. So from the simulation study, what we observed is that the Minimax, the Brewster-Gidde technique, the estimators obtained by using the Brewster-Gidde technique are actually better than the estimators obtained by using the Minimax approach, except the MLE, which are actually competing. So we actually compare all these estimators. These are actually improved estimators we have chosen for the numerical comparison. Now, after comparing all this, we observe that there are two types of patterns. If eta star, we take actually beta 2 by beta 1. So if eta star is between 0 to 0.7, the estimators are actually ranked in terms of rank values, this risk values in this form. First, the best is your delta hat CML. The next is delta hat C1U, and then the other estimators follows. So if eta star is greater than this 0.7, then the performance will be reversed. So this delta hat CMK is the best, then delta hat CMTK, then after that all this. That means we are actually ranking the estimators in terms of the risk values. Similarly, we also did the numerical comparison for estimating beta 2 power C. So specifically, let me tell you here, we are considering C is equal to half. That means standard deviation. Okay. So in the case of the second component, surprisingly, we observed that though the percentage of risk improvement actually quite similar. In fact, all are positive and quite similar to the first component. In the overall performance, we see that the estimators which are proposed by using the minimax approach perform better than the estimators using the Brewster-Judet technique in terms of risk values for second component. So this is a little bit surprising. And this is actually obtained in the edge, that means in the boundary actually, basically, in most of the cases. And here, eta star, when eta star actually 0 to 1, mean all values of this eta star, that is beta 2 by beta 1 is basically 0 to 1, because these are ordered. So we can actually rank the estimators like this. First will come this D2 hat C, D2 ML, and then D2U, like that we can order. So finally, we present one real data for this application purpose. So this data set we have taken from this COVID-19 data from in India. So we first check that the normality for these two data sets. So normality is actually checked. Then we also test the hypothesis that the variances are ordered, which is also checked, satisfied. And also we check that the means are equal. So after satisfying all the theoretical assumptions, we finally propose the estimators under this condition. So all the estimators are actually presented here for beta 1 power C is equal to half, and beta 2 power C is equal to half. So that was the main goal. And these are the references I have taken from various sources. Thank you, sir, for giving me this opportunity, sir.
We can have one or two quick questions if is there anybody. You can unshare your.
Yes, sir. Yes, sir. Sir, as internet a little bit slow.
Okay, there is no question. I just wanted to ask one question here.
Sir.
So if we extend it to more number of populations, so
yes,
is there a
sir, actually, for these two populations, I actually faced little bit difficulty. So okay. I didn't try, but it is actually in our future work. So it is actually tedious. It's doable, I think, sir. It is doable 100%.
Okay, fine. Okay. Thank you. Sir. Okay. Our next speaker is Raju Day, and so I think he is present. Yeah, he's there. Yeah. So his title of the talk is Estimation and Inference of New Overlap and Containment Indices for Multivariate Distributions. Raju Day is presently a research scholar in the Department of Mathematics, IIT Kharagpur. So I invite Raju Day to present his work.
Sir, am I audible?
25 minutes. Yeah.
Am I audible, sir?
Yeah, you are audible. Yeah, please share your slides. Yeah.
Are you able to see my slides?
Yeah, we are able to see. Yeah, please. Yeah, you can please go ahead. Yeah.
Good evening, everyone. The title of my presentation is Estimation and Inference of New Overlap and Containment Indices for Multivariate Distributions. This is my joint work with Professor Somesh Kumar, Department of Mathematics, IIT Kharagpur. These are my outlines. I'm going to cover all of this throughout my presentation. First, we will introduce the concept of overlap and containment indices. Then we'll see some literature survey, then some basic definitions, then some overlap and containment indices, and they are existence. And then we propose new overlap and containment indices. And finally, we conclude our presentation. Now, let me see what is overlap and containment of two intervals or two regions in Euclidean space. Now here, if you consider two intervals J1 and J2, then this is the intersection part. Now, one can quantify the containment of J1 into J2 as the length of the common interval divided by the length of J1. Similarly, the containment of J2 into J1. And also in the higher dimensional case, also we can quantify. Now what happens if we consider distribution functions over these intervals or in Euclidean spaces? Like here in the first subplot, we have plotted two normal distributions. One is normal 0, 1, another one is normal 0, 2. The blue one is normal 0, 1. And in normal 0, 2, the variability is much higher compared to the normal 0, 1. And also you can see that the containment of normal 0, 1 is more compared to normal 0, 2. And similarly here, we plotted two bivariate normal distributions. And the red one is bivariate normal distribution with mean vector 0, and the variance covariance matrix is identity matrix. And the blue one is bivariate normal distribution with mean vector 0, and the variance covariance matrix is 2 times the variance covariance matrix of the red one. So here also the red one, which is bivariate normal distribution with mean vector 0 and variance covariance matrix is identity, that is more content in blue one. Now one question arises, why you are interested to quantify this overlap and containment of distributions? Now often new biomarkers or diagnostic tests are developed for a variety of medical conditions in many subfields of medicine as well as in clinical trial. But the evaluation of the accuracy of those biomarkers or an diagnostic test is very much necessary. And the main task of a diagnostic test before make it practical is to see the ability to discriminate diseased peoples from the healthy individuals. So one possible approach is to measure the overlap or similarity between two distributions, which are based on some parameters or some measures taken from those individuals. And from the ecological point of view, Hutchinson in 1957 described a niche as a n-dimensional hypervolume, and each axis represents an environmental factors which permit a species to survive and reproduce in a community. And the concept of H niche overlap is nothing but the common share of two H niche. They are coming from two species. Now ecologists are very much interested to quantify the overlap between H niche and comparing the overlap and volume between two niche. Different hypotheses like how climates or other factors influence diversity of the species and also assembly of the communities, one can test it. Now, from the statistical point of view, to quantify the niche overlap between two species or populations, we assume that each niche follows some distributions. So the problem of quantification of niche overlap between two niche reduces to the problem of quantifying the overlap between two distribution functions. So also in most of the cases, the number of factors means their measurable ecological features is more than one. So in those cases, so we need to quantify the overlap between two multivariate distribution functions. So, and in the multi-dimensional setting, multivariate normal distributions are often used. And also we need to give some reliable estimates of overlap as well as their confidence intervals. So let us see some literature survey over this. In 1989, Inman and Berlejar consider the overlap coefficient, which is defined by OVL of two densities f and g is equal to integration of minimum of f comma g dx, where integration is taken over the common support of the two PDFs as a measure of similarity or overlap between two distributions. In 2016, Junker et al. Introduced a non-parametric approach to quantify the niche overlap between two species. In 2018, Parkinson et al. Noticed some disadvantages. Those are proposed by the Junker et al. In 2016, and they proposed new containment and overlap indices. In 2022, Parkinson, Schwartz, and Badke proposed a non-parametric test for equality of two distributions using the concept of niche overlap. In 1971, Green, 1974, Priyanka and Patritis, they defined different methods to quantify the multidimensional niche and their overlap. However, the thing is that the overlap matrix they propose that is based on testing the hypothesis that the resource using by two species, they are exactly same or not. In 2015, Sconson et al. Proposed a new probabilistic method for quantifying the multidimensional niche overlap. They define the niche overlap function in distribution function of x in RD, then the statistical depth function D center point theta, and third one is monotonicity SN1, and similarly for the G. So, practical implementation of this, we need one suitable depth function. We have to find one depth function which is the Malloy function
to complete
here. We consider different by two dishes each other. Real life for the multivariate distribution and distribution under functions. Estimators are proved for and estimators are proved for and of our proposed estimators for our
Trivariate.
Bivariate and trivariate, yes. Yes,
Critical
that's
values.
yes, yes.
So testing against H0 against the three-order alternatives here. And Bartholomew in the year 1961, he has considered that various three-order with respect to control, and they have considered that heteroscedasticity means variance are and power values. We have used the parametric bootstrap method. And for the model and assumption, we have considered the standard one-way ANOVA model where Yij is defined as a mu y and epsilon ij, where I runs from 0 to k and j runs from 1 to ni. So here Yij represents the ij's observation and mu y is unknown. And our main aim to test that H0 against H1. Here H0 is that in the k plus 1 group, that means are equal, and H1 is that mu naught less or equals to mu y, and with at least one strict inequality. And here we consider that variances are unknown and unequal. So here we considered the test statistic as d max. It is max of d vector, where d vector is d1, d2 up to dk, where di denotes as xi dot bar minus x naught dot bar by under root of si square by ni plus s naught square by n naught. Here xi dot bar is denoted as the sample mean and si square as a sample variance of I treatment. And x naught is the sample mean of 0 treatment, and s naught square is a sample mean of 0 treatment. So so we construct the test statistics, and we have to test. For that we have to under H0 supremum over under H0 probability of capital D max greater than small d max equal to alpha. Here alpha is a significance level, so we reject H0 at level significance level alpha if d max is greater than small d max. Where small d max we have to found that d max denote as a critical point for this test. So in this context, that if for d mean test we simply replace in the equation 2 max by mean, and equation 3 also d max by d mean. So we get that test statistics for mean d test. And here is the first algorithm that how can we found that critical value for the max d test. For that first step is that first we have samples xij, which from that sample we will found that a sample variance si square. From this data we have to generate bootstrap samples from normal 0 and this si square. And next, from this data, from step 2, we have to calculate test statistics value. Like max of d, we denote that as a max of d vector, d star vector. Sorry. So here x j dot bar and s j dot square star are the mean and variance of j bootstrap samples. So next we have to repeat step 2 and 3 a whose number of times, suppose that 5,000 times or 1,000 times. So from that repetition we get 1,000 number of d star max value. So we have to arrange this value in the non-decreasing order, and we have to take that 1 minus alpha quantile value, and that is our for testing we need that quantile value. So that is the critical value, or our critical value. So we reject the null hypothesis at alpha level significance if capital D max greater than small d star max. So similar way for mean d test, simply we can here we can replace in the equation for max by mean. So we get that procedure for finding critical value for mean d test. So next one can find that confidence interval from the test statistics value. As for max d test we get that confidence interval as xi dot bar minus x naught dot bar minus d star max into under root of si square by ni plus s naught square by n naught comma infinity. Next, we have to now we have considered the asymptotic versus IND test. For that, we consider asymptotic setup. Like we consider that Ni by capital N goes to Pi as minimum of Ni goes to infinity, where Ni denotes the ith sample sizes and I and capital N is total sample sizes. So capital N is summation of Ni, I equal to 0 to k. So now we previously that test statistic we can construct as a Di can be written as Wi by Ci hat, where Wi is equal to under root of Ni n naught by capital N into xi dot bar minus x naught dot bar, and Ci hat square as n naught by capital N Si square plus Ni by capital N S naught square, where I runs from 1 to k. So one can easily check that since sample variances converges in probability to population variation, so Ci hat converges to Ci, where we consider this value as a Ci. So now we define the vector W vector, then W as a W1, W2, Wk, which is defined in step 2. So W vector follows normal 0 sigma W, where sigma W is a covariance matrix, while element of that sigma W as defined as AII as a diagonal element, Ci square, which is defined in step 3, and AI is equal to sigma naught square under root Pi Pj for all I not equal to j, which is defined in previous step. So now we construct the matrix capital C hat, which is diagonal matrix, and diagonal elements are C1 hat, so C2 hat, and Ck hat, and C as a diagonal matrix C1, C2, Ck. So here capital C hat is converges in probability to C. And next we construct the test statistics as a maximum of D vector, where the maximum of C hat inverse W, and one can easily check that it is asymptotically follow normal 0 C inverse sigma W C inverse. So for MXD we have test statistics and we have to test for it. So we have to find the critical value. For that we reject null hypothesis at level alpha if Dmax greater than Fmx, so where Fmx is the critical value for this test. So for MND test, simply we can replace by max by mean. In the step 5, we get that supremum over H naught, probability of D amine greater than F amine equal to alpha, where F amine denotes as a critical value for the amine test. So here we use that parametric bootstrap technique to find a critical value for MXD and MND test. For that we have to compute, we have data Xij. From that data we have to compute sample variances Si squared. So then from that Si squared we have to calculate sigma hat W and C hat, and C hat inverse sigma W hat C hat inverse. From this calculation we can find that we can generate the data from normal 0 C hat inverse sigma W hat and C hat inverse, and then we can find the test statistics value. So we repeat the step 2 to 3 for a huge number of times, suppose 1000 times. So from that we can find the 1000 number of test statistics value using the bootstrap data. So that 1000 number of values we can arrange in a non-decreasing order. Then we take the 1 minus alpha quantile value, which we denote as a critical value for MXD test. And we reject null hypothesis H naught at alpha level significance if Dmx greater than F star mx. And we substitute the max with mean and get the mean critical value. Simply from this algorithm we can find at alpha level significance reject H naught is D amine greater than F star amine, when F star amine is a estimated value of the critical value for MND test. Next, we estimate the size and power of MaxD and MXD test. For this, we have to fix the fix the size, fix mu value and sigma square value. Since it size we are calculating size, for that we have to take the mu i's are equal. So that's why I am taking the here mu, and sigma i's are different and unknown, and ni's are sample sizes for treatments. And then after taking that, we generate the from normal distribution, normal mu sigma square, we generate the bootstrap data. Then from step 1 and step 2, from this data we have to calculate, from using algorithm, and using algorithm 2 we have to calculate D star max and F star max, like critical points. So and then and also we have to calculate the test statistics D max and DMX value. So we have to, from the step 2 data, we have to calculate two things. One is D star max and capital D max, and also D star mx and capital D mx, like test statistics value and critical points. So now we repeat 2 to 4 steps. Here you can see 2 to 4 steps. We have to repeat huge number of times, suppose 2000 times. So from that we get 2000 values of D star max, F star max, and also capital D max and capital D mx value. So now finally we can find the estimated value of sizes for max D and mx D. Like we can how many times DMX value in that 2000 value, how many times Dmax value is greater than small d star max value by total number of repetition. We get as a alpha MD, which is known as size for max D test, and alpha AMD, how many times DMX greater than F star MX by total number of repetitions. So we get sizes for asymptotic max D test. And for power calculation, simply you can see in the step 1 we have considered mu as a under H naught, mu i's are equal to mu. So for power calculation we have to take mu i's are in tree order, like mu naught is less or equals to mu I for all I equal to 1 to k. So that condition we have to put here. So we will get that power calculation for this max D and mx D, and mean D, mn D. Similar way we can replace max by mean. So from that we will get the mean D and mn D, and asymptotic version of mean D test we get size and power. Similar way. So here is the simulation studies. You can see here for max D and mean D, they are for defined values of sigma square and sample sizes that goes to close to 0.05, which we considered as alpha equal to 0.05, and MXD, MND not so close to 0.05. Here two sample sizes considered, N1 as 20, 30, 22, 25, and N2 as 10, 10, 10, 10, and defined values of sigma square we considered. Same values of variance and defined values of variance we have considered. So from that we can say that max D and mean D are close to 0.05. And here is the power estimation table. From this you can see that max D and mx D is better than other tests in power calculation. So here we have considered mu vector as a C into 1.1, 1.2, 1.2, 1.4. It is in tree order. So C can be 0, 1, 1.3. We have considered this. And when C is 0, then mu i's are all equal. So that first row values are giving that alpha value, and others are giving power. So when we increase C value, the power is automatically increasing. So from these studies, we have get that max D and mean D test accurately display and the desired significance level. And also, if we sample sizes increases, then MXD and mean D test is converges towards the significance level 0.05, and but mean D test displays more accurate approximation to the desired level. And in the power studies, max D and mx D test showed higher power values than the mean D and mn D test. So here and also mx D tends to rapidly approach to desired power levels of 1 as sample size increases. And in conclusion, we actually we propose the 4 type of test procedures: MaxD, MinD, and their asymptotic versions. Next, from simulation study, we get that MaxD and MinD test effectively preserve and intended significance level, thus enhancing their practical usefulness. And in power studies, MaxD and MXD are better than the other tests. So therefore one can conclude that MaxD is the better than the other 2 tests in the term of power and also significance level. So one can prefer to test with using the MaxD test. Here is the references. Thank you.
We can have few questions on this presentation. So if I invite any of the participants to ask questions. You can unshare your screen.
Me? I'm not asking anything.
Okay.
No, sorry.
Yeah, okay. Yeah. Okay, if there is no other question, let us thank Shubha for such a wonderful presentation.
Thank you, sir, for giving me this opportunity to talk here.
Now over to Professor Satish Kumar. So we are a little ahead of the time. We have completed in time. So you are mute.
Okay. Okay, Professor. In fact, you are completed within time, and there is time for the next session. In fact, Professor Thomas Matthew already joined. Next session started at 6:30 because probably someone will be waiting for that session, particularly attending that. It is not better to start the session early. I think so.
Yeah, you can start in at the right moment, which is mentioned there, because some people will.
So let us have a break for the small break, for if it requires, or otherwise you can interact with the team within the participants.
Yeah, I think we can have a break and then we can come back.
That's fine. Okay. Just This occasion to congratulate some support.
Hypothesis test. So, delaying you further, I once again extend a warm welcome to you on the behalf of the org.
Thank you. Take 40 minutes, sir. 45 minutes is assigned to you. You may take 40 minutes, for rest 5 minutes we'll have some discussion. Over to you, sir.
I will speak for about half an hour.
That's
actually.
excellent, sir. That's excellent.
Yeah, I want to, first of all, I want to thank the organizers, especially Dr. Satish Kumar, for inviting me to speak here. Yes, sir. And I, Dr. Muralidhar, kind.
Thank you very much.
Very silent audience there. Nice heart. Process, even though you're making a copy, you just have to show that the generic drug and the original brand name drug, they are equivalent. So equivalent means there is some chemical in the drug that is responsible for its therapeutic effect. That active chemical, the amount that enters the blood is similar, may not be the same, is similar, close enough for the two drugs. The process of doing this is called bioequivalence testing. Two drug products, you want to show their performance is very similar or close enough. So here is an example. So this is a very well-known cholesterol lowering medication. It is called Lipitor. This was the top selling drug in the world for a long time. So in 2010, you can see the annual sales figure, $10.7 billion. You are talking about a huge amount of money. Now, obviously, Pfizer, which manufactured this medication, there was a patent period during which Pfizer could sell this and make money. So the patent period in Canada and Spain expired in 2010. Immediately, you can see that in 2011, there's a dip in the sale. The US patent expired in 2011, and you see the huge dip in sale. from 10.7 billion in 2010. In 2012, the sale was 3.9 billion. So now copies or generic versions are available, manufactured by many companies, including copies manufactured in India. But Lipitor continues to be still a popular medication. So the annual sales last year, for example, it was pretty close to 2 billion. So here is another medication. This is anti-inflammatory drug used for treating arthritis and so on. It's called Humira. This came into the market in 2002. This was actually the top-selling drug in the world for a long time. In 2022, the sales figure is 21.2 billion. A lot of money there. So in 2021 and 2022, it became the second top-selling drug because of the COVID vaccine. The COVID vaccine became the top-selling drug. So the price of Humira is about 7,000. Now some copies have started becoming available now. So the copy will cost about $995 per month. Still, this is a lot of money. But if the generic copy was not available, you can see the price, $7,000 per month. We define what is called the biological availability of a drug or bioavailability equivalent if they provide. Therapeutically equivalent means, for example, Lipitor and a copy will provide the same extent of reduction in cholesterol. That is therapeutically equivalent. Bioequivalent means the active chemical that shows up in the blood is similar for the two drugs. And there is this fundamental bioequivalence assumption, which is pretty much accepted. So the amount of the chemical that shows up in the blood, that eventually determines how effective the drug is therapeutically. Now let's see what type of data will be used for bioequivalence testing. Okay, so here is a drug that is used for treating epilepsy. It's called mysolin. The active chemical in mysolin is called primidone. And mysolin comes as 250 milligram tablet of primidone. So here's what you will do. Let us say mysolin is a brand name. And let us say I manufactured a copy. And I want to show my copy is similar to mysolin. So here is what I will do. So let us say I am in this study to find out if the copy is similar to mysolin. Let us say I will take the copy or mysolin, then measure the concentration of primidone in the blood over a certain after waiting for some time called a washout period, so that the drug I took initially, that is called a washout period. That will depend on the drug. Some people will take the drug in the order R followed by T, and the second group will receive the drugs T first followed by R. This is called sequence 2-period design. There are 50 studies. 2 of them will receive the R first followed by T, the remaining 25 by R. Means you do a joint analysis, joint modeling of any 2 of them. The most important ones are AUC and Cmax actually, or you can do all 3 of them. And usually we analyze the data after taking the logarithm, because these quantities have been noticed to follow the log normal distribution. So we'll talk briefly about this. And 2 problems of interest. One is you want to test if the mean vectors of the responses are close enough. So I have data on the test drug and the reference drug. They have the corresponding means. After I take the log transformation, sample size, we will add A1 and A2, call it capital A. We know that A1 and A2 follow Wishart distributions. Is a convex combination of the quantities B1 and B2. Actually, this is a convex combination of A1 and A2. That's a typo there. Now let us think of the likelihood ratio test statistic for testing sigma 1 equal to sigma 2. So here is the LRT statistic after you do the power 2 out of 2 over n, lambda to the power 2 over n. Lambda is the LRT statistic. And being an LRT statistic, we know that quantity has to lie between 0 and 1. Now, motivated by this expression for the LRT statistic, what we will do is we will use this to define a criterion for testing the equivalence of sigma 1 and sigma 2. I will call that theta 1, sigma 1, sigma 2. All I have done is I replaced the B1 and B2 with sigma 1 and sigma 2, and we'll keep W1 and W2 as two numbers between 0 and 1, adding up to 1. W1 plus W2 equal to 1. So this is the criterion I can use to test if sigma 1 and sigma 2 are close enough. So if this quantity is equal to 1, if this quantity is 1, that means sigma 1 is equal to sigma 2. If this quantity is small, then sigma 1 and sigma 2 are very different. So here we have a criterion for assessing how close sigma 1 and sigma 2 are based on the properties of the LRT statistic. You can have a sample dependent choice of W1 and W2, or you can simply choose them to be half, because the criterion can be defined even before you decide to collect the data. So I'm going to focus on this criterion with W1 and W2 equal to half. I will call that theta 2. So that means it is determinant of sigma 1 to the power half times determinant of sigma 2 to the power half over determinant of sigma, where sigma is simply sigma 1 plus sigma 2 over 2. So this is the criteria we are going to use to check if sigma 1 are close. Criteria. It has some interesting properties. It is invariant. Look at property 3. It is invariant under non-singular transformations. That is actually pretty easy to see because of the determinant. It is equal to 1 only if and only if sigma 1 and sigma 2 are equal. You can prove that algebraically, or it also follows from the property of the LRT statistic. And what is not very obvious is probably that criterion is invariant if you replace sigma 1 and sigma 2 with the corresponding inverses. That means which I thought was nice. So if sigma 2 are close, then sigma 1 inverse and sigma 2 inverse are also close to the same extent. So that is another interesting property of this criterion. So sigma 1 and sigma. So when this is equal to 1, only if sigma 1 and sigma 2 are equal. So that means if theta 2 is close to 1, sigma 1 and sigma 2 are close to each other. So that is the alternative hypothesis. I put a threshold, let's say 0.8. I want it to be close enough to 1 if theta of value theta naught here. So we can actually compute a lower confidence limit for eta. Eta is the logarithm. And then reject h naught. Quite different if you just apply the bootstrap to compute a lower confidence limit for eta. So we did a double bootstrap or a bootstrap calibration or a bootstrap correction. And I'm going to show you if I compute a lower confidence limit by the double bootstrap, what will be the coverage probability of the resulting lower confidence limit. So here is just a snapshot of the numerical result. This is the parameter choices, 6 parameter choices in the bivariate case. We did extensive simulation, both bivariate and trivariate. So this is the bivariate case, 6 possible parameter choices of the variances and covariances for the two matrices, sigma 1 and sigma 2. And you can see with the double bootstrap, even with the sample size 10, the coverage is practically equal to 0.95. We looked at sample size 10, 20, and 30. So very accurate, very easy to implement. Numerically computing that lower confidence limit, very easy. And it is very accurate. Let's look at an example. So this is actual data I took from the US FDA website. Here we have data on bivariate data, AUC and Cmax. The data was obtained using a 2x4 crossover design with 18 subjects assigned to the sequence TRRT and 20 subjects to the sequence RTTR. So this is a drug that was used for treating depression. It is called MAO inhibitor, used for treating depression. So the brand name drug and its copy. Remember, T is the copy, R is the reference drug or the brand name drug on the market. So using the data, I computed the sum of squares and sum of product matrices A1 and A2. So there are these matrices. The question is, are these matrices close enough? Maybe they are not equal. Are they close enough? Let us see. So this is the hypothesis we want to test. So again, we are going to look at a lower confidence limit and verify if it exceeds the threshold theta naught. So the lower confidence limit by the double bootstrap is 0.731. So if I use a threshold of 0.8, clearly the lower confidence limit does not exceed the 0.8, which means using 0.8 as the cutoff value, we cannot conclude sigma 1 and sigma 2 are equivalent. So in this problem, that is the concept. So that means when this is below a threshold, we can conclude the two determinants are close enough. So there is the alternative hypothesis that the two determinants are close enough. And the null hypothesis is the complement of that. Again, by rejecting H0, we conclude equivalence of the generalized variances. So a natural test statistic is simply to take, so we're going to assume that the degrees of freedom associated with A1 and A2 are the same, by the way, which is the case in bioequivalence testing because of the crossover designs used. So this is the test statistic. You can actually express, standard multivariate results. You can express determinant of A1 as determinant of A1 times determinant of A1 star, where A1 star is Wishart with scale matrix identity and so on. So this will allow us to express the test statistic. The test statistic actually is free of any unknown parameters under the boundary at the boundary of the null hypothesis. You can actually show that this is a meaningful test statistic because its distribution is stochastically increasing in the parameter of interest. So rejecting H0 when values of t is small values of t is a meaningful thing to do. Okay, let's continue with the example. So the required personnel or the p-value has to be determined numerically. So, for example, the matrices A1 and A2. So, this is a standard choice when you want to test equivalence of variances in the univariate case, 1.25 square. So, this is the hypothesis we are testing. And statistic has value 1.017 after simplification. You can compute a p-value, turns out to be 0.0182. So, if you use a 5% significance level, we reject our hypothesis and conclude that the two generalizations are equivalent. Even though the matrices themselves were not equivalent, the generalized variances are equivalent. That is what we do. You can extend the criterion for testing the equivalence of several covariance matrices. You can simultaneously test the equivalence of several mean vectors. So the talk is based on the first article which we published a while back, and the second one is a thesis by a student. And I'll show some references in case somebody is interested. These are all books dealing with bioequivalence, the first three books. And there is this book, this 2010 book, edition. This is a very general book on testing equivalence. Basically, what Wellach has done, you take any problem where you test equality, for example, ANOVA, where you test if several things are equal, he will change that into an equivalence problem. Several means may not be equal, like in a one-way ANOVA, they may not be equal, but they may be close enough. And he will develop bioequivalence testing. And there are so many open access journals deals with bioequivalence and bioavailability and so on. So it's a very important topic in clinical research, bioequivalence. So that's the only articles on bioequivalence. And then we have the guidance documents from the FDA. If anybody is interested from the website. I think that's my talk. Thank you for.
Thank you very much. It was really an interesting one. I leave it open for some discussion. Before, let me ask you a simple question directly, sir.
You mean how the matrices A1 and A2 are independent?
So there are two things. Two matrices are independent, and similarly, two covariance matrices are quantities are independent.
Well, the two
test is accepted with a threshold level theta naught. That means they are not independent.
Okay. I'll follow your question. Right. Okay. Let me go back. Yeah. No, I understand your question. Let me go back.
Yes.
Yeah. There's an important formulational issue there.
Yeah.
Okay. Look here. We conclude equivalence not by accepting H0, by rejecting H0.
By rejecting H0. Yes. Equivalence is established by rejecting H0. That's correct.
Yeah. So was that the question? No.
So does that means it is independent? Does that mean it is independent? Can establish with that?
No. We are not talking about we are not talking about independence here because
no, we are not talking independently directly. That's right, sir.
Yeah. So what I'm saying is the matrices used here. Where is that? Yeah. So these A1 and A2 are independent.
Okay.
And they are independent, statistically independent.
Okay.
Yeah.
They are statistically independent, but
yes,
you are silent about that term. Actually speaking here, you are not straight away making a claim that they are independent, but we believe to be independent.
They can be proven to be independent. Let me put it that way.
To be independent. Okay.
Yes.
Okay.
Yes.
Good.
Yeah. But no, you are right. You have a point. I should have been explicit about it. Yes.
Okay.
I agree. Yeah.
Okay. Now let us have some discussion. I mean, some questions from the audience as well. Audience is a very important problem of testing of independence as well as testing of covariance covariances. Krishnamurthy sir, any observations, sir? Your student is presenting.
Today, I just wanted to be present just because Thomas Matthew is presenting. And since you are asking something, I may say in the slide number 15, Thomas Matthew have said that AUC is the variable. Is it correct?
Let me check. AUC is the variable. Yes.
It's a variable. And you say it is log normal.
Yes.
Is it log normal or normal?
Because it is typically log normal.
Concentration
typically log normal.
Perhaps.
Yeah. It's in practice, it has been noted that is not a theoretical observation. In practice, it has been noted that if you look at data on AUC, it is skewed and it follows the log normal distribution.
Right.
Yeah, that is now well accepted actually, and it is very rarely it is not true.
Right.
Yeah.
See, a little weak because I had my cataract removed last week, so I couldn't see very much.
Okay, sir. Okay.
No problem, sir. No issue.
Yes.
Okay. Any other questions or suggestions or? Okay, I think we will not wait anymore. Okay, we are on time, sir. So nice of you. Again.
Well, thank you. Thank you for having
thank you very much, sir.
This talk, and thank you for the questions and discussion.
Thank you very much, sir. It's my pleasure.
And once again, great to see my teacher.
Okay, sir. Thank you so much, Muli sir, for nicely managing the session in a very attractive way. And and also we would like to extend our gratitude to Professor Thomas Matthew for your support.
One more statement.
For your deliberations. Yeah, Kalyan sir is speaking something.
Yeah, Kalyan Ram sir is saying something. Yes,
I
please.
just want to say that Thomas Matthew has proven to be a good teacher.
Yeah.
Happy.
Thank you, sir. Well, I learned from people like you.
Yes, I could understand it at this age. Yes.
That's very nice.
So his talks are always attractive and very informative. In fact. And we would like to extend our gratitude to you, sir, for your special care to us, and for giving a wonderful talk to this in this platform. And we are always glad to chair the session with immediate. Yeah, I need your presence somehow here in the platform. That's why I contacted you, sir.
Oh, okay. No issue, sir. Yeah.
Thank you so much, sir. Thanks a lot.
Okay, thank you.
Thank you. In fact, we have time. No problem, Professor. We are in time. Now the next speaker, we have Kusmovsky. Professor Kusmovsky, whether he joined or not, we have to check. Professor Thomas J. Kusmovsky also, I think, I hear affected with some earlier the COVID, etc. He mentioned. I want to check whether. I think let us wait for some time. No, I can't able to, I can't locate his name the list. Let us wait some time because the talk is scheduled at 7:20. Probably he will join us by the time. Hi, Professor. Yes, sir. We have very attractive talks in the Professor Vijay Nair will join in the meantime, and also Professor Barry will join at 10. So let us wait a few minutes.
with the list of authors who studied the distribution. Various tables were developed, an approximation on how to deal with this quantity, as it was important in testing at the time. So approximate percentage points were developed. There were some methods for through Greenwood, through Edgeworth expansions and saddle point approximations and so forth. Most recently, the distribution was also studied in the paper by Albrechter and others for distributions with regularly varying tails. Now, it should be noticed that this quantity actually is very closely related to some other well-known statistics, such as the sample coefficient of variation is closely related to Tn, which has been used over the years as a measure of heterogeneity in the sciences. It's a very popular measure. Sharp's ratio is another one that comes up. It's the reciprocal of the coefficient of variation, self-normalized sum, and also the T statistics. So all of these are very closely related to what we're looking at. Understanding modeling and prediction problems in climate, hydrology, finance, social science, ecology, seismology, etc., motivates the use of this statistic. We want to understand the behavior of samples, in particular from heavy tail distributions, and how to model this, and what is the connection of that Greenwood statistic with the tail index is some of the things that we shall discuss, and also how it connects with clustering. So from peak of the threshold theory, or POT, or extreme value theory, that also motivates the use of this statistic. Now, if you look at the equation itself, it's very clear that it's actually scale invariant, but it's not shift invariant. So to make it shift invariant, we can actually also subtract observations in addition to the ratio, and people have studied this extensively. So we can look at the following ratio. So basically, we look at the set of order statistics x1 through xn related to the random sample, and then we subtract. We look at the particular level k that can be anywhere from 0 to n-1, and then we subtract this k order statistic from all the higher order statistics when we evaluate that Tn. So in connection with this, we shall call it Tnk. When we use k equals 0, this basically goes back to the original statistic, but it can also be used with the higher order of k. So that one is scale and location invariant and has been used for some time in connection with testing for extreme domain of attraction, with some references on the bottom. Now, we're also gonna work with the heavy tail or power tail distributions that for us will simply defined as follows. So the tail probability of the value exceeding x behaves like a power function at infinity. So this type of asymptotics has been observed in many data across different areas of applications, very known phenomenon that oftentimes the values are indeed heavy-tailed. So what is the connection between this tail index alpha and clustering in samples from heavy tail distribution, this connection can actually be facilitated through these statistics, either Tn or Tnk. So it's gonna turn out that if we have a small values of alpha, so the tail is light, then that corresponds to also small values of Tn when we calculate the values based on this data. While for heavy tail values, heavy tail type of data, where alpha is large, then the statistic Tn will also tend to be large. So the main results of this research actually have to do with the behavior, how this statistic Tn or Tnk, how they behave when the tail of the distribution is changing. So, and in fact, we will argue.
Then he got his PhD from University of Berkeley in 1978. He was professor of statistics and industrial and operation research engineering from 1993 to 2017. And he retired from that university in 2017. He is currently managing director and head of modeling and machine learning and advanced computing in the corporate model risk group at Wells Fargo. And while he was at the University of Michigan, he taught several courses among reliability, design of experiment, quality improvement. And he is an elected...
Dr. Gopal, if I may interrupt you, very brief is good.
What?
Let's keep it brief.
Oh, yeah. But I like to tell something. He is an elected fellow of American Association for Advancement of Sciences, American Statistical Association, American Society for Quality and Quality, Institute of Mathematical Statistics, etc. And he was the chief editor of International Statistical Review and the former editor of Technometrics. And he guided about 24 students for PhD. And he is going to talk on bias and fairness with machine learning algorithms. And we have heard bias and variance trade-off in machine learning, and he is going to talk on bias and fairness with machine learning algorithm. Thank you, sir. Now over to you, sir.
Thank you, Gopal. Hey, Satish, I am not able to share my screen. I sent you my file. Can you share it? Can't hear you, Satish. You're muted.
Okay, Professor. Okay. We can.
I just sent you my file a little bit ago. Yeah. I think my computer is blocking me from sharing for some reason.
Okay.
So while Satish is, sorry guys, I am just trying to find a comfortable spot here. Thank you for joining the call. And I am going to be talking about a very applied topic. Well, let me put it this way. My presentation is very applied. It is not very technical. It's not going to be as elegant as the previous professor, but I hope it's of interest to you. I am calling in from North Carolina, and we're actually having a storm that is going up from Florida all the way up the East Coast right now. So hopefully Satish can share my, you got my screen, you got my presentation, right, Satish? You're muted.
Oh, sorry, Professor. Yeah, Professor, we have. We are sharing. Try to share from here.
Sorry for the delay. I will be brief. I have two of my colleagues who are giving talks right after me. Yeah. Their presentations are, I would say, let me see. Let me make this.
Professor, you just give the directions so that we can move the slides one by one.
Yes, yes, yes. Let me try to make this full screen. How do I make this full screen? Not really. All right. Okay. All right. So I am going to be talking about machine learning algorithms. I'm going to go on, take my video off. And I'm going to be talking about machine learning algorithms and the challenges. One of the challenges that arise from the use of machine learning algorithms. Just to give you some context, I've been spending my last 6 years at a bank, which is one of the largest 3 banks in the U.S., Wells Fargo. And we deal with lots and lots of data, right? And we deal with data, customer data of various kinds, transactions, deciding who do we give loans to, predicting how much money we're going to make, how much money we're going to lose, all kinds of data. In addition to that, we also are now dealing more and more with text data, where people are calling us, having conversations with us, and we are also having conversational chatbots, for example, things like Siri and Alexa, which you're familiar with. So the main point here is that we have lots and lots and lots of data, right? And in this environment, people have been traditionally using before text data, what we call tabular data or numerical data. People have been using traditional statistical techniques, a lot of regression techniques, also some unsupervised learning like clustering, dimensional reduction, and all of that. So over the last 5 years or so, as you all know, machine learning and artificial intelligence techniques have taken off. So like everybody else, we are also interested in exploring, the usefulness of these techniques. What do they provide? And how can we benefit from them, right? And the challenges of machine learning is that they are very flexible models, but they're very complex. And so when they become so complex, it's very hard to see. There is no actual analytical expressions that says y hat equals some functions of the data that you can see, right? So when you cannot see that, then you put in a little x, and then you can you get as an output y hat, but you don't really know the algorithm. So that leads to all kinds of challenges, right? How do I know what is the input-output relationship? How do I know if the function, what is the other interactions, and various kinds of challenges, right? And one of the things that we are interested in is when we are using machine learning algorithms, do they lead to bias? Okay, Satish, next slide, please. Okay, so what do I mean by bias? The particular thing we are interested in is bias is related to discrimination. Discrimination of what? In our context, in many contexts, is discrimination in the context of protected attributes like sex, race, ethnicity, age, religion, and so on, right? That's really what we're concerned about. Are the algorithms fair, or are they deciding in favor of some of these groups at the expense of other groups, so they're discriminating, right? That's the question. So, for example, you applied to a loan to a bank, and is that bank favoring certain ethnic groups, certain races over others, right? And we have seen biases in pretty much, we all see biases in our daily lives, right? Whether you are trying to get an insurance, medical insurance, car insurance, for example, at least in the young people, because it is known get males. The architects, on the other hand, is in the data, and predictions have all kinds of implications for us. Right? Okay. Next. There are many other examples that are, just to give you a quick one, Amazon, and so, and you look at all of the characteristics of the historical resumes, women and potentially as males, right? Especially in the tech industry, the male is a male-dominated industry recently, right? So next slide. Okay, I've already mentioned this, right? Because the data, so when you're doing skill modeling, you don't have the ability to do all the diagnostics, look at the data, visualize it, plot it. When you have, tens of millions of observations, you can't plot that unless you sample the data. And then as such a text, images, and there's a lot, we are now able to analyze, and the algorithms are both automated and they're very complex. So we don't understand these models. So they're black box, right? And so because of this, we don't really know what to do. There's a lot of potential biases, and it's much more so we used to early. Okay, so let's talk about how do you measure and how do you measure and then unfairness, right? US thing called disparate. Are you treating two groups differently? Typically, very overtly, intentionally, or disparate impact means you may be trying to treat them fairly in your best possible way, but the impact on the two groups are different. So you may do the best you can, but if the impact is different, the results are different, then you're still treating them differently, right? But there are no formal guidelines how to measure discrimination, and there is a huge area of research right now. What metrics should I use to measure fairness or unfairness? Next slide, please. Okay, so I have included some metrics here. As I say here, many proposals, and and there are no universally agreed upon metric. And it turns out some of them have inherent mathematical conflicts among them, right? And I'm not going to get into the details of those, but I just want to say this. And there are, as I say here, there are lots of things called democratic parity, unawareness, and so on and so on. Counterfactuals. Counterfactual means, suppose I made a decision on something, and let's suppose I switch the sex. Would I have from male to female? Would I have made the same decision? So, right, that's counterfactual. What if, right? Next slide, please. Let me just go through a few of them. Unawareness means let me try as much as possible to remove the variables. So in the US, when you're giving loans, for example, you're not allowed to use any of the protected attributes. Can't use sex, race, age, anything like that in your decision, right? So you remove these things in your model, right? It's easy to implement and use, right? But what's the caveat? What is the problem? Because there are lots of surrogate variables. When you're in your model, you're using lots and lots of variables, right? But you look at the data, and then there can be some hidden variables that are basically acting as a surrogate for these protected variables, whether it's age or race, right? Or sex, right? So it's hard to detect, particularly when you're using, these days people use hundreds of variables in their model and using automated variable selection techniques, right? Okay. I already mentioned counterfactual fairness. Let's go to the next one. Next slide, please. Okay. So here I have the only slide, I guess I have two slides where I have some mathematical notation. So let's suppose y is a response variable, whether a person, let's say a prisoner relapses or not after he or she is released. And then you have a bunch of background variables, right? Education, age, sex, criminal history, and so on and so on. And y hat is a decision, is your prediction. It's a binary prediction you're making, right? It's a result of an algorithm, right? Let's say a parole board uses to predict whether the person is going to relapse or not. And they do this over a period of time. They use it over a period of time. And then A is the protected attribute, right? A is the protected attribute, gender, for example, right? Or age or race or whatever, right? So demographic or statistical parity means that the probability, right, your prediction, y hat, it should be the same. A is equal to 0 means, let's say, female. A is equal to 1 means, let's say, male. Your prediction should be the same for males and females, okay, regardless of what the x is. Regardless of what the x is, your prediction should be the same, okay? This is called demographic parity, and let's say you are required to enforce this, right? Now let's think about this issue, right? The problem with this is it is quite well known that females, women, right, once they are released, they commit crimes a lot less than males. A lot less. It's well known, a lot of evidence. So should you enforce this parity? That's the question. Should you enforce it? Because you should not, because the males and females should not have the same parity, right? So right away you see a problem with this, right? Next slide, please. So let's focus on what's in blue. This is called conditional parity. The conditional parity is saying that given some variable, here I call it u, the probability that your prediction should be the same, right? For example, in banking, we often condition on your credit score. Your credit score is what how based on how you have behaved over the period of time, you've gotten credit, you've paid off, credit cards, auto loans, or whatever. Now you're looking for a housing loan. Given your credit history, that's you, we should treat you the same, right? But as I told you, right, and then there is this conflict between group parity, which is university admissions, versus individual parity, I told you, right? So there are a whole bunch of things. The issues here is any particular metric you come up with, you can find problems with it. That is the issue here. Next slide, please. Next slide. Okay. So what I'm going to do is I'm going to talk about the sources of biases, and then I'm going to, talk about how to mitigate them, right? So I should probably go faster, right? As I said, the biggest source of biases is, of course, the data, right? Historical data. Typically, our data, historical data I gave you the example of people in the high-tech industries. There are more males than females. Data are severely imbalanced. And so these biases accumulate over time. The case of the credit lending, the blacks have been discriminated over time, so they have an accumulated lot of wealth, and so now we keep on discriminating them, right? So things like that. Next slide, please. Next slide. Oh, let's skip all this, right? I'm running. There are a lot of bias. Okay, this is in semantic bias in language models. Let's skip this too. Okay, so I'm now just essentially repeating what I've said. Why there is bias when you have large data sets and you're using semi-automated algorithms, and so you're not having a human in the loop, then the algorithms can really learn. These are very flexible non-parametric algorithms. They're trying to fit the data very well. Of course, they're going to learn all the biases in the data, and then that's what they're going to regurgitate, right? Next slide, please. how do I debias and the bias in the data and mitigating, I should say unfairness, right? Not fairness here, right? And I'm not going to have much time, so I'm going to go through just these slides, right? So one of the things that people propose is you scrub the data, you clean the data as much as you can, right? And so there's a lot of efforts to say, let me take a look at the data, let me have some automated algorithms that go through and make sure that the data is more representative. If there are more women, fewer women than men, I would underweight the men and I would overweight the women, for example, all of those kinds of things, right? The challenges with that is, when somebody is scrubbing the data to look for biases, you hope that that person has the best intentions. We use algorithms, algorithms can be wrong. But then if you're not managing it, if there is no way to supervise that, people can, and you give them an opportunity to change the data, then they can do it in many, many different ways. So, and then of course the other thing is that what is bias in the data, right? That's also a very subjective thing, right? So that is an area that is really has a lot of challenges as well. Now, the other thing is when you're developing models and you're choosing variables, what's we call feature engineering, can I do this very carefully? Can I develop models? For example, I can have a multi-objective optimization where I have an optimization rule is that I want to optimize a loss function subject to some optimizing some metric of fairness. So I can do that as well, right? And then the third item there is model testing and assessment. Once you have developed a model, I test it to see if it is fair or not, right? And that we do now in banking. Once somebody has developed a model, there is an independent group that actually tests the model to see if it is fair or not, right? And then, of course, you got to deploy the model, use and monitor over time. So there's a lot of effort on these areas. Some of them are very technical work. Unfortunately, I think these problems are not going to be solved by technical work because they're very conceptual problems. And so, it's really a hard problem, but, we need to figure out how to address potential issues for bias. And as I said, my talk is not about solutions, but more about problems. Next slide. I'm going to skip a whole bunch of slides and come to okay, let's skip this. Skip this. Skip a bunch of slides. Skip. Yeah. So there's some math there that I'm skipping. Okay, skip, please. I had an example, which I don't have time to get into it. Next one. Okay, next one. Next one. Okay. All right, let me just summarize, right? So fairness is a critical consideration in modeling. And as I said, there are a whole bunch of areas of application, whether it is finance and credit lending, social justice, criminal justice, right? Whether you're going to use an algorithm to review resumes, whether you're going to use an algorithm to do, whether somebody is violating a policy or not. And this a whole bunch of areas where fairness comes up, and it's becoming a bigger issue when there is with machine learning and huge amounts of data. But there are also huge challenges in implementation. The research area for us is techniques to debias or mitigate, how to clean, should protect. One of the bigger things is questions a lot of people in this research in this area are telling us is, government regulations should not tell us you shouldn't have access to protected data. In fact, people are saying that it's better to have access to protected data, but then he sends you the slides. If you're interested, take a look at the paper that we had published. Rahul in my team, who's going to be talking in about a half an hour or so, he's leading research in the natural language processing area. A lot of interesting problems in these areas, and I'll stop here. Thank you. Satish?
Yeah.
Yeah, Gopal, sorry.
Any clarification needed from the audience?
Yeah.
Any questions or clarification needed from the audience? No? Thank you, Professor Nair, for your interesting applied talk. Thank you very much. Thank you.
Bye-bye.
Over to Professor Satish.
Thank you, Professor Nair, for very interesting talk. In fact, it is very helpful to those who wish to work in that direction of especially in the machine learning perspectives. And we are very much grateful to you, Professor, for your support to our activities, our conference. Yeah. Now let us move to the. Also, we wish to thank our chair, Professor Gopal sir, for your nicely managing the session and your support. And we expect your continual support from each of you professors. Now let us move to the next session, because we have, as mentioned earlier, we have two speakers there in this session. And Professor Bhagilakshmi, please introduce the chair and do the needful for the smooth running of the session. Bhagilakshmi? Yes, Manoj Kumar is here to chair. Yeah. Bhagilakshmi?
Okay. Wish you a very happy day, ma'am, and all the participants. Actually, this session is the start with Avnish Bhattacharya and Wills. She is from the Frago, USA, and his title of this presentation is using Markov boundaries approach for interpretables and generalization future selection. So I think take too much without taking too much time. So I discuss. So I want to some information about this ma'am. She is a senior quantitative analyst, specialist in the statistical modeling and machine learning. And see, I also learned some papers, ma'am's papers. She did complete her PhD in 2000 during the 2015 and 2020, and a lot of these publications are based on the Bayesian Quasi models, and which are very applicable in right now times, very applications. So I would like to ma'am Avnish Bhattacharya ma'am to deliver his lecture ma'am. So over to you ma'am. Please start your lecture ma'am. Over to you.
Thank you for the kind introduction, Dr. Kumar. I will start sharing my screen and let me know if you can see it, okay? Okay, can you see the screen?
Yes, ma'am.
Okay, thank you so much.
Yes, it is visible.
Okay. So, as Dr. Kumar mentioned, I'm going to talk today about, with a lot of data, there are people use a lot of predictors, especially when Vijay in his talk was mentioning, people in machine learning use, thousands of predictors and do automated feature selection. And sometimes those features may make sense, or, sometimes they do not necessarily make intuitive sense. So ideally, people around the world, when they use these algorithms, you would want to ensure that the features that are being used in these algorithms have some causal implications. So that was the main idea when we started working on this research. So if we can identify some intuitive, causally interpretable features for the subsequent machine learning algorithms. And we finally took up the Markov boundary approach. So I'm going to talk about, this specific approach of feature selection and how it can be used to improve the performance of machine learning algorithms. So, as I said, typically, the ML models use a large set of predictors. A lot of the time, these predictors would have a high amount of correlation between them. And sometimes these features are just, transformations of the source feature or the original feature. And people just throw a lot of these predictors at the algorithm, hoping that it's going to automatically select for you the most important one. The problem is that when you throw so many large features, so many features at the model, it kind of creates some instability in the model performance, such as to maybe changing macroeconomic scenarios, right? If you have the unemployment rate is increasing or decreasing, or you have high inflation, then the performance of the model can change quite a lot under these macroeconomic scenarios if your feature selection is not done carefully. Now, obviously, feature selection is a very old classical problems, and they to be very broad in their categorizations, we can think about them as filter methods, which are model agnostic subset selection, in the sense that they are independent of the subsequent model you're going to use to on these features. Then there are the wrapper methods, where you pick a subset of features, you train the model on those subset of features, and you do this repeatedly for different subsets, and you choose the best subset. Now, this subset is the best according to the model that you've used subsequently. So this is not model agnostic in that sense. And then thirdly, you have the embedded methods, where the modeling approach has automatic feature selection embedded inside it, through the regularization of some of your optimization criterion. For example, if you think about linear regression and you think about lasso, the L1 penalty, that can automatically select the features for you. So those are the embedded methods. Now, what we want here is to choose a model agnostic subset selection, so that
Sorry, Anvisha, are you changing the slides? I see only the first slide.
Do you see the introduction slide?
No, I just see the...
Yes, ma'am. Your slide is
title
not,
slide. Yeah, I just see the title slide.
Oh, okay.
Now I see the introduction slide. Now I see that.
Okay. All right. Right. And then, so as I said, finally, the wrapper methods and the embedded methods obviously depend on the subsequent algorithm that you're using, but we are kind of interested in the first set of methods, where it's model agnostic selection. So, the subset of features that we use have some intuitive meaning, irrespective of whatever model that is being that we are going to use later on these features. So that's the first set of methods of interest here. Now, the title of my presentation had the word Markov boundary. So I just want to start by, introducing what the Markov boundary means. So ideally, as I said, when you select this subset of model agnostic features, you want to identify some causal features, right? Like that would have some causal implications on your response. Now, when you select causal features, this is usually done through interventions or randomized experiment, where you have a specific trial or a design in place, and then you try to find whether your feature is causal or not. So that is, there is obviously a lot of literature on causal inference and how to carry out these experiments. However, this is not a typical problem. This is hard problems, specifically in the case of observational data. Because we do not have a lot of control on the settings, and we are just getting the data as it comes. And that is the usual scenario in the bank that I work in. We mostly deal with observational data, and if you want to learn the causal structure in the case of observational data, you have to learn the entire causal structure, right, around the target. And we'll talk about it later, but usually this means you form some sort of direct acyclic graph around the target, and you try to identify, okay, these features are the one that are directly affecting the target. So there are obviously methods that can enable you to do that, where you find the entire causal structure on all your predictors and your response. But the methods that are, and these are come under the broad umbrella of causal discovery methods. The issue is that a lot of the times the directions can be ambiguous in these methods, especially in the case of unmeasured confounders. And often the algorithms are going to give you partially oriented graphs only, which are called graphs that belong to a Markov equivalence class, because you cannot sort out the exact direction of the arrows. And in which case it remains unclear, that what the causal direction is, what is actually the cause and what is the effect. And hence, it doesn't really enable you to, a lot of the times, select the actual causal features. So that's why we thought about using just the Markov boundary of the target. And this is kind of finding the features that impact the target in a local sense. I'm going to talk about that shortly. So why the Markov boundary, right? So we have that under certain faithfulness assumptions, the Markov boundary is basically the minimal subset of features which can give us the maximum predictive power. So it assures us that with this subset of features, if you use them for your prediction, then there is going to be no loss in predictive accuracy. So if the model generating data can actually be faithfully represented by a Bayesian network, which is a direct acyclic graph, then we also know that the Markov boundary of the response is going to be unique. So you would have this unique set of features which you can get for your prediction. And the selection of these features is as agnostic of the subsequent algorithm. Whatever algorithm you want to use later on, whether it's a logistic regression, you want to use a gradient boosting machine, a neural network, doesn't really matter. The selection approach is independent of the subsequent modeling. And the most important thing is that we have this guarantee that given the Markov boundary of the target, all other variables are independent of the target. So they wouldn't add any information to your prediction problem once you have the Markov boundary of features. You are not interested in any other variables. So we have that guarantee here. Now, the concept of Markov boundary is not new. It has been, used over the years in various works, and I have just listed some of the works over here. And I just want to, give a particular example of what I mean by the Markov boundary, right? So for an example, think about default in home loans, right? Now, you might think that, okay, what are the factors that can cause to a default in the home loan? Now, obviously, a drop in income can cause a default. A change in the property value can also lead to a default in home loan. But if you think about recession itself, then if you just look at the correlation between recession and default in home loans, you might see, a high correlation. But how is recession affecting default? It is affecting it through the other variables in the internal layer here, and that is how the relationship is actually causing that high correlation. So if you condition on these two other variables, then you would see that actually default in home loans is independent of that recession. So that is what we are interested in. Can we identify the features that will ensure that the other features which might have initially a high correlation with our response is actually independent once we condition on these actual true impactful features. So that is kind of the idea. This is another example that I'm going to use once again as I move through the presentation, is that of lung cancer, right? Now, you can see this is once again a directed acyclic graph for lung cancer, and there are a lot of factors that can affect lung cancer, and we have them in blue, right? The factors that can affect lung cancer or may be caused by lung cancer itself. Now you can see anxiety, which might have a high correlation with lung cancer, is actually the correlation is through something called the smoking habits of the patient. So if you are typically an anxious type of person, there is a high correlation with smoking, which can lead to lung cancer. So that is actually the causal pathway that is causing the lung cancer. Note here that we also include in this Markov boundary features some things which we called the children. You would typically experience fatigue or symptoms of coughing. So these are also predictors that make it into the Markov boundary set. So we are not only interested in just the causal features, but also the direct effects of lung cancer as well. And we will also see some other nodes that make into this Markov boundary. I'll get into the actual definition of the Markov boundary in the later. That can have a high influence on the predictive power of the algorithm. So not only just causal features, but direct causal effects and some other variables that will help ensure that other features which might have a correlation with your response get excluded through these kind of conditional relationships that we're going to discuss. So just to give a brief outline of how the rest of the talk is going to proceed, we're going to talk a little bit about the directed acyclic graphs that I mentioned, and how they can and how they imply boundary in the context of a directed acyclic graph. Then we're going to talk about the identification algorithm itself, and the tests that we use for this identification algorithm, specifically the conditional independence tests. We are going to talk a little bit about the simulation studies, which shows the efficacy of the tests that we are using. And then finally, we are going to talk about a grouping approach, which can handle mixed data types, right? Because in the real life, we don't typically face problems where everything is continuous and nice and following Gaussian assumptions and things like that. You have a lot of we have data that violates these assumptions every time. So we need to have an algorithm that is able to handle this kind of issues of nonlinearity or non-Gaussianity and mixed data types. So we're going to talk about how we can use the algorithm to handle all these data. And then finally, we are going to show a real data application. So talking about directed acyclic graphs, usually this consists of nodes, which we can think about as the variables, and edges between the nodes. And if you have an edge between the node, then that implies a direct association between the variables, which means that if there is a variable present, then these two variables if there is an edge present between two variables A and B, then they will always be dependent. So for example, in the previous example, we saw that recession can cause drop in income, and so that's a direct association. And then we have some other nomenclatures here, which I just want to get through, so that if I use them, people can actually follow what I mean by when I say a parent or a child. So if you have a direct edge from C to D, then C is the parent and D is the child. If you have a cycle, right, like you have an edge from A to B, B to C, and then C comes back to A, then that's a cycle. And if you have a cycle in a graph, then the concept of causal flow really does not hold, because you're saying A is causing B and B is causing C, then C is causing A. So then that really doesn't make sense. So whenever we are talking about, causal impacts of variables, on other variables, we think about acyclic graphs where there are no cycles present. The final term that I want to introduce is that of the colliders or the spouse. So if you have two parents, right, like for example here C and F, who share a child D, so they're colliding on D, but there is actually no direct edge present between C and F. So then this is called a spousal relationship where you don't share direct edge, but you're connected through the child node D. So once we have these terms, we know what they mean, we can actually define what the Markov boundary of a variable is in a DAG. It actually implies by the Markov boundary of a particular feature, we mean that if we have the relationships present in the DAG, then for a particular node, if we just look at the parents, the children, and the spouse of that node, then those are the variables that constitute the Markov boundary of the given variable. So these are the three things, these are the three relationships that we look for when we try to identify the Markov boundary of a particular variable. We try to identify what are the parents of the variable, who are the children of the variable, and who are the spouses of the variable. And once we identify these variables through some tests of association or independence, once we get those set of variables, we have our Markov boundary. So talking about these relationships, right, the conditional independence relationships in a DAG. Now, so I just want to introduce the Markov condition, which says that, if you have a DAG, which consists of the vertices and edges, and the probability distribution on these DAG, then that probability distribution is said to satisfy the Markov condition if and only if for every node in the graph, that node is independent of all other nodes that is not its descendant and conditioning on its parents. So basically, if it's a direct descendant, then there would be some association definitely. But if it's not its descendant, then those variables are going to be independent of our chosen variable conditioning on the parents. So that is the Markov condition. And then we have a second assumption on this directed acyclic graph is that of faithfulness, that all the dependence or independence relationships that are implied by the DAG structure, the directed acyclic graph structure, is respected by the probability distribution that we have on this graph and vice versa. So whatever probability distribution, whatever relationships the probability distribution implies is also captured through the directed acyclic graph structure. So those are the two important conditions that we need on our data generating mechanism to finally identify the Markov boundary of any variable. Now, given that we are aware of these conditions, just let's talk about the relationships themselves. So when we say that the probability distribution respects the directed acyclic graph, what do we mean by that, right? So if there is an edge from x1 to x2 and x2 to x3, then we say that x1 is dependent on x2 because there is a direct edge, and then x2 is dependent on x3 because there is a directed edge. Excuse me. So that is the Markov condition. So basically, we are saying that x3 is going to be independent of x1 once you condition on its parent. Now, similarly, the other relationship that we have is, when you have a directed edge from x2 to x1 and x3. So marginally, x1 and x3 are going to be dependent, but once you condition on their parents, which is x2, x1 and x3 are independent. So that's the Markov condition. And then finally, the spousal condition I mentioned in the previous slide. So if x1 and x3 do not have a direct edge between them, but they share a child. So given that they do not have a direct edge, marginally, x1 and x3 are actually independent. But once you get some information on their child and you condition on that information, x1 and x3 actually become dependent. So x1 and x3 are dependent, conditioning on x2. So these are the relationships that the DAG structure implies, and we are assuming that the probability distribution that we have on our data actually respects this DAG structure, and vice versa. The DAG structure respects the probability distribution that we have. Now, given this information, let's just try and focus on if whether we can find out what the Markov boundary of the variable lung cancer would be from this directed acyclic graph. So we heard before that the Markov boundary consists of the parents, which means over here the ones that have a direct edge to lung cancer. So we have smoking and genetics, which have a direct edge to lung cancer. We also have the children of that particular node. So the children of lung cancer means ones which have an edge coming in directly from lung cancer, and that means coughing and fatigue. And finally, the spouse, which means ones that do not have a direct edge with lung cancer, but share a child with lung cancer, and that is allergy. So allergy and lung cancer have a child called coughing here, right? So why is allergy important? Think about it in this way. Say if you have coughing symptoms and would you jump to the conclusion that this person has lung cancer? But no, you are going to see the other factors that might have caused coughing. So if you know that a person has an allergy reaction or some kind of infection, viral infection, then you would rule those out first. So if you have information on allergy or whether a person has infection, then that actually decreases the chance that the person is coughing. Feature which has the highest association to your target based on some sort of test. So you test whether X is dependent on Y, conditioning on the current Markov boundary, right? And when you're starting with a null set, this is just a marginal test. And if it's dependent, then you choose the feature which has the highest association. You include it in your current set of Markov boundaries. And if it's independent, then you drop this out of your candidate feature set, and you proceed until your candidate feature set is empty. Now, once you have run through this, the forward phase once, you repeat this forward phase with a certain number of times, and that certain number of times is given by the value k here. So k is basically standing for the number of times you repeat the forward phase. And when you repeat the forward phase, when you finish the first phase, the next phase you initiate the candidate set of features by the features that were dropped out in the previous iterations. So that's how you carry out the forward phase a couple of times, and then once you have finished your forward screening, you start your backward phase, which is basically eliminating the false positives. So now you take each feature and then you test its independence on Y, conditioning on the other variables that have entered the Markov boundary, the current Markov boundary set. And if you find that it's independent, then you just drop it out from that set. So that's the forward-backward selection algorithm. Now, talking about these tests of independence that we mentioned in the forward phase as well as in the backward phase. It's challenging to choose an appropriate test here because the predictors in ML models can be numeric as well as non-numeric. The relationships can be nonlinear, and the independence test should be able to handle these different scenarios. Now, typically, when these algorithms were introduced now, just to show you the results, right? The simulation studies that showed the efficacy of this RCIT test or on the correct recovered edges of each structure. So this is testing the effectiveness of RCIT against the Fisher z-test as well as the chi-squared test, where we binned the continuous features into 30 bins and 50 bins, respectively. And what we saw was, and these are the 8 structures, the 8 DAG structures that we looked at, and each of these relationships, these edges, these relationships, we had simulation situations where we had them linear, we had linear relationships as well as nonlinear relationships. So with this, the lower recovery in these cases. The RCIT has a pretty stable performance.
Sorry for interrupting you, ma'am. Please wind up your presentation.
Yeah. I'll be wrapping up in 5 minutes. Yeah.
Yes. Okay, okay.
So you can see that from the table that the recovery for the RCIT is pretty stable, comparable to the chi-square and the chi-square test. And in fact, the chi-square tests sometimes have a lower recovery than the RCIT. And we once again used it with the FBED algorithm to see that it's correctly selecting the features. And we found that the recovery when we were using the RCIT with the FBDK was also quite good. So you can see that the recoveries in most cases are above 90%. And we had looked at different situations where we have linear interactions of the features with the response. We had nonlinear relationships. We had a GAM model type thing here where we have generalized additive model, and then we also had generalized additive models with local effects. So we tested the FBD algorithm for different cases of data generating mechanism with different amount of correlation in the data, right? So the features might have 25% to 50% correlation in the data, and we found that the RCIT was working pretty well. We found that the number of Ks did not seem to matter too much as long as it was a reasonable 2 or 3. And we found that the recovery would slightly, be better if you have lower correlation in the features. The problem with the RCIT is that, it cannot handle large conditioning sets. So if you have, a lot of variables in your conditioning sets, then you would need to increase the number of Fourier features that you are using as your basis functions. We found that as the conditioning set grows, but the number of Fourier features is constant, the false positives increase. Increasing the number of Fourier feature would control the false positive, but increase the computation time. So we aim to restrict the conditioning set size so as to control the false positives without having to tune D so that it increases the computation burden. So that's the final algorithm that we want to have, so that we can actually somehow increasing the computation time. So that usually if you restrict the size, then the number of Fourier features per variable can be limited to around 15 or 20. So we want to restrict the conditioning set size to 5 or 7. So that was kind of an ad hoc way of keep constricting the conditioning set size. And we introduced a multi-group algorithm where we kind of broke up the possible set of variables into multiple groups based on their correlation. And what we would do is we started with a particular group and applied the FBD algorithm on that particular group to select the variables from that particular group. And now we would iterate through the groups and rely on some non-parametric regression method to filter out the selected variables from the other groups. So we would do a non-parametric regression to eliminate the effect of the selected variables from the other groups. We would use the residuals and use these residuals to carry out the FBD algorithm with the RCIT test on the current selected group. And we would iterate through this process until the selection of the covariates kind of stabilize. And the advantage is that we have a lower false positive rate, and we actually had a lower computation time as well without the effort of tuning the hyperparameter of the number of Fourier features for RCIT. And we saw a pretty good average of 1 score using this kind of multi-group approach. And this approach can be actually extended to non-numeric features as well. If you have categorical features, then you just change the RCIT to a chi-square test, and you can actually handle the non-numeric features as well. So getting into the details of it or the simulation of it, I'm just going to go directly to the application on data sets. So first of all, we have the bike share data, and we used the FBD algorithm, the Markov boundary selection algorithm, to create a subset of features. So you have the performance here from the total set of features, and you have the performance from the selected Markov boundary set of features. And you can see that the test performance of the two sets remains the same irrespective of the algorithm. It remains pretty close. And actually, the gap actually decreases. The training and the test performance gap decreases when you use the Markov boundary features. And if you know that the gap is usually used as a test for overfitting, so if you use a subset of features which can perform equally well but actually give you lower gap, then that is an indication that you have a more stable algorithm in the long run. And this is applicable for the Taiwan dataset as well, which is a credit dataset used to predict default in cards. And we've applied the same algorithm here. We had the larger set of features and we have the Markov boundary of features. And we applied an XGBoost algorithm for a neural network algorithm to predict the defaults. And you will see that the test performance for the larger set is comparable to what we have in Markov boundary, maybe just very similar, and yet there is a decrease in the gap statistic, which shows that the algorithms, when on the Markov boundary features, is producing more stable performance. A sequential strategy for identifying the Markov boundary, and the method is utilizing the appropriate tests to handle the different types of predictors. We have tests that can respect nonlinearity, non-Gaussianity, as well as in case of categorical features, we can use the chi-square test, and you can actually plug in whatever test is appropriate each group. And the strategy has been demonstrated the correct Markov boundary in complex simulation scenarios while keeping a low false positive rate. And it's providing a relevant set of features that is agnostic to the subsequent predictive model and is helping in generalizing the predictive performance as well. So that's the conclusion. I'll give it back to you, Dr. Kumar.
Okay. And very much thank you, ma'am. Your lecture was really fantastic, and I hope some of these students benefited from your lecture. And really, the Markov boundary concept is really very useful for the estimation procedure, as well as for the computation point of view. I observed some points. Now, have any question from the audience? If there are any question or clarity regarding this boundary of the Markovs. Is there any query from this audience? Okay, ma'am. So once again, I heartily welcome you, ma'am. Really, your lecture was very fantastic. I enjoy from your lecture very too much because I am working in that dimension, Bayesian. Okay, but in future I will communicate with you, and I heartily welcome to Satish sir also to invite such a speaker on that platform. Really, it is very fruitful for all the statistician person or a youngster as well as a PhD students. So we are, frankly speaking, I'm getting your points, and all these results are really nice. Okay. So once again, thank you, ma'am. Thank you. And the next speaker, invite Rahul Singh, and his title is Evaluation of Generative AIs from the techniques to applications. This is also a another dimensions of this presenting, and Rahul has a lot of the vast knowledge about these AIs, and Shar has a lot of ideas regarding the applied science as well as for the research and developers with the year of experience in a statistical data analysis as well as for machine learning and the deep learning. So without taking too much time, I would like to invite the next speaker, Rahul sir. Please continue your lecture, sir. Over to you.
Thanks, Dr. Manoj. Can you see my screen?
Yeah. Yes.
Yes, it is visible. Yes.
Okay.
Yes.
Okay. So can you see the screen where I'm presenting my slides?
Yes, it is visible, sir.
Okay. So thanks, Dr. Manoj, for the introduction. So without wasting any time, I'll just get started with the presentation. So the topic of my presentation today is large language models and generative AI. This is a brief overview of my presentation. So I'm going to talk about large language models, what is language models, and what makes them large. Then I'm going to talk about generative AI and the ChatGPT phenomena that has become very popular in the last year. Some of the applications of generative AI and how banking is using generative AI in various fields. And then I'm going to touch upon some of the things that we are doing within Wells Fargo in the generative AI space. So first of all, what are language models and what are large language models? So the basic definition of a language model is a machine learning model that can predict the next word given the history of text. So given a history of words, it tries to predict the next word, and that is the basic definition of language models. Now, over the years, this definition has been modified or has improved upon to do next word prediction. So it predict the next word in a sentence. Then the second popular way language modelings are used is to predict masked words. So given an input where some words are masked, language model can identify the masked words within an input. So, and the last, but not the complete picture, you can also use it to predict the next sentence. So language modeling has evolved a lot in the last few years. It is an old concept that was introduced sometime in early 2000s. And at that time, the definition of language models was limited to next word prediction task. But over the past few years, it has been the definition has included many other tasks. For example, predicting masked words and other such tasks within the text domain. So the next picture here shows just a brief history of how these things have evolved. So most of these are deep learning models. So LSTM was the de facto natural language processing models, and that was introduced in 1997. The first neural language model that was introduced in a paper by Bengio in 2003. And so both of these concepts are very old, but the major development started happening after 2013. So 2013, word-to-vec embeddings or method of creating embeddings was introduced. Then glove embeddings was introduced, and then the pace just picked up. So around one of the major reasons of these developments was the introduction of GPUs in the deep learning world. So GPUs provided a way to increase computation power. They also provided a way to ingest more data and to parallelize these computations so that larger deep learning models can be trained. And the progression from word2vec and to ChatGPT, it just took about approximately 9 years. Now the GPU, like LSTMs and GPUs started getting used together. Attention mechanism, which is a very important component of transformer architecture, got introduced in 2015. Although it was introduced in the computer vision world, then it was introduced in the NLP world, in the transformer architecture. And then I think the starting innovations in the language modeling, which were in the form of GPT and BERT, they were introduced in 2018. And like last year, ChatGPT was introduced, and I think a lot of people know about ChatGPT and the way it has transformed the whole textual or NLP space in the last 1 year. So this is a brief history and the definition of language model. Now, where does the large now how does the large is associated with these language models? So lately, the term called LLMs have become very popular, which is a short for large. So some of the key characteristics of these large language models is that they are trained on text data, and by huge I mean trillions of bytes of data. So assuming text that is available on the internet, so that amount of data is used to train these models. Built on a technology or a deep learning architecture called transformers, so transformers are the base model for almost all the language models that are available online or that are causing these transformations. So this transformers was introduced back in 2017 in a paper called Attention All You Need by author Vashpani. And after that, there have been a lot of improvements. There have been a lot of modification on these models. The models become bigger, or a lot bigger, and have come to state of large language models. And these are a type of deep learning, deep neural networks. So how does generative AI is associated with large language models? So the basic definition of generative AI is a technology or a tools that are used to generate new content based on existing content. Now, lately, this content can be in the form of text, can be in the form of images, video, code. So generative AI can be used to generate all these different modalities like text, images, video, code, and nowadays they are also being used to produce sounds and different type of things. So for example, here if you see, I picked up this example from ChatGPT. So I provided a prompt that I want you to act as a data scientist and code for me, and I gave the model some details that I have a time series data set, and from this time period, and I want to build a machine learning model. And the ChatGPT provided me a perfect running code based on my input. So this is just an example, but similar to this, you can do a lot of other things. You can ask it to generate emails. You can ask it to generate code. You can ask it to generate images. So depending on the input, you can do called training. So it has been trained on a lot of data set, and the user is the inference stage. So that is the second stage, which is the inference stage. So so ChatGPT, as a basic model, it's a question and answering model. So it's a bot, and it was developed by OpenAI last year. But there have been a lot of improvements on ChatGPT, and they also released a model called DALL-E. So this is the right side shows an example of DALL-E. So I asked the model to give me an armchair in the shape of an avocado, and it provided me these funny looking chairs in the form of avocado. So you can see that the model is very creative, and depending on the prompt, it can generate very different things and very interesting things. So how does generative AI work in the NLP context? So as I was saying earlier, that the way to create these techniques or models involves two steps. One is the first step is training, that is involved in any machine learning model, and the second is inference stage. During training, a language model is used, and it is the basic language model training is to predict the next word in a sentence based on the content of the previous word. So the language modeling is used to train these models, and at the inference stage, you as a user, you just provide a text in the form of an input, and these models generate an output text. So for example, in this image, what you are seeing, the user is not exposed to the underlying architecture. So the user just provides an input, for example, like this, how it's going. Under the hood, these models convert these textual input into vector representations, and after conversion to vector representations, they go through multiple matrix transformations, and they are encoded in these hidden vectors. And there are two components. One is encoding component and one is a decoding component. So encoding component converts text into vectors, and then decoding component converts the text back in, converts those vectors or hidden vectors back into the textual space. And then finally, as a user, you just see this type of output from these models. I am doing all right. Thanks for asking. How are you? So the users just see that given a textual prompt, they are getting some type of an output in the form of text. But under the hood, there are a lot of matrix operations are happening. And under the hood, there is a large language model that is working on encoding and decoding these textual messages. So the major explosion that has happened in generative AI for NLP is because of these developments that have happened in the large language modeling space. So this graph just provides you like a snapshot of all the language models that have developed since 2018. So like in the earlier slide, I showed that the transformer architecture was introduced, I think, late 2017, early 2018, and BERT and GPT were developed in 2018. And after that, you can see there have been just an explosion. Like there have been many models. Different companies are working on it. Every day there are like a new model gets released, and a new model gets released, a better model gets released. So the two things are happening is over the last few years that the performance from this stage to this stage is very different. The models performing at this point are much better compared to the models back in 2018. The models are much bigger compared to models in 2018. They have been trained on much bigger data. They need a lot of computing power, but the development, like they are transforming different type of spaces. This graph gives you a little picture about the parameters. So the size of these models is measured in terms of parameters, and parameters are directly related to memory in your computing in your computer architecture. So you can see that in 2018, BERT and GPT were around 300 to 400 million parameters, and now the biggest model is 1 trillion parameters. So there is the scaling. There has been a big difference in scale in just 2 years. And then as you increase the number of parameters, the performance increases, and the model can be used for different type of applications. And now the major task is that one of the major goals in the NLP world is to reduce the space of these parameters, at the same time maintaining the performance. So this is a brief picture about the transformer architecture. So this is one block of transformer architectures, and there are many blocks. So this is called a transformer block. You can see there are two components, like very different. The left side component is called encoder. The right side component is called decoder. So as like in the initial slides, I showed the text as an input. So the input here, the input represents textual components. It can be image components, and converted into this vector space or a continuous vector space in this step, which is called input embeddings. And then you add something like a position embeddings, and there are multiple steps that happen, multiple matrix transformations that happen inside this block. So that it goes through attention mechanism. Then after attention mechanism, it goes to another feed forward neural network, and after that step, the encoder produces a hidden vector that is now goes to a decoder step. So I'm not going into too much detail, but I'm just going to go through. I'm just going through the pipeline of the sequence of steps that happen within this architecture. And in the decoder side, the decoder tries to decode these vectors, and at the end, like at the output level, you get the probabilities in over the textual vocabulary, and using these probabilities, a text out. But if anybody is interested, they can definitely go into the details of this architecture. This is a little complicated. My point of view, it is a little compared to other deep learning architectures. This is the big lot of language that being used right. Okay, so there are multiple ways or multiple versions of transformers. Model component application. I so encoder architecture. So encoder part of the transformer architecture, and they are very applications. They are application specification, named entity. So these are classification tasks. One is simple text classification, and is sequence to sequence classification. Models like GPT, transformers, Llama, they use the decoder component of transformer, and they are mostly used for generating textual content. So for example, applications like text summarization use only models. And lastly, the original form of transformer, which is encoder to decoder. So in applications like machine translation, where your input is in the form of text, output is also in the form of text. This form of transformer architecture is used. So applications of AI. So there are multiple ways in which these models are being used. So in text, it is being used in places like marketing, sales, support, general writing, note taking. If you have been following, there is models like Code Llama that can be used as an assistant while you are writing code. So that makes your coding faster and easier. It has been used for image generation. I think you can generate very, but as a human, it would be very hard to find if the images are synthetic or the person is real. But they are also using for creating 3D smart in a lot of these applications. There are certain areas where we are thinking where this might be useful. The first application is information retrieval. So banks have a lot of access. They have a lot of documents, and a simple use case is that a user given a query, a user wants to retrieve relevant content from those documents. So we are also looking into those areas. The second is the summarization, because we have, like, banks have a lot of documents. These models can be used to summarize important content present in those documents. we can automate this process and provide an assistance to the humans that are doing this manually, and this would probably reduce the time spent in these things. So internally, we have developed a product called LLM Studio that, and we are also trying to target similar applications. So currently, we are using Llama 2, which is an open source model developed by Meta, and we are targeting these applications. So now we have, like, in addition to developing these applications, we also want to analyze the responses generated by these models. So we are also doing some experiments within our groups. So we have identified 2 tasks. One is called table summarization. The second task is the verification task. And we have identified users, and we are trying to quantify the responses of these models in these metrics, which are accuracy, factual consistency, comprehensiveness, and coherence. So these are some of the different metrics along which we are trying to measure the quality of responses given by these models. So there is a lot of work going on in the LLM space, and there is a lot of use cases, and people see a lot of usefulness of these models. And hopefully we would be able to also develop better products and assist humans to make their life easier. That's it from me. Any questions from the audience?
Thank you, Rahulji. Thank you.
Hello, sir. Hello, sir. Very nice presentation, Rahul sir. But sir, I think, sir, your talk based on artificial intelligence tools in various fields, like as banking sectors and any other sectors, sir. But nowadays, sir, deepfakes are very famous. How to control, sir, deepfakes, sir? I think, sir, misuse of artificial intelligence, machine learning in sir, deepfake.
Right. So as I was like, I mentioned the challenges of these models. So there are a lot of challenges. So we have not developed or exposed any models to the users, because those pose a very high risk, and we are experimenting on the defects posed by these models. So we are currently working towards that direction, so that we can reduce the amount of defects posed by these models. So one example is the hallucination. So hallucination is something that these models produce irrelevant answers to the given input. Sometimes the answers can be irrelevant, and sometimes the answers are completely inaccurate with respect to a given input. So there is a need to identify these cases where these LLMs produce these hallucinations. So we are trying to identify metrics or develop metrics that can identify hallucinations in these models. So the work is currently ongoing, and we are trying to quantify these things or the defects posed by these models. Does that answer your question?
Okay, sir, because that's a very big challenge, sir, in the world.
Yeah. That is a very big challenge. So unless these defects can be mitigated or risk can be reduced, these models won't be exposed to the public.
Yeah. Thank you, sir. Thank you.
Okay, thank you. And thank you, Rahul sir. Your lecture was very nice. So once again to Satish sir. So
yeah.
Lecture is over. Okay. And
okay, professor.
Yes, sir. So you take this.
Thank you, Dr. Manoj Kumar, for chairing the session, and thank you so much to both the speakers of the session. They are very interesting,
very informative lecture, sir. Last
let us give a big clap to the
Arnold sir is here.
Yeah, both the speakers. Yeah. That's good.
Okay, sir. Okay, thank you, sir.
Yeah. Once again, thanking you all. Let us move to the next session. Professor Barry I see Arnold has joined, and Professor Venkatesh sir also here to chair the session. Bhagilakshmi, please introduce the chair and please do the needful for his support.
Yes, sir. Hello, everyone. We are moving on to the next technical session of ICSTC 2023 that shall be chaired by Dr. P. Venkatesan. Now, is currently serving as an advisor at the Child Trust Medical Research Foundation, Chennai. Also, he is a visiting professor at Sri Ramachandra University. He was the former head of the Department of Statistics, National Institute for Research in Tuberculosis, ICMR, Chennai. He has a lot of achievements, including Lifetime Achievement Award by the Tamil Nadu Dr. NGR Medical University for the exemplary contribution to the cause of medical education and health research by Eminent Mathematician Award by Biomathematics and Biostatistics Society, R.N. Srivastav Young Scientist Award by Indian Society for Medical Statistics. He has a lot of publications to his credit and has been the part of several national and international conferences, an excellent academician with about 4 decades of experience in teaching. We feel privileged to have you with us sharing the session today. So it's a great pleasure that I invite you, sir, to chair the session. Over to you, sir.
Yeah, please.
Okay, thank you. Thanks for a nice introduction. Thanks, Professor Satish. I think we are coming to the last session of today's in. So, Professor Barry Arnold, Association, and he's also fellow of Indian Institute of Mathematical Sciences, and is elected member of International Statistical Institute. With this brief introduction, may I call upon Professor Arnold to have his talk. Professor, over to Professor Arnold, please.
Can you hear me?
Yeah, we can able to hear you now.
Hallelujah. Because this morning no one could hear me. Okay, how do I get started here? There we are.
Upward arrow, press now button.
Does that look good?
Yeah, click on that, then you go to the entire screen.
Okay, can you see my slides?
Not yet, Professor.
You can't?
Yes. It is not there.
Well,
I think probably you have to share it.
Yeah, whether the share button that is blue in color, when it is active, and then click.
Okay, I'm not sure how to do this. I've got to. Let me go back to the picture here. Now, what do I do in order to load my slides from here? All I can see is a picture of me talking. Now, where's the instructions to load a?
Once again, please press no button. The upward arrow, no button. And then in which the enter screen.
I thought that I would just be able to.
In case of very difficulty, we can from here.
Yeah, I think we can ask Professor to send the slide so that you can display from your end.
Oh, darn. There's no instructions here for me to load the thing, and I'm not used to your system.
I think Professor Satish, I think you can help Professor to see how it can be.
Yeah, Professor. Yeah, Professor.
I think one way is ask him to send the slide so that you can display it from your side.
Yeah. Professor, just once again you try, or otherwise we can share it from here, Professor. You just send to me, mail to me, so that I shall, Nikhil will, or myself will share it from here.
Professor Arnold, you can send the slides to Professor Satish. He can display from there where you can able to talk from that side.
Can you see that?
Yeah. Yeah, good.
Yeah.
I think.
Yeah, fine, Professor. Now it is
Very
excellent.
nice, very nice. We can able to see the slides now.
Now.
Yeah, yeah.
Yeah, Professor. Yeah.
You got it. Okay.
Okay. Okay.
Please accept my apologies for being so inadequate in this system, but I think we're ready to go now, I hope. Okay, if this should change the screen, yes. Can you, is everything okay?
It's okay.
You can hear
It's
me?
okay,
and
Professor.
see,
It's okay.
Yeah, we can hear you. And okay.
and you can see my screen.
Yeah, screen. Okay, we can see the screen.
Okay, here we go. All right. I'm going to talk about bivariate proportional hazard models and some processes that are related that have proportional hazard marginals. Okay, and we're going to do the work that I'm going to report on has a lot of co-authors. I've worked with different people on this. One person, Sheila, he came was my student in Riverside. David Strauss, a colleague in Riverside. Enrique Castillo, Jose Maria Sarabia from Santander, Spain. Guillermo also from India. B.G. Manjunath, who's worked with me on the process part, but the other parts, but I'm going to just spend a little time talking about proportional hazard models. This is not new to you, I'm sure, but the general structure is as follows. We take an arbitrary distribution function. If we're talking about survival. Pardon?
This is now that
To see that.
And can you see the new picture and a new slide? So as I go through, I'm getting new pictures, right?
at present we can see that picture of the university.
That's all you can see? That's ridiculous.
Earlier you moved, but now it is not moved. Only the picture of the university building.
Well, I don't know.
Yeah.
Okay, well, I'm just going to do this. Can you see? Can you read?
Yeah.
Can you read this?
Yeah. Now it is okay.
It's not very good, but you can read it.
Click. Full screen.
Pardon? Okay, this is just the
is it
PowerPoint presentation.
Full screen.
You can just click the second, that a bottle type shape. Yeah, second from slides. Yeah, from current slide.
Yeah.
Click that.
Yeah, just a click. Not
now
working.
You said you can't see that.
It is
So
not
at the
working.
bottom, I think ask him to click to the bottom.
Oh.
Fourth key.
And bottom a small bottle type shape. Yeah.
Yeah, full.
Or otherwise you can move close.
I have no idea. I just know how to make here. This is a PowerPoint presentation, and usually you just hit slideshow from the current slide or something, and it works. But apparently, it doesn't work now.
Nothing happens when you click on that, isn't it? Nothing. It's not changed. Then it's okay. Okay, Professor.
You can't.
Yeah. Now we can see the bivariate. Yeah. That's okay.
No.
Sir, ask him to press F5. You will get first.
Just click on the F5 button.
F5 button.
F5?
Yeah, F5 button in your laptop.
I did.
On the first floor.
Okay.
You can't see it.
The first floor, F5.
Not working, huh?
Not working.
I don't know what else I can do.
Doesn't matter, so you can continue as in this way itself. No problem. Okay, Professor. Sometimes that such a things will not work. So that's because of the settings of the. Yeah. Now it is okay. Slides gone away. Once again, try to present now button. Then enter screen. Yeah, now it is coming. Now it move to the that slides. Okay. Yeah. Yeah, click on that. Again.
Is that? Can you see that?
Yeah, we can see. We can see it from beginning. From beginning, you please click there's above. There is a from beginning. Start. Now fine. Now it is excellent.
Now, can you see a picture?
Yeah,
it is fine, Professor.
Okay.
Another picture.
Another picture. Yeah, university building.
And now another title.
Yeah, great.
Names.
Yeah, names. Okay.
Okay. Well, I'm gonna, and the next slide starts proportional hazard models.
Proportional hazard. Yeah, everything fine.
Are we ready? Everything works.
Everything fine works. Yeah.
Okay. Well, I'll assume it does. You just holler if it stops. Okay, if it doesn't work. Yeah. Proportional hazard model. We start with an arbitrary continuous distribution function on the positive half line, because we're talking about survival times, which are typically non-negative. Let the density be the function of this proportional hazard random variable is intimately related to the hazard function of the base distribution f. In other words, and it is proportional. So if you have two different choices of alpha, the ratio of their two hazard functions will be a constant. Okay, and so we do have what we call proportional hazards. Notice that these things can be related to this start material is familiar to you all. I apologize for doing such simple things. Make sure we're using the same notation and thinking about the same things. If y has an exponential distribution, then you can build the proportional hazard variable with a distribution parameter f and shape parameter alpha by just taking the quantile function evaluated at 1 minus e to the minus y. So you can think of this proportional hazard as being obtained by a very simple monotone transformation to an exponential variable. Just in there's some people about a situation in which we have a rule. These things are sometimes called reverse proportional hazard models, and in those you just, instead of using the function f, you use the survival function to take on the role. And those models would have a distribution function, which is just a power of a base distribution function. They used to be called Lehmann models or reverse hazards. To know that the thing that I proportional hazards without can be called. Think about. I'm going to talk about will extend from 1 to 2 dimensions, and there are 2 ways to do that. One is to think about bivariate distributions which have marginals of the proportional hazard to form, and the other way is to consider bivariate distributions which have conditional distributions which are of the pH form. And there are 2 different ways to do that, which I'll explain. Okay. The ones talking about distributions with pH marginals, proportional hazard marginals, start out with 2 different F1, F2 absolutely continuous distribution functions on the positive half line with corresponding densities F1 and F2, and hazard functions. I'm afraid this should have been H sub I of X sub I, but they're just a ratio of the density to the survival function, not to the distribution function, but F1 divided by F1 bar. Okay, so that's the setup. And what you can do then is talk about a multivariate proportional hazards distribution with parameters F1, arbitrary distribution function F1, another one for F2, which corresponds to X2, and shape parameters alpha 1 and alpha 2. And we'll call it a bivariate distribution with pH marginals if the marginals behave appropriately. In other words, are indeed proportional hazard distributions themselves. Okay, so that's straightforward. We know to go back and remember the way that I said we could construct these random variables. X sub I will actually just be the ith quantile function applied to 1 minus e to the minus yi, where the yi's are exponential with intensity parameter alpha sub I. So if you want to construct a proportional model of this type, okay, I guess I am there for multivariate, but it's really just 2-dimensional here. We can do the thing in higher dimensions if we wish. What we can do, any distribution for y1, y2 that has exponential marginals. Now, there are tons of those in the literature. If you go back and look at, I think there was a book with a clever title like Exponential Distributions, which had a chapter on bivariate exponential distributions, which went on for pages with lots of different examples. But the most popular choices of bivariate exponential distributions that are used in practice are 3 types. There's 2 of them that were introduced by Emil Gumbel, the type 1 and type 2. A third one, I guess there's 4, the Marshall-Olkin, and the 4th one is the Farley-Gumbel-Morgenstein family. So effectively, it turns out that for many applications, the Marshall-Olkin bivariate exponential is very popular. It is an unusual distribution because it allows for ties, because the usual description of what happens to get a Marshall-Olkin bivariate exponential distribution, you look at the life of the components of a two-component system that is subject to shocks, and if there's some shocks just attack one component, other shocks attack the other component, and a third kind of shock hits both of the components. And that means that you have ties in the failure times. Now, people use that a lot, but they don't always make sure that the data that they have is such that it does allow ties. And it gets to be kind of hidden when you go to the transform to the proportional hazard marginals, because you take a Marshall-Olkin distribution for y1 and y2, you transform y1 using f1, and you transform y2 using f2, and you no longer see the ties. So it's very hard to look at the data and decide whether or not it would be appropriate to use a transform Marshall-Olkin model. The Gumbel models are simpler. Farley Morgan's done is a very arbitrary structure, but you can transform marginally to get any distribution that you wish. If you wanted to add flexibility to those models, we can postulate that each of the distributions of F1 and F2 should be a member of some parametric family of distributions. And then there's an even third, different, more creative, shall we say, possibility where we actually use a semi-parametric model where we just envision that the FIs are actually to be estimated from the data. The only thing we assume is that we have a bivariate proportional hazard structure, and we can estimate perhaps the dependent structure for the underlying Y sub i's, but the F sub i's that we are going to be dealing with have to be estimated from the data. That's a much more challenging situation. Now, I'm going to switch over now to something that I'm going to spend a little more time on, which is a case where we're talking about bivariate distributions, which have conditionals of the first kind, because there's going to be a couple of these. We just we know what distribution of x1 given a particular value of x2 is the form with a distribution parameter f1 and a shape parameter which depends upon x2. And on going the other way around, the distribution of x2 given a particular value of x1 is proportional to proportional hazard distribution with distribution parameter f2 and shape parameter that depends upon x1. What must the joint distribution look like? Now, I want to do a little aside here for well, first thing we want to say here is that we must have a situation where y1 y2 has exponential conditionals. If you wanted to conditional underlying y1 y2 variables, which will have exponential conditions. For a second, condition I don't, so trying heights it's what's a bivariate thing ever and might be reasonable and weight. That's a little easier to than what you might. In particular, if you were thinking to ask is, can you about a bivariate normal model? The assumption of the bivariate normal model is what has one silly assumption. It says that the distribution of x1 given a particular value of x2 doesn't depend on the particular value of x2. So it says that the variance of the heights of the policemen who are tall is exactly the same as the variance of the heights of policemen who are short. And I don't think I believe that. So I would use this as an argument to think about specifying my model in terms of conditionals rather than marginals. But let's get back to our pH conditionals. We're going to have a bivariate distribution which is related to the y1, y2, which is bivariate exponential, and we ask them to have exponential conditional. So the distribution of y1 given a particular value of y2 is exponential with intensity parameter that depends upon the particular value of y2. Other way around for y2 given y1. Well, it turns out I can answer that question. That distribution, if for that to hold true, the joint distribution must have a very simple form. It's a exponential family of distributions with parameters or sufficient statistics, shall we say, y1, y2, and y1, y2. And it has parameters alpha 1, alpha 2, and delta. And there's a normalizing constant, which is actually has to be obtained by integrating this thing. And it turns out to be a little bit awkward. It involves the exponential integral function, but it's something you can handle without too much trouble. So we have what here is a nice characterization of all the bivariate densities which have exponential conditionals of the form that we described. A nice exponential family. Now, it turns out where that comes from, something happened about 100 years ago. Three researchers were studying and solving the same problem, a functional equation problem. A gentleman named Stefanos in Greece, Suto in Japan, and a fairly well-known mathematician, Levi Civita in Italy. They all were looking at the following equation, which we call the Stefanos-Suto-Levi-Civita equation. And it's an equation of this form. The psi sub i's and the phi sub j's are known functions. I don't even know the names of these Greek letters. Psi sub I and C sub I are known, C sub j are known, and you want to solve for the f's and the g's. Now that's m, them in terms over here, in terms of there are a lot of there are m plus n functions to be solved from this one simple equation. It's very demanding, but as a consequence, it can be solved. The solution is, in fact, we wish to estimate the f's, i's, and the g sub j's. The solution is very simple to describe. The fi's have to be linear functions of the c sub j's, and the gj's have to be linear functions of the psi sub i's. Really easy to describe, and not only that, easy for you to prove. You can do it by taking that original equation you saw before and doing some differentiation with respect to y and x enough times to work it out. Let me just show you as an example to show you can do it yourself. In a particular case, on an envelope back, you wouldn't have to work. Suppose somebody says, and I want you to solve f1 of x times y plus f2 of x times y squared is equal to g1 of y times x cubed. I want to know what f1, f2, and g1 can be. Okay, that's the only thing you know, just that. Now, turns out that Levi Civita, Stefanos, and Suto and their proof assumed that you could do differentiation, but you can do differencing instead. And so their proof, although it's a little bit made assumptions that were not stated, it remains valid in general. So there's nothing wrong with the thing. The only things have to be is measurable for this. Now let's see what you can do here. Let's assume we'll allow you to differentiate. Okay, so you can differentiate with respect to x and differentiate with respect to y. And if you do that, you will very quickly come up and see that you can get what the solution to that one is. Even easier. Okay, here's one. f1 of x times y squared is equal to g1 of y times x cubed. Can you solve for f1 and g1? Well, that one just falls in your lap. f1 has to be c times x cubed, and g1 has to be c times squared. And if you plug that in, the only possible example where you could just, given that Suto equation, you can solve it. And that's developing the statement that if you want to prove that, you allow yourself to differentiate, and this is obviously proved. Also, obvious solution, and you can also differences differentiating. So that means that if we want to get distribution with proportional hazard conditionals of the first kind, we just have to make the usual transformation of the bivariate exponential distribution that we just saw with exponential conditionals, making the same kind of transformations that related way back here when we said how to relate. Here's the transformations that we go. We take the yi's to have exponential conditionals and define the xi's using the corresponding distribution parameters that we have there. So it's very simple to okay. this is what our conditional joint distribution looks like. I choose usually to make a different parameterization, alpha, beta, and gamma, and it's still the 3-parameter exponential family that is the exponential family, exponential conditional density. And then with that notation, you can write down what the marginals look like and what the conditionals look like. Notice that, of course, the conditionals have to be exponential because that was our criteria. And notice that the marginals are not exponential. Okay, this is a more complicated density, but in fact, what you're going to do probably to estimate parameters and do analysis, you might very well use conditional data, and you can use something called conditional maximum conditional likelihood, or sometimes called pseudo likelihood to estimate parameters. So they're feasible. Well, let's try a different take on this thing. In survival context, perhaps it's more natural to condition not on what the actual time of a component dying, but condition on the fact that the component is still functioning at a given time. Okay, so what we're looking at under those circumstances is, okay, I think I must have skipped a slide there. No, that's not it. Okay, so what we're going to ask is, what is the distribution of X, Y, that of the proportional hazard form. And what's the joint density look like? Once again, we can go back and ask the question in terms of exponential conditionals. And this is the setup for that, where we're conditioning on y2 surviving at least to little y2 time and y1 the same way. Yeah, so here, what kind of a joint distribution? It's going to have exponential conditionals, but with the definition of conditional being involving yi bigger than little yi. Okay. In that case, it's very nice. You can solve that equation very easily and get that the joint survival function, which is the thing to deal with here rather than the joint density, is of a form very similar to what we saw in the case of the exponential conditionals of the first kind. So it involves, once again, it's a 3-parameter. It's actually, when you see it, it's recognizable as Gumbel's type 1 distribution. He introduced 2 bivariate exponential distributions in a paper of his about 1958. And the joint survival function looks like so if you transform this to get pH conditionals instead making a standard transformation, it is of this form. Again, I choose to do a little differentiation, and then I can write down the original conditional density for this exponential family and find that in this case, surprisingly, with Gumbel's model, we actually have exponential marginals. So this distribution that Gumbel suggested has exponential marginals, and it also has exponential conditionals where we're thinking about the distribution of X given Y1 is equal to Y1. Okay, so it's a very nice model. And so in this case, by making the usual transformation, we end up with our conditional proportional hazard model of the second type involving parameters F1, F2, alpha, and beta, and then a gamma, which is the shape parameter that shows up from the bivariate model. In inference situations, we usually would assume that F1 and F2 are either completely known, which means you can just go right back to exponential distributions, or are known up to involve some parameters, which means that you would probably want to use maximum likelihood or something to transform to analyze the data in that situation. If you assumed that the model, for example, had Weibel conditionals, then there are only 2 new parameters to be involved, and it's a total of 5, and that's a pretty simple model that you can handle with maximum likelihood. Okay. Okay, I about time here. I think I'm going to skip introduction. and move on to try to get onto a proportional hazard processes. Okay. Let's. I think I only have about 10 more minutes. Is that right? I could go back and talk that if I end up with time, but I'm going to talk about proportional hazard process. I'm going to introduce something called the complementary power function distribution. It's a fancy name, but for an old friend. It has a distribution function of the form 1 minus x to the power alpha, where alpha is a shape parameter for this complementary power function distribution. It is an old friend because, let's go back to it, because in fact, you all know what a power function distribution is. That's a random variable which has, or a distribution that is of the form f of x is equal to x to a power alpha, where x is between 0 and 1. Okay, and this random variable is just 1 minus one of those power function distributions. Okay, so it's useful for my purposes in terms of the proportional hazard processes because of the following. The complementary power function distribution has a property that is closed under minimization. If you take two independent complementary power function distribution variables with parameters alpha and beta, okay, and look at their minimum, it has a complementary power function distribution with parameters alpha plus beta. And then the next thing is closure under complementary raising to a power. If x has a complementary power function distribution alpha, and if we choose a constant delta that's positive, then v, which is equal to 1 minus, let's see if I can get this, 1 minus quantity 1 minus x to the power delta, that's said to have, that will have itself will have a complementary power function distribution, but now with the shape parameter replaced by alpha, but now it's alpha divided by delta. Okay, so that will, those are properties that we want to use. Now I'm going to talk about two complementary power function distribution processes. One of them was introduced by Kundu fairly recently, where he had a model for prices of gold, I think it was. But anyway, and he didn't call it a complementary power function distribution, and indeed he looked at a transformed version of this. But his name is associated because we use the structure that he suggested. So what we're going to do here is we take a sequence of IID and we're going to define a process Vn star, where n equals 1 to infinity, and Vn, the nth V star variable, is going to be the minimum of 1 minus, it's going to involve n minus 1 and n. So 2, it's going to involve the n minus first uniform variable and the nth uniform variable. And in fact, you notice that this guy here has a complementary power function distribution with parameter alpha, and this one has a complementary power function distribution with parameter beta. And so the minimum of the two will, because we know how complementary power function distribution minima operate, it will have a complementary power function distribution with parameter alpha plus beta. Here, alpha and beta are just positive numbers. Okay, so the way that's set up, for every n, the distribution of Vn star is complementary power function distribution with parameter alpha plus beta. And so this is going to be a completely stationary process. It's not a Markov process. It can't be a Markov process because, in fact, when you look at n and Vn1, involves the nth and the nth uniform, and the n plus first one with the nth and the n plus first. A little thought convinces you that it cannot be an exponential process, but it's a nice, completely stationary process, and it was used by Kundu to analyze. And looking ahead, right, if we've got a completely complementary power function distribution, we'll be able to transform it into a proportional hazard distribution by our standard transformation. So we'll be able to come up with a proportional hazards process in a simple manner using this model. The second model is one that was I labeled AM, an AM complementary power function distribution process. The A stands for me, and the A stands for Manjumda, who's my co-author down in Hyderabad. And what we do in this case, we start out with a standard. We're going to have define it in terms of independent uniform random variables, okay? And we're going to have U0, U1, and the 0th term in our process is just going to be 1 minus U0 to the 1 over alpha, but that is just a complementary power function distribution with parameter alpha. So it starts like that. And then for every n subsequently, we're going to define this thing to be the minimum of, now this is where we have to be a little sneaky, minimum of two quantities. This second one, 1 minus un to the 1 minus delta, that's a complementary power function distribution with parameter delta. This one here, we start out with the fact that this thing is 1 minus the 1 minus this, okay. And the bottom line is this quantity here is has a complementary power function distribution with parameter alpha divided by alpha minus delta. And so Wn star being the minimum of those two things, okay, will have a complementary power function distribution with parameter the sum of alpha over alpha minus delta and 1 over delta. Okay, and if you do that, you can convince yourself that indeed they all have, when you add that thing up, you're just going to have that the Wn stars, all of them have a complementary power function distribution with parameter alpha. And then we said that we could easily switch over to power function to proportional hazard processes with proportional hazard marginals using the Kundu process by just taking the F0 or the quantile function applied to Vn star, and you can verify that Sn star has a proportional hazard model with a base distribution F0. In other words, it's but with parameter alpha plus beta. So it's a nice. So every Sn has a proportional hazard distribution with a base distribution F0, and it's a completely stationary process. In parallel fashion, we can look at the situation for the AM proportional hazard process, and we can reduce it. We can recognize that it, in fact, is just our usual transformation of a process with exponential with exponents. And okay, so you can do a little bit of algebra to verify that the AM proportional hazard process T sub n star does indeed have a proportional hazard distribution with parameter with distributional parameter F0 or base distribution F0 and shape parameter alpha. So this process, although it had a little more complicated definition, process that had proportional hazard distribution after transforming was a process which did have proportional hazard distributions that all had the same parameter alpha. Okay, so that's where we are. And of course, we noted that the proportional hazard, the Kundu process was stationary but not Markovian, while the AM proportional hazard process is Markovian, and it has a proportional hazard stationary distribution, started in the right stationary distribution. So it would, in order to have a completely stationary Markov chain, you have stuff in the long run distribution. That shouldn't be Moravian. That should be Markov. Okay. In most applications, what we're going to do is we're going to have some parameters in that base distribution, and that'll make things a little more complicated, but it's more natural for fitting data. I want to give an example of that, but I'm going to do it in terms of what I will call Pareto processes, so stationary Pareto processes. I want to remind you of what the Pareto distribution looks like. The classical Pareto distribution has survival function, which is of the form x over sigma, scale parameter sigma, raised to the negative of alpha power, where the alpha is sometimes called the inequality parameter, and sigma is the scale parameter. A notation is Pareto 1 sigma alpha. The model was introduced by Mr. Pareto, Wilfredo Pareto, who had a whole bunch of data on income distributions in small Italian cities, small and large Italian cities, but really small sample size. And looking at them and drawing some pictures, he drew the conclusion that that almost always the distribution of income in various populations followed such a distribution. Okay, it's the model has survived with bells and whistles and is still used a great deal in economic settings. Notice that if we had two independent Pareto standard Pareto 1, and there's, well, I call it Pareto 1, there's Pareto 2, 3, and 4. If you add a location parameter, it becomes Pareto 2. If you add a location and a scale parameter, it becomes Pareto 3. If you add a location, scale, and a shape parameter, it becomes Pareto 4. And then there's even more general models than that. If we take two independent Pareto, basic type 1 or standard Pareto models, and look at the minimum, it's of the same form. So this is exactly the kind of thing that we would like to have for our proportional hazards. And of course, it's obvious that the Pareto distribution is a proportional hazards distribution in its own form. So for a fixed value of theta, it's a proportional hazard family. And with a base survival function given by this, and corresponding quantile function if we need it down there. And so the Kondo Pareto process would now be defined to be Sn star is equal to, in terms of independent uniform 0-1 random variables, it's sigma times the minimum of the n minus first uniform random variable raised to the power of 1 minus 1 over alpha, and the nth one raised to the power of minus 1 over beta. And if you that for every n, Sn star has a Pareto distribution with parameter sigma and shape parameter alpha plus beta. Okay, and the other one, the AM process, we start out with an initial Pareto random variable t star minus 1, and the subsequent ones are obtained by taking the minimum of the n minus first values rescaled and raised to this rather convenient power. And here's the UN, and and this is all in terms of independent uniform 0-1 random variables again. And in this process, we're going to have that Tn star is Pareto sigma alpha. So this is a uniform. This is a process which has standard Pareto marginals, and it's a stationary. Okay. Now. If you go back to the complementary power function distribution processes, what you can work out with the Kondo process, you can work out the mean and the variance. Okay, and notice that if you're going to think of using the method of moments to try to estimate the parameters, this is not going to work very well because alpha and beta always appear together. Okay, and the correlation is a bit complicated, so we don't want to do that. Here's the correlation. So once you see that, you say, I don't want to mess with that for my method of moments. But what we can do is we can look at situations where we look at variation, the probability that the ith observation is less than the next observation, or that the second observation is bigger than the first. You can work that out. It depends upon whether alpha is bigger than beta or not, but it's a very simple of the standard method of moments estimate. And for the other process, the situation again is we have one parameter, right, to estimate. We have two parameters, alpha and delta, and if we just but delta does show up at additional probability, which is now delta or alpha plus theta, which allows us to estimate the parameters for that one also. Okay. If there are more parameters in the basic distributions F0, we just have to hope that we can use method of moments or maximum likelihood to get consistent estimates from them. Much more interesting, and I leave it up to you to deal with, is if F0 is completely unknown, okay? Because if that's the case, the problem is very challenging. And of course, if F0 is known, that's much easier because you can transform back to a process which has exponential marginals, if you wish, or for example, the new Pareto process where we just look directly at the pH variables themselves. So that was, but the unknown case is a challenging problem I leave you with, and I bet you're tired, and I thank you for your attention. You might think that picture is a picture of some place in India. It's not.
Oh.
It's in Riverside, California. It's a hotel in downtown which has a rather interesting structure. And this is the beach at my hometown, Huntington Beach, in a rare picture when there are no surfers there. And again, with that, I will stop and thank you again for your attention.
Thank you, Professor. Thanks for your wonderful talk. Really, it has thrown a lot of challenges for persons like me, where we are working in survival analysis for more than 2 decades, 3 decades. Now, I think Professor has elaborately discussed about the pH assumption, how this can be extended, process can be extended, various things. And particularly, he talked about 2 things. One is the distribution of pH conditionals of 1 and 2, where you said that it can be written in the form of exponential family, and we illustrated with the exponential distribution. But if you take Bible, it's not from the exponential family. How it is going to be incorporated, that's going to be one open problem. The next one is, Professor has not discussed anything about the sensory mechanism, how this can be incorporated in the conditionals. That probably for youngsters, there are a lot of problems are there. And even for writing the from the marginals to write the conditional distribution, still inherently assumes independence. Now, I think some work has been going on in the differences. So people can take this one. There's a lot of leads in this one, at least about 5 leads I can able to say, where the youngsters can work. Well, thank you, Professor, for your illustrated talk and very, very knowledgeable presentation. We are very much benefited by your thing. Thank you very much. And behalf of the organizing committee, I thank you once again. Before concluding, if any member has anything, any queries or anything like this, I think we cannot give any suggestion to the professor, but you can ask some queries or clarification. So anybody, any of the audience you want to discuss or you want to get something clarified? If nobody is there now, thank you for your wonderful talk. Really, we are benefited because we are the persons who are working survival analysis for about 4 decades. So naturally, we are very much motivated by doing the new things, particularly the processes, which we have never thought of this one. So with this, I thank you once again. Now over to Professor Satish Kumar. Thank you.
Great, Professor. Thank you so much. Very informative and wonderful talk, Professor. Let us.
Thank you. Could I just mention that I went very fast. I left out some material on hidden truncation associated with these.
Yeah.
If people are interested in that, send an email. Barry.arnold@ucr.edu, and I'll be happy to discuss or send you a copy of the slides or something of this nature. Okay.
Yeah, again, thank you, Professor. Thank you. Because particularly the type of sensor incorporate on this, probably truncation to be there. One trans. This we conclude. Thank you. Thank you very much.
Thank you, Professor. Once again, we
thank you.
Gratitude to you, Professor.
Thank you. Thanks for Professor Arnold for your wonderful talk once again. Yeah. Okay. Now, Satish sir.
Yeah, Professor. We, on behalf of the organizing committee of the International Conference on Statistics for 21st Century, we extend our gratitude to you, Professor.
Yeah. Really.
Professor
all pains to come once again.
Professor Barry, for your support to our activities and great, wonderful talks, Professor Barry, and also Professor Venkateshan sir.
No, that is very okay.
To you, Professor.
Thank you.
Also, even several are there in the group to attend the program.
Yeah, I really.
Thanks a lot, Professor. Now let us conclude today's sessions with a hint to tomorrow morning at 9 itself. For 9, please join. Yeah, Richard Burke's talk with Richard and move back. Sorry. Yes, and support. Yeah, the minds. Thank you, Professor Barry.